Thanks a lot, Norbert. Thanks a lot, Thomas. It's a great pleasure and a great honor to give the first talk of this wonderful conference. And it's wonderful for me because I spent quite a few years of my life dealing with the semantics and epistemology of theoretical terms. And in my today's talk, I want to convince you that descriptivism about theoretical concepts implies Ramsification or a Poincarean version of conventionalism. The question that is at the center of my talk is, what is the semantics of descriptions in a descriptivist theory of reference of theoretical concepts? The plan of the talk is as follows. There will be an introductory section on theoretical concepts. Second, some preliminary remarks concerning theories of reference in philosophy of language. And within this preliminary section on theories of reference, I'll distinguish three kinds of readings of the description in a descriptivist account of reference. First, factual statements. Second, semantic reading of a description. It can be viewed as a denoting phrase in Russell's famous on denoting. And finally, I will investigate a third reading to be characterized as interpreting descriptions as conceptual truth in a weak sense, not implying any metaphysical necessity or unrevisability. Let me start with the first section. Since this is the first talk of this conference, let me very briefly explain how the distinction between theory and observation is commonly drawn. Most of you will be familiar with it. The concept C is observational if and only if its referent is accessible by direct and unaided perception. This explanation was given by Carnap in his famous Testability and Meaning and was more or less shared by a number of other logical empiricists. Then, on the basis of this understanding of an observation language or an observation expression, a concept C was introduced as theoretical if and only if it is not observational. So it's a merely negative characterization of theoreticity, and quite a number of people complained about its being just a negative characterization, and for this reason, various authors at the time of Carnap's writings and Carnap's active work came up with a positive characterization of theoreticity. Concept C is theoretical if and only if its meaning is determined by the axiom of an explicitly axiomatized scientific theory. Such an understanding of theoreticity is to be found in the work of Ramsey, Hermann Weyl, also in Carnap's work, and famously in Lewis and Snead's writings, where in particular Snead makes a lot of this positive characterization of theoreticity. What I'm interested primarily in this talk is the formal semantics of descriptions, and in the context of this formal semantics, I am to deal with the formal semantics of theoretical terms. Now, arguably in the philosophy of science literature, you can distinguish between various kinds of formal semantics. First account, arguably, is the one by Ramsey, given by the Ramsey sentence. Then there's a famous variant of the Ramsey sentence given by the Ramsey-Snead sentence by Snead 40 years later. Then there's Carnap's notion of an indirect interpretation given in Carnap's famous Foundations of Logic and Mathematics. Then there's a Carnap sentence by Carnap. There is the method of indefinitely describing theoretical terms using Hilbert's epsilon operator, also by Carnap. This method is based on the Carnap sentence and is a refinement of the Carnap sentence. And furthermore, Lewis was not quite satisfied with only indefinitely describing theoretical terms, and so he came up with an attempt at a definite description of theoretical terms. Another position is that of semantic realism by Tuomela. In brief, semantic realism is the position that theoretical concepts can be treated just like ordinary concepts. There is no deviation from standard semantics necessary for theoretical statements. You can just go along with standard truth conditional semantics. And finally, there's an attempt of mine, which is based on Carnap's notion of an indirect interpretation. And this semantic explanation that I try to give of Carnap's notion of an indirect interpretation is given in a modal setting, and for this reason I describe it as a modal semantics. And in the course of my talk I'm going to explain this semantics in greater detail. Of central importance for this talk will be Carnap's distinction between direct and indirect interpretation. Brief explanation: the interpretation of a symbol is direct if and only if it is given by expressions of the meta-language and consists in an assignment of an intension or extension. By contrast, the interpretation of a symbol is indirect if and only if it is given by one or more sentences of the object languages. Now, given this principal distinction, Carnap furthermore distinguishes between two kinds of indirect interpretation. First, the definition of a defined term, and second, the introduction of a theoretical term by what he terms postulates. The introduction of a defined term is easy to exemplify. R and A may be two predicate expressions of a formal language. Predicate R is interpreted as designating the property of being rational, and A may designate the property of being an animal. And on the basis of this understanding, you can introduce the predicate H by the following axioms. All X that have the property H are such that they have the property R and A. And of course, this explicit definition of the predicate H intends to be an explicit definition of the concept of a human being. So, a human being is rational and is an animal. Just meant to exemplify the notion of an indirect interpretation with an explicit definition. Everything is very easy, very straightforward. It's not so easy and not so straightforward with theoretical terms and postulates. Given the distinction between direct and indirect interpretation, you can give the following classification of formal semantics of theoretical terms. First, Thurmiller thinks that theoretical terms are best directly interpreted. This is the position that Thurmiller calls semantic realism. Then there are various accounts of indirect interpretation. First, Carnap's merely syntactic account given in the foundations of logic and mathematics. Then there are various approaches based on the Carnap sentence. First, the Carnap sentence itself, then epsilon term reconstruction, and finally definite descriptions in the style of Lewis. Notably, all of these accounts are based on the Carnap sentence. And essentially also the attempt of mine, this modal semantics, is based on Carnap's notion of an indirect interpretation and aims to give an explicit model theoretic understanding of Carnap's syntactic notion of an indirect interpretation. Finally, the third class of formal semantics of theoretical terms is given by the Ramsey account, and there we have basically the Ramsey sentence itself and then its Sneedian refinement. This much for the basic understanding of theoretical concepts. I move on to an introductory section on theories of reference. So recall from your 101 class on philosophy of language that there are three major theories of reference. First, there is what has come to be referred as a descriptivist picture, going back to the works of Frege and Russell. Then there are causal and causal historical accounts devised by Putnam and Kripke. And third, there are hybrid accounts that combining descriptivist elements with causal and causal historical elements. The basic idea of the descriptivist picture is that in order to refer to an entity, be it an object or a concept, you are to describe that concept. And as you know, Kripke was not quite satisfied with this picture for various reasons and aimed to give an alternative of this descriptivist account. The question that confronts us in the philosophy of science, particularly if we are doing logic of science, which account of reference works best, works properly for theoretical concepts? And then I think it's uncontroversial that descriptivism is very highly intuitive. So, for example, an electron is a negatively charged particle whose charge is elementary in the sense that any other negative charges are multiples of this unit charge. Seems like a pretty stable description of the concept of an electron, which has been used for at least 100 years or so. However, there is a warning that comes with the descriptivist picture. Descriptivism may lead to a dynamic ontology and various types of incommensurability. And it's no accident that at least Paul Feyerabend held a descriptivist view of the semantics of theoretical concepts and expressed it in terms of contextual theory of meaning, basic idea of a contextual theory of meaning, that the meaning of a theoretical term is given by the ways this term is incorporated into an axiomatic scientific theory. And in this formulation, descriptivism about theoretical concepts and the contextual theory of meaning in the philosophy of science almost coincide. Purely causal and purely causal historical accounts are hardly to be found in the literature. So I'm not aware of a single paper that advances a purely causal or purely causal historical account of reference for theoretical concepts eschewing any descriptivist elements. And arguably, to my mind, even the accounts by Putnam and Kripke, which are referred to in the literature as purely causal or purely historical accounts, contain descriptivist elements, because descriptivism is so highly intuitive and it's very likely to be acceptable and true in whatever sense of true. Notably, there are some hybrid accounts, such as the one by Psillos and also a sketch by Lewis. And of these, I want to sketch briefly the hybrid account by Psillos. First condition, a term T refers to an entity X if and only if X satisfies the core causal description associated with T. Second condition, and this condition is meant to ensure stability of reference during the evolution and the dynamics of scientific theories. Two terms, T prime and T, denote the same entity if and only if, first subcondition, their putative reference play the same causal role with respect to a network of phenomena, and B, the core causal description of T prime takes up the kind constitutive properties of the core causal description associated with T. And if I understand the program of this conference correctly, then we will witness an update of this account the day after tomorrow. Notably, the core causal description associated with the theoretical term is to be taken from scientific theories in their state of the art at the respective time. And this feature is noteworthy since Psillos does not employ what Putnam calls a metaphysical understanding of causation. Rather, causation is taken as described by currently held scientific theories. The core question of my talk is, what is the formal semantics of descriptions? And to approach this question, I distinguish different semantics readings thereof. First reading, a description may simply and straightforwardly taken as a factual statement, in a sense yet to made precise. Second reading, it may be read being more faithful to the original Russellian account expounded in denoting as a denoting phrase in this precise Russellian sense I'm going to explain soon. And finally, it may be taken as a conceptual truth in a somewhat weaker sense, not excluding empirical content. And the plan of my talk is to investigate these three different semantics readings and assess their suitability in the formal semantics of theoretical concepts. In order to assess these three different readings, I'm going to conduct a little case study. Let us take not too trivial and not too complicated theoretical concepts, namely the concept of temperature. And arguably this concept is characterized, at least at a certain stage of phenomenological thermodynamics, by the following description. If the temperature of an amount of a gas changes, then the product of volume and pressure of this amount will change proportionally. The background of this description is the ideal Gauss law, also referred to as the Boyle-Charles law. So as noted, this statement was, at a certain stage of phenomenological thermodynamics, part of the causal description of the kind-constitutive properties, at least presumably, associated with the scientific concept of temperature, so this seems to be a suitable example to further investigate the hybrid account by Psillos. First semantic reading, let us investigate how sensible it is to take descriptions as factual statements. What do I mean by a factual statement? A factual statement phi is one for which truth conditions can be specified such that the truth of phi depends on the truth of its atomic components, the truth of which, in turn, depends on whether or not certain states of affairs obtain in the world. So, in brief, for factual statements, you adopt straightforward standard truth conditional semantics as it is informally explained, for example, in the Tractatus by Wittgenstein. Now, there's a brief argument why descriptions cannot be factual statements, and this is an attempt at a straightforward refutation of this semantic reading. By assumption, we accept a descriptivist or a hybrid account of reference for theoretical concepts and terms. By assumption to be refuted, descriptions in a descriptivist account of reference are factual statements. Further, by assumption, T may be a theoretical term. Then it follows from 3 and 1 that there are sentences phi subscript 1 to phi subscript n being used to refer to T that have occurrences of T, though this is easy to verify and easy to show. And usually these phi subscript 1 to phi subscript n are axiomatic description of the theoretical concept T and the theoretical term T correspondingly. Then it follows from 4 and 2 that these axiomatic descriptions have truth conditions in terms of their atomic components. This follows from 4 and 2 and the above explained understanding of a factual statement. But if these axiomatic descriptions have truth conditions in terms of their atomic components, then the term T has to have reference independently of whether or not these axioms are used to describe and thus to refer to the term T. Follows from 5. Otherwise, these axioms could not have truth conditions in the way factual statements ought to have truth conditions. And from this observation, it follows that descriptions of T, such as those given by the axioms phi subscript 1 to phi subscript m, are not relevant to the reference of T. T has reference independently of these axioms being used to describe T. And hence we obtain contradiction from 7 and 1. Hope this is acceptable. A related problem which I want to expound here as a circle of referring might be a more intuitive but also more demanding description of the basic underlying problem. So assume these phi subscript 1 to phi subscript n are factual statements and used to refer to the term T, then intuitively speakers are successfully referring to T only if these axioms are true, or at least approximately true. So in brief, this is the common sense wisdom. If you want to refer to an entity, then you are correctly to describe it. If your description is incorrect, then you won't be successful in referring to the entity. Or in yet other words, on the one hand, we need to assume the truth of descriptions of theoretical concepts in order to refer to them. On the other hand, we can meaningfully assert the truth, or at least the approximate truth, of such a description only after having successfully referred to such concepts. And this circle of referring is reminiscent of Snead's famous problem of theoretical terms. And when working out what I call here a circle of referring, then of course Snead's famous problem of theoretical terms was in the background. This formulation of the circle that I'm using to refute the factualist reading is a bit more demanding since the notion of truth comes into play in the context of these axioms. Unlike this intuitive explanation, this brief argument in this brief argument against the factual reading, no reference to the notion of truth is made at all, though this argument works independently of whether or not you is assuming the truth of descriptions in a descriptivist account of reference. This much for the refutation of the factualist reading. Let us move on to the second reading, descriptions as denoting phrases. For this, I very briefly recall the core of Russell's famous theory of description as expounded in denoting. There are basically two kinds of descriptions. First, indefinite ones, having the logical form that NF is G, which may be formalized as given here. And then there are definite descriptions having the general form that the entity being definitely described by the property F has the property G. In brief, the F is G. In more formal terms, there is an X such that X has the property F, and for all Y also having the property F, X and Y must be identical, and X has also the property G. Now, let us try to adapt this core of Russell's theory of description as much as to an extent as much as great to our little case study about the theoretical concept of temperature. So let f subscript 1 be the temperature function and phi any proposition concerning this function. Then this proposition translates to the following statement: when we transfer the Russellian theory to a descriptivist account of reference of theoretical concepts and theoretical terms. First version, first translation, there is a natural kind function x subscript 1 such that if x subscript 1 of an amount of gas changes, then the product of volume and pressure of this amount will change proportionally, and proposition phi must hold, where in phi all occurrences of f subscript 1 must be replaced by this higher order variable x subscript 1. Second translation, and this translation differs from the first one just by introducing the uniqueness condition, thus being even more faithful to Russell's original theory, of which the uniqueness condition is an essential part. There is a natural kind function x subscript 1 such that if x subscript 1 of an amount of gas changes, then the product of volume and pressure of this amount of gas will change proportionally. And for all natural kind functions x2, with that property it holds that x1 and x subscript 2 must be identical, and second subcondition, phi must hold, where in phi all occurrences of the theoretical constant f subscript 1 must be replaced by this higher order variable x subscript 1. But we are not ready yet. Note that volume and pressure are theoretical terms as well. So this proposition has to be translated as follows, where in the following translation also occurrences of volume and pressure are to be replaced by appropriate higher order variables, and we are to give an axiomatic characterization of these functions, volume and pressure. So the translation goes as follows. There are natural kind functions x subscript 1 to x subscript 3 such that if x subscript 1 of an amount of gas changes, then the product of x subscript 2 and x subscript 3 of this amount will change proportionally, and phi holds, where in phi all occurrences of f1 are replaced by the appropriate higher order variable, and where x subscript 2 and x subscript 3 may further satisfy a set of A of axioms, and this set A of axioms is obtained from an axiomatic characterization of the pressure and the volume function. Basically, this will be an axiomatic introduction of metrization, and in this axiomatic characterization, all occurrences of the constants of volume and pressure are to be replaced by higher order variables x subscript 2 and x subscript 3 respectively. And the experts on theoretical concepts will recognize that we will now have arrived the Ramsey account of scientific theories just by applying this Russellian theory of description to a scientific statement. So to recall what's the Ramsey account of scientific theories, you start with a scientific theory given as a conjunction of axioms having occurrences of non-theoretical terms n subscript 1 to n subscript k, and having also occurrences of theoretical terms t subscript 1 to t subscript n. And then, as you will know, Ramsification consists of two operations. First, replace the theoretical terms by appropriate higher order variables, and second step, bind these variables by existential quantifier, and as a result you obtain a sentence of the following form: conjunction of axioms where all occurrences of theoretical terms are replaced by higher order variables. And this is almost the same logical form that we just received by applying the Russellian theory of description to this little case studies. It just differs from the pure Ramsey sentence by this proposition phi, which you also obtain in Ramsey accounts if you are discussing atomic statements and the translation of atomic statements in this account. Nice result, this circle of referring expounded in the second section of my talk disappears. To recall, what was this circle of referring about? On the one hand, we need to assume the truth of descriptions of theoretical entities in order to be able to refer to them. On the other hand, we can judge whether such a description is true and, even more importantly, meaningfully assert the truth of such a description only after having successfully referred to such entities. This circle disappears since descriptions are not asserted but rather used as denoting phrases. So this is an important point, descriptions are not statements anymore. So we do not adopt the factualist reading of descriptions. We logically analyze descriptions as denoting phrases, not having truth values by themselves. And by this reading, we are more faithful to Russell's original theory of description. Open problems, of which I want to discuss only the third one concerning Ramsification. Must the axiomatic description be unique? Carnap says no, Lewis says yes. Second question, shall we assume a natural kind ontology? So Lewis or some philosophers of science having strong sympathies with Lewis say yes, others say no. I don't want to decide this question. What I'm going to discuss is the syntax of the Ramsey account. The syntax is very cumbersome. It's very complicated, and it deviates substantially from the practice of deductive reasoning in science. So to show this, let us go back to this formulation. We start with a very simple, perhaps atomic proposition about temperature. So let's say the temperature in this room is 20 degrees Celsius. And when translating this very simple atomic proposition, we end up with such a complicated statement. There are natural kind functions, x1 to x3, perhaps even more natural kind functions, such that these natural kind functions satisfy certain axioms where the constants are replaced by higher order variables. And if we were to perform deductions with these statements, this would be very, very complicated. And for these reasons, we are looking for an account whose syntax is closer to the standard practice of deductive reasoning in the sciences. And this problem will be addressed by the third reading, which I characterize here as Poincarean conventionalism, or as the view that descriptions in a descriptivist theory of reference are conceptual truth. Now, what is a conceptual truth? In order to clarify this, let me distinguish between two understandings of this conceptual truth. So first, one may mean by conceptual truth an a priori unrevisable and metaphysically necessary truth. Of course, this understanding of a conceptual truth is no promising candidate for an account of reference and meaning in the formal semantics of theoretical concepts, since the axioms of scientific theories would have to be taken as unrevisable, metaphysically necessary truths, and this is hardly plausible. But perhaps there is something in between. There's something in between this notion of an unrevisable, metaphysically necessary truth and the notion of a purely contingent statement. So perhaps there is a sensible notion of a statement being partly synthetic and partly analytic that contributes to the interpretation of theoretical terms. From the logician's point of view, the question is arising how to make precise this understanding of a conceptual truth. And my proposal for explaining this understanding of a conceptual truth, which is fairly in the spirit of Poincaré's philosophy of science is in turn based on Carnap's notion of an indirect interpretation, which I try to sustain with an explicit model theoretic explanation. According to this explanation, a set A of axioms that interpret a set of theoretical terms on the basis of an observation language imposes a constraint on the admissible or intended interpretations of the complete language, comprising both an observational and a theoretical vocabulary. Or more precisely, an interpretation I of the complete language is admissible if and only if either the first two subconditions are satisfied, namely I is an extension in the model theoretic sense of the given interpretation of the observation language, and second subcondition, I satisfies the axioms of the theory T, or in case there is no such interpretation satisfying these two subconditions, I is just an extension of the given interpretation of the observation language. So firstly, we are looking for interpretation that is both an extension of the interpretation of the observation language and satisfies the axioms. In case there's no such interpretation or structure, then any structure extending the given structure of the observation language are to be taken as admissible. This semantics deviates from standard truth conditional semantics in allowing for a range of intended interpretation. So each interpretation being an extension of the interpretation of the observation language and satisfying the axioms qualifies as intended. Though the uniqueness condition usually entrenched in standard truth conditional semantics is abandoned in this kind of semantics. And another important deviation is that for the valuation of truth values, we adapt a supervaluationist strategy, namely a theoretical sentence phi is true if and only if for every structure of this range of admissible structures it holds that it satisfies phi. By contrast, phi is false if and only if for every structure that is admissible is such that it does not satisfy phi. And finally, in case there are structures A subscript 1 such that it verifies phi, and another structure such that this structure does not verify phi, then the value of phi is indeterminate, as subscript A is given by the set of admissible structures. So as most of you will know, this kind of supervaluationist strategy can be expressed using modal terms, and this explication goes as follows. The sentence phi is true in the complete language if and only if box phi, where the set of worlds is given by just the set of admissible structures as previously explained. So this is just the formalization of this set of admissible structures, and the accessibility relation of this simple S5 modal semantics is given by the Cartesian product of the set of worlds with itself. Three properties of this semantics are noteworthy, I think. First, good news, this circle of referring disappears, and this circle disappears since the descriptions of theoretical entities contribute to the interpretation of theoretical terms. So no previous or antecedent interpretation or understanding of theoretical terms is presupposed by accepting a proposition as part of the description of theoretical concept. So again, descriptions are not read as factual statements having truth values independently of its theoretical concepts. Rather, they are read as conceptual truth in the weak sense and read as contributing to the interpretation of theoretical terms. So in brief, valuation of the axioms comes, in a certain sense, before the theoretical terms are interpreted. And the valuation of the axioms is the foundation of the interpretation of the theoretical terms, at least if there is an interpretation that extends the given interpretation of the observation language. This is the basic idea of this modal semantics, which is a model theoretic elaboration of the Carnapian idea of an indirect interpretation, which was spelled out by Carnap in primarily syntactic terms. Another property being noteworthy, the axioms of T are conceptually true insofar as any admissible interpretation of the complete language must satisfy on this crucial condition that there is an interpretation extending the given interpretation of the observation language and satisfying the axioms. You may characterize this notion of truth as truth in virtue of determining meaning, though the axioms are true in virtue of determining the extensions of the theoretical terms. Nevertheless, and for this reason, they are conceptually true only in a weak sense, in a weak Poincarean sense. Asserting the truth of the axioms is not void of empirical content, since in case there is no such structure extending the given structure of the observation language and satisfying the axioms, then the values of the members of the axiom sets are indeterminate. So if you use this supervaluationist logic in order to assign truth values to the axioms themselves, then the axioms end up being indeterminate in case there's no structure extending the given structure of the observation language and satisfying the axiom. And this case amounts almost, not quite, to the condition that the scientific theory is empirically adequate, as demonstrated by Geoffrey Ketland. Hopefully you agree. Another feature being noteworthy of this modal semantics is that its syntax is very close to the practice of deductive reasoning in science. So let the set A be a set of sentences such that its members do not contain any modal operators, and let phi be such a sentence not containing any modal operator. Then the logical consequence between box A and box phi in the semantics of modal logic, this relation will obtain just in case phi, not prefixed with a box operator, is a logical consequence of the set A, where this box uppercase A designates the conjunction of the axioms alpha subscript 1 to box alpha subscript 1. So basically this means that prefixing scientific statements of ordinary scientific practice with a modal box operator has no impact on the validity of deductions. So if an argument is valid without this modal prefixing in classical logic, then it will also be valid in this modal semantics. And for this reason, unlike the Ramsey account, the present modal account requires no replacement of theoretical constants by higher order variables. Also, unlike the Carnap's method of the Carnap sentence, by which he tried to recover theoretical constants from the Ramsey sentence, no such recovery is necessary in the first place. And furthermore, unlike the latter accounts, the use of theoretical constants does not depend on the Ramsey sentence being true, though in brief, this modal account is slightly nicer and slightly more elegant than Carnap's, even though it is, of course, in the spirit of the work of Carnap. Time for conclusion and summary. There are three different readings of a description in a descriptivist account of reference of theoretical concepts. first reading, descriptions may be read as factual statements. Second reading, as denoting phrases in the sense of Russell's theory of description. And third reading as conceptual truth in a weak sense, not excluding empirical content. The first reading, as I've tried to show, is provably inconsistent with descriptivism. The second reading leads to the Ramsification of scientific theories under consideration. And the third reading can be given a modal semantics that explicates, I think, very well the Poincarean notion of a non-arbitrary convention, though. So it's of utmost importance that this Poincarean notion of a convention is to be understood in the sense of a non-arbitrary statement, not to be confounded with the notion of an arbitrary stipulation. Outlook to further future research, two open problems. First problem, first open question that I carefully avoided to talk about: does scientific realism in its state-of-the-art account imply that the axioms of scientific theories are factual statements? If so, then scientific realism would be incompatible with descriptivism, and since descriptivism is highly intuitive, there would be quite a strong argument in favor of, for example, Ramsification or another alternative account of descriptivism. Second question, meant to be independent of scientific realism in its state-of-the-art account: is it a reasonable requirement, in a wide philosophical sense of being reasonable, of, let's say, non-metaphysical scientific realism, that the axioms of scientific theories are truth conditions such that their truth values depend on the truth of their atomic components, such that this problem of the factualist reading does arise? These are open problems left for future research and possibly the discussion. Many thanks for your attention.
As you all know, the topic of induction is a classic one, obviously, in philosophy of science and even traditional epistemology. And in recent years, in the Bayesian variant of it, it's become very, very prominent again in general philosophy of science. Accordingly, the topic of theoretical terms is a central one, obviously, in general philosophy of science. And recently, in the debates on structural realism and with the renewed interest in the history of logical positivism, the topic of theoretical terms became very prominent again. But strangely, there's not a lot of discussion of the two of them together, jointly. And actually, also for me, it's my first talk ever in which I talk about both of them within one presentation. So your feedback will be especially inductively relevant for me. And it's even stranger that there's not a lot of discussion of both of them jointly. If you go back a couple of decades, then you'll see there was a lot of joint discussion of the two topics back then, in the late 1950s and in the 1960s and 1970s. And part of what I want to do in my talk is to go back to these old debates and revive them a little, advertise them, and solve some problems, if possible at all. And the whole talk is, in a sense, some kind of advertisement of doing more of that. For example, what would be the right Bayesian treatment of theoretical terms? I think that's an obvious question to ask, right? It's a very relevant question to ask. And there should be a lot of work, interesting work, to be done about that. So that's the background. Now you can also see the subtitle here, 2 Carnapian remarks. So what I want to discuss in particular is, let's take Carnap's mature account of theoretical terms, and let's see how it does with inductive systematization. What I want to show is that what Hempel has to say in the theoretician's dilemma, that is that theoretical terms are indispensable in science, partly because they allow us to inductively systematize data. That if you take that, what Hempel is saying here, that this is perfectly consistent with the Carnapian treatment of theoretical terms. That will be my first thesis, the first claim that I want to argue for. So if you take Carnap's view of theoretical terms seriously, then yes, what Hempel has to say is exactly right. Theoretical terms are really, really important for inductive systematization. And that just, in a sense, drops out of the Carnapian picture. And secondly, that's my second thesis that I want to argue for in the talk. If you take Carnap's treatment of theoretical terms seriously, there's something else that you get in addition, namely, you can take logical uniform probabilities, and still you will be able to inductively learn on the basis of them. And that's something that I think even Carnap would find surprising, because Carnap actually argued against logical uniform probabilities. We can't use them, would be nice, but we can't inductively learn on their basis. But it seems to me if you combine Carnap's view of theoretical terms with some natural assumptions concerning uniform probabilities, you get uniform probabilities on the basis of which you can learn inductively. And that would be my second thesis. Right, and the plan is I'll first tell you about theoretical terms a la Carnap and inductively systematizing data. At first glance, you would think since Carnap's account of theoretical terms involves Ramsification, there should be a problem here for Carnap, because there are well-known arguments from back then, right, that Ramsification can destroy inductive systematizations. So you might think Carnap will have a problem here. But as I will show in that part, that's not true. Carnap's account is fine. And then in the second part, I'll deal with this new thought that maybe Carnap himself dismissed uniform probabilities as logical probabilities too quickly. If he had combined uniform probabilities with his own account of theoretical terms, he would have hit upon a nice and simple account of logical probabilities that still allow for inductive learning. And then I'll draw some conclusions from that. There's a lot that I will simply take for granted, just for the sake of the argument. Right? So there may be lots of problems over and above induction with Carnap's account of theoretical terms. Okay? So I'm not actually arguing that this is the right account of theoretical terms. I'm just saying he doesn't have a problem with induction. That's the only thing I'm saying. Right? He might have lots of other problems. But I'm just ignoring that here. Accordingly, as far as logical probabilities are concerned, there are lots of arguments why the notion of a logical probability is problematic, deeply problematic. Right? I just leave that open. I just put it to one side. I only want to show that from Carnap's account of theoretical terms, you get uniform probabilities that don't have the problem that you can't learn on their basis. They might have other problems. And in all of that, I take for granted this distinction between observational and theoretical terms. And again, we know, there's lots of problems about that distinction, right? That demarcation. But I'll just put it to one side. Okay, so just give me all of that, and then we'll see what we can say about theoretical terms and induction. All right. So I have here a quote from Hempel in the Theoretician's Dilemma. And there he says that as far as suitability for inductive systematization, along with economy and heuristic fertility, are considered essential characteristics of a scientific theory, theoretical terms cannot be replaced without serious loss by formulations in terms of observables only. Right? So that's one of the main messages of this famous essay. Why do we need theoretical terms? Well, partly for their inductive power, because they help us to inductively systematize our observations. Now, what is this inductive systematization that he's talking about here? At the beginning of his article, he points out that obviously there are many instances of scientific explanation and prediction, which are deductive in nature, right? Think of the deductive nomological account of explanation, right? But then again, there are also many of them which do not fall into a strictly deductive pattern. Then he gives a little example in the paper and says this kind of argument is inductive rather than strictly deductive in character. It calls for the acceptance of E, right, some statement, on the basis of other statements which only constitute partial, if strongly supported grounds for it. An argument of this kind will be called an inductive systematization. And the procedure of establishing an argument of the kind just described will also be called inductive systematization. Okay? So sometimes we put forward arguments, they might involve laws, right, or other general statements, and some side conditions, which might be observation statements. And from these, sometimes we can deductively, right, conclude another observation statements. But sometimes we just can't do that. What we can do is instead give something like inductively strong arguments rather than deductively valid arguments, right? And in these cases, we'll have some premises. They might be general again, laws or other general postulates. And we might have some initial conditions again, right, some observation statements. And they, in some sense, inductively rather than deductively support another observation statement, right? Both of these cases are covered by the term systematization, but the first class is called deductive systematization and the other class is called inductive systematization. And much of what Hempel is talking about in the theoretician's dilemma is about these inductive systematizations. All of the cases of scientific systematization that we've covered share this characteristic. They make use of general laws or general principles. These general laws have the function of establishing systematic connections among empirical facts in such a way that with their help, some empirical occurrences may be inferred from other such occurrences. And the inference may be either deductive or inductive. Okay? Now, when he then runs through a couple of examples, he concludes, well, obviously, you see from the examples that inductive systematization is very important for science. And since this is so, we get from this an argument against the usual anti-realist, let's call it like that for the moment, anti-realist reconstructions of scientific theories. And again, he looks at an example, so he considers a theory T prime, and the theory that he considers has no consequences in terms of the observational sublanguage, except for purely logical truths. In other words, T prime effects no deductive systematization among the observation sentences at all. That's just because he picked an example like that, right? So in deductive terms, that would be sort of an empirically vacuous theory, right? It's empty. Deductively, but not inductively, that's his point. Nevertheless, T prime may play an essential role in establishing, among the observation sentences, certain explanatory or predictive or post-dictive and so on connections of an inductive kind. And if the systematizing use of T prime is conceived as involving inductive as well as deductive procedures, then the corresponding anti-realist reconstruction of it cannot in general replace T prime because, and that's the point that he wants to make in the paper, these anti-realist reconstructions mess with the inductive structure. Okay, so you first have T prime. It doesn't give you anything interesting deductively, but it gives you something interesting inductively. Then you replace T prime by something else. The thing that he looks at here in this quote is the Craig re-axiomatization of the empirical content of that theory, right? And then he shows that this Craig re-axiomatization doesn't support the same inductive systematization that the original theory did, right? So in the transition from the theory to its Craig re-axiomatization, you destroy inductive systematizations. And hence, you shouldn't replace the theory by the Craig variant of it, okay? He doesn't, in this passage, say anything about Ramsification. He gives other arguments against Ramsification in the paper. But still, this kind of argument was picked up a little bit later by other authors in the 60s and 70s and extended also to the Ramsification of scientific theories. So what some of these authors argue is that choose a theory, a scientific theory, like Hempel's T prime here, replace it by its Ramsification, and you're going to see that you mess again with the inductive structure. You may, if you're unlucky, destroy inductive systematizations by the transition from T prime to its Ramsification, just as it's the case here with the Craig system. And maybe the most discussed examples of this kind you find in some papers by Israel Scheffler. For example, this 68 paper in the Journal of Philosophy. But at the time, back then, there was a real industry of such papers. They were looking, some were defending Ramsification against these attacks. Others were improving the arguments against Ramsification of this kind, and so on. If you're interested in that, the best surveys that I know, you'll find in a very nice paper by Nii Luoto in Synthèse. It's a really very good paper. A review by Tu Mela in the Journal of Symbolic Logic. And most recently, Panu Ratikainen published sort of a new paper on that topic in Synthèse, which is more or less a paper of the sort, well, we've all forgotten about this great discussion and we should go back to it. Okay, so it sort of advertises this whole area rather than developing lots of new thoughts in the paper. Okay, and here is one of Scheffler's examples. So this is supposed to be an example that shows that when you Ramsify, you may destroy inductive systematization. And of course, what Scheffler does is he picks a toy theory, right? So this is the toy theory here. Just has one statement with a theoretical predicate in it and say two observation predicates, O1 and O2. And the theory just says everything that has the theoretical property T has the observational property O1. And if it's T, then it also has the observational property O2. Okay? So if it's T, then it's both O1 and O2. That's the theory. And then Scheffler Ramsifies that theory. I've heard there is a bingo going on, the Ramsey bingo. So it's very important to mention Ramsey sentences in the talk. I think I'm fine. There's lots of Ramsey sentences, as you're going to see. And here's the first one. So you Ramsify away in the usual style the T, and then you get the corresponding Ramsey sentence here. So there is a capital X such that everything that is X is O1 and O2. And as you can see easily in second order logic, this is a logical truth, right? So think of the standard interpretation of second order logic. This really means there is a set of individuals, right, which is a subset of the O1 set and also a subset of the O2 set. So it's a subset of their intersection, right? Well, take the intersection of that. That's a subset, right? Or take the empty set. That's a subset, right? So there will always be such a set X such that the rest of the Ramsey sentence is satisfied. So this is a logical truth. So by Ramsifying, we turn from a theory, TH, that is not a logical truth to a logical truth. Then Scheffler considers another theory, TH prime, which is very similar to TH. The only difference is where TH says if something is T, then it is O2. TH prime says if it's T, then it's not O2. Okay? But it's still O1 in both cases. And he also Ramsifies that theory. And again, you get a logical truth out of that. Okay? So by Ramsifying the two theories, which are different statements that are not logically equivalent to each other, you end up with two logical truths, and logical truths are, of course, logically equivalent to each other. Okay? So obviously, you lose some information. Well, fine. That's not a problem in itself. Then he turns to inductive systematization. Scheffler argues, first of all, that the original theory TH achieves inductive systematization between a statement of this form, an observation statement, A has property O1, and another statement saying that A also has property O2. Okay? He argues for that. And the idea is very roughly the following, right? Let's assume you get that as evidence. A has property O1. Then given the theory, this should make it more likely, roughly speaking, that A has the property T. Okay? And again, given the theory, this in turn, by the second conjunct here, should make it, say, more likely that A has property O2. Okay? And hence you get inductive systematization in some sense between these two statements given the theory. Okay? Now, as you can imagine, this is a step that has been questioned, right? Especially because Scheffler puts this forward as a sort of two-step process, right? In the one step, you move sort of against the material conditional, and the other step, you move along the material conditional. And that's fishy, right? If you think of the old Hempel argument, right? If you're not careful enough with assumptions on your confirmation relation, then very easily every sentence confirms every other sentence, right? So that's not a good way of arguing. However, it was shown later by Niiluoto that this problem of Scheffer's argumentation can be avoided, okay? Because you can show that you get this inductive systematization going in one fell swoop, in one step, okay, by plausible principles. So although the original argument by Scheffler is no good, you can turn it into a good argument, okay? And if you want to know more about that, let's have a look at Niiluoto's paper, which, as I said, is very good. So I'll just take that for granted, okay? Other people have questioned that step, okay, in order to defend Ramsification. I just take for granted, well, there can be a problem here, okay? I think they're right. There is a problem here, as you'll see. Okay. Now, similarly, same pattern, TH prime achieves systematic inductive systematization between A has property O1 and A doesn't have property O2 for the same reason as before, okay? And again, the original argument is no good, but it can be turned into a good argument, okay? And now you drive home the point. Let's assume Ramsification does always preserve inductive systematization. Then this Ramsey sentence should inherit the inductive systematization properties of TH, and this Ramsey sentence should inherit the inductive systematization properties of TH prime. And two of them are logically equivalent, okay? And if they are logically equivalent, then at least for all probabilistic considerations, they are indistinguishable. They have the same probabilistic properties, right? So this means ultimately either of them should have both inductive systematization properties. Either of them says the Ramsey sentence of TH should achieve inductive systematization between A has property O1 and A has property O2, but also between A has property O1 and A doesn't have property O2. Okay? And that can't be. That's absurd, right? It can't be that this piece of evidence here makes this more likely and this more likely at the same time, right? Or makes this very likely and this very likely at the same time, okay? So something has gone wrong here, right? And the conclusion is supposed to be Ramsification does not always preserve inductive systematization, okay? So that's the argument, okay? And that means you shouldn't replace theories by their Ramsifications. Now, if you look at Hempel's original paper, it's not so clear what inductive really refers to, right? So, for example, it might refer to absolute confirmation, right? So that you get a probability that's greater than 1/2 or greater than a threshold or something like that, right? Or it could refer to incremental confirmation. Something gets more likely given the evidence than it was before, right? But you can show that in whatever way you understand the term inductive here, you get the problem from the previous slide, okay? And again, this was shown by Niiluoto. So it doesn't really matter that much. And I'll sort of gloss over that in my examples later too. All right, so here's the worry for the Canepian account of theoretical terms. Carnap's mature account of theoretical terms involves Ramsification. Ramsification can destroy inductive systematization, hence there is a problem. Or so you might think. And now let me defend Carnap against this attack. And in order to do so, let me briefly remind you of Carnap's account of theoretical terms, but I can be quick at a conference like this. So say you have a theory and theoretical terms. That's the Ramsey sentence of the theory. But then additionally, you get what is now in the literature usually called the Carnap sentence, right, over and above the Ramsey sentence. And the Carnap sentence is nothing but a material conditional, the antecedent of which is the Ramsey sentence of the theory, and the consequent of which is the theory itself, right? So if Ramsey sentence, then theory. That's the Carnap sentence. And the idea that Carnap had, first sketched, as far as I know, in his reply to Hempel in the Schilp volume, but then worked out systematically in his philosophical foundations of physics. Carnap's idea was that the full content of the theory can in this way split up in two parts, one of which captures the empirical content of the theory. That's, of course, the Ramsey sentence, which has the same, from which you can derive the same observational conclusions as from the original theory. And the analytic part, and that's the Carnap sentence. Okay? And this is backed up in different ways by Carnap. Most importantly, you can't derive any observation sentences from the Carnap sentence, unless they are logically true. And if you put the two of them together, you get back up to logical equivalence the original theory. Okay? Now, what you don't get in this way, if the theory is axiomatized in some way, so you have, say, 10 axioms, then you can't nicely put 3 axioms into the empirical content basket and the other 7 axioms in the analytic component basket. That you can't do, right? But still, you get pretty much what Carnap wanted to have. So that's Carnap's account. It's not just Ramsification, there's also what we now call the Carnap sentence. And that's going to be the crucial point. Now, there is this other version, you've already heard about that, this other version of Carnap's account of theoretical terms at the time, where he spells out theoretical terms in terms of epsilon terms, Hilbert's epsilon terms. You find that in a paper that was unpublished back then and then edited by Stathis later on. You also find that in a paper that came out in a volume edited by Bar-Hillel in 1966. And there the idea is you explicitly define theoretical terms in terms of epsilon terms, or if you like, you just replace from the start the theoretical terms by epsilon terms. And then, in a sense, you still have something like the Carnap sentence, but here you would have the corresponding epsilon terms. And you don't need to assume the Carnap sentence anymore because it becomes a logical truth of the epsilon calculus. Okay. But it's still pretty much the same account, but spelled out with an additional logical symbol, namely Hilbert's epsilon symbol, right? Which is semantically something like a choice function. Okay. I'm not using that way of presenting this matter here, but it's pretty much the same account, presented in different ways. Okay. Now, let's see what happens if we combine induction with this account of Carnap's of theoretical terms. So for that purpose, we first need a probability measure, right? That's going to be the measure by which we will measure inductive systematization, right? Now, in Carnap's theories back then, this measure would preferably be a logical probability measure. In today's world of probability, it won't be a logical probability measure, but it will be something presumably like a personal, subjective degree of belief function, right? Bayesian probability measure. It doesn't really matter for what I'm going to say. So pick a probability measure, and now make the following assumption, which given Carnap's account of theoretical terms is perfectly natural. Okay, you can't do otherwise, right? If Carnap had combined probabilities with this account of theoretical terms, he would definitely have assumed that the analytic statements, in particular the Carnap sentence of a theory, should receive probability 1 by the probability measure, right? In fact, he explicitly does so in his late work on probabilities, on induction, right? So by late work, I mean this work that was then really edited by Richard Jeffrey, right? And came out after Carnap's death. There he has his so-called A postulates. These are the analytic postulates, and they are assumed to have probability 1, right? In our case, in the case of theoretical terms, the A postulate is the Carnap sentence, so it should have probability 1. So this is obvious for Carnap if you take a logical probability measure. And even if you think of it in Bayesian terms, right? If you have sort of the scientist as the Bayesian agent, then since the analytic statements are supposed to be conceptual truths, right? The agent should be certain of them, or at least should, if you like, assign a very high probability to them. And if you do the latter, then what I'm now going to say will hold at least approximately. Okay? So either way, you should be fine. Either they have probability 1 or a high probability. So the situation really should be this. We have our logical space of possibilities, if you like, possible worlds, or models of the language of the theory that we're interested in. we have the theory, TH, right? So that's a set of models here. I present things now in this model theoretic way. It doesn't really matter that much. You could also spell it out in terms of probabilities of sentences if you like. Then you look at empirical submodels of these models. That's where the grid comes from. So the idea is if you look at one cell in this grid, then all of the models of our language have the same empirical submodel. They assign the same extensions to the observation terms. Okay? So within a square, you don't find any differences as far as observation terms are concerned. But you might find differences as far as the extension of theoretical terms is concerned. Okay? And now, what happens if you Ramsify is really, in terms of a picture, that you get something like a digitization of the original theory, like a coarse graining of the original theory. That's Ramsification, really. So if the original theory, that's the red thing here, right, touches one of these cells, one of these little squares, right, this means that there is a model in this little square that satisfies the theory, right? So this model is such that it assigns some extensions to the theoretical terms and some extensions to the observation terms, so that overall the theory, TH, is satisfied. So all of these models make true the Ramsey sentence of the theory, right? There is something that you can assign to the theoretical terms, such that given the assignment of the observation terms that you find in this square, the theory comes out true. Okay? But if one model in such a square satisfies the Ramsey sentence of the theory, all the models in such a square satisfy the Ramsey sentence of the theory, right? Because they all have the same empirical submodel, right? For all of them, it's true that there is something that you can assign as an extension of the theoretical terms, such that, and so on, comes out as true. So this means if this red line touches just one model in such a square, the whole square will be true, will satisfy the Ramsey sentence. That's why the Ramsey sentence becomes something, in terms of a picture, like a digitization of the original theory. Okay? That's the coarse graining picture that you should have in mind. And now, we have assumed that the Carnap sentence has probability 1 for a probability measure that sits on that logical space, right? So the probability measure assigns to propositions, sets of worlds or models, probabilities in this space. And it assigns to the proposition expressed by the Carnap sentence probability 1. Now this means the following. The Carnap sentence is if Ramsey sentence, then theory, right? That's a material implication. So equivalently, you could say it assigns to not Ramsey sentence or theory probability 1, right? If A, then B is as much as not A or B. Okay? So it assigns 1 to the negation of the Ramsey sentence, so that's the area outside here. And it assigns and the disjunction with the theory, and that's the red area in here, right? So the area outside here and the area inside here, right? That taken together gets probability 1. So this means that the remaining part, that's the part sort of in between the Ramsey sentence and the theory, that overall gets probability 0. It's a 0 set, as probability theorists would say. Right? So that really means that once the Carnap sentence has probability 1, the difference between the theory and the Ramsey sentence is just a 0 set. You can forget about it in probabilistic terms. From the viewpoint of the probability measure, it's as if the proposition expressed by the Ramsey sentence and the proposition expressed by the theory, that's the same proposition. It's not really the same, but in terms of probabilities, it's as good as being the same proposition. Okay? Accordingly, you can derive easily by the axioms of probability that once the Carnap sentence receives probability 1, the probability of the theory must be identical to the probability of the Ramsey sentence. Right? Their difference is just a 0 set. You can forget about that. And even more importantly, for example, the probability of B given a conjunction of theory and some statement A is identical to the probability of B given the Ramsey sentence of the theory joined with A. Right? In other words, the theory and the Ramsey sentence, they have the same probabilistic inductive properties. Right? You can always substitute the one for the other. But that means whenever a theory TH achieves systematic inductive systematization, right, also the Ramsey sentence will have this property. Right? If TH given some evidence, right, observational evidence, makes B more likely, then the same will be true for the Ramsey sentence joined with that observation sentence, right? If the theory makes B likely, right, probability greater than 1/2, the same will be true for the Ramsey sentence, and so on. So that means, given Carnap's account of theoretical terms, the Ramsey sentence achieves inductive systematization if and only if the theory does so. And hence, Carnap doesn't run into this problem. Okay? Carnap's account of theoretical terms is not threatened by the arguments that we've spelled out before. And the reason is that the Carnapian analytic part of a theory is taken for granted probabilistically. So actually, in Carnap's account, it turns out to be crucial not to eliminate the theoretical terms, but to keep them and to introduce them by the Carnap sentence, right? So this is not just sort of, an additional nicety for people who like realist languages, right? It's an important move here, actually, if you think of inductive systematization. So that's my first point. By the way, if you don't know what to work on, right, here's an interesting question, right? So we all have good accounts of empirical contents of theories, right? Say the set of observation statements entailed by the set of empirical submodels of models of the theory. You identify the empirical content with the Ramsey sentence. There are different versions of that. But they're all really deductive versions of empirical content in one way or the other, right? But once you take for granted that you have a probability measure around and that theories allow for inductive systematization, a natural question to ask is, what would be empirical content in this richer world of deduction and induction? And I don't think people have worked on that topic a lot. Now you can see that for Carnap, he can still identify, in a sense, the empirical content with the Ramsey sentence, right? Because of the move that I've just made. But in general, I think it's an open question. What's the probabilistic empirical content? I think it's an interesting thing to think about. Okay, now the measure P that I've used. I've told you the Bayesian story that could be a degree of belief function, right? But for Carnap, of course, it would have been a logical probability measure. And he has this elaborate theory of logical probability. Now, actually, the second point that I want to make is, if you take Carnap's account of theoretical terms seriously, you can actually use as your P here a probability measure that is both uniform and logical. And you won't run into the problems that led Carnap to think, well, I can't use these uniform probabilities. They don't give me what I want. Okay. So actually, I'm now more Carnapian than Carnap was, okay, in the second part. So this is Carnap, logical foundations of probability. And what he says here is, well, prior to experience, there seems to be no reason to regard one state description or possible world, right, model, as less probable than another. Accordingly, it might seem natural to assign equal probability values to different worlds or their singleton sets. Okay? So initially, you would think, well, at the beginning of all times, as it were, right, there should be a uniform, a flat probability measure. And that's what you get here. And then you define confirmation, Carnap's binary confirmation function, in terms of that probability measure. However, right, in spite of its apparent plausibility, this function, the confirmation function that you get in this way, can easily be seen to be entirely inadequate as a concept of degree of confirmation. And the reason is, you can't learn inductively if you presuppose a confirmation measure that is uniform in this sense. Okay? And Carnap gives a little example here. So let E be the conjunction of these, say, if you like, observation statements, but it doesn't really matter here. Okay? That's a long conjunction saying A1 has property P and A2 has property P and so on up to A100. And say the number of individuals that we're dealing with currently is 101. Right? So there's one remaining. Right? And the question is, how likely is it, given that this is the case, that individual number 101 also has property P? Right? And you would think, well, all of the others have property P. Now it becomes very likely that A101 also has property P. Okay? That's at least a natural thought. Right? That would be something that sort of straightforward inductive reasoning would seem to give you. But if you use the confirmation measure that you get from uniform probabilities, that's not what you get, for obvious reasons, right? And Carnap makes this argument himself. So H is this statement here, E is the other conjunction. If you join them in conjunction, you get a state description, right? If there are only 101 individuals, all the information that there is, if you just look at one predicate, is given, right? So the corresponding statement, E and H, will have the probability 1 divided by the number of all worlds or state descriptions, right? And then E, that is this conjunction here, really holds overall in 2 state descriptions, right? In one, additionally this holds, in the other one its negation holds, right? So the probability of E will be 2 divided by the number of all state descriptions, right? And if you divide that number by that number, you get 1/2, right? So the probability, given that piece of evidence, that A101 has property P is 1/2. You haven't learned anything. Doesn't really matter that you've seen all these occurrences of objects that have property P. And this would obviously be in striking contradiction to the basic principle of all inductive reasoning, but what Carnap wants to do is, of course, inductive reasoning, so this apparently plausible logical probability measure is out. And then he moves on to assign, as you know, probabilities not to state descriptions, but to so-called structure descriptions, right? And later on, he generalized it to the full continuum of inductive methods, right? And you get this elaborate theory of logical probability. And now I want to argue maybe he was too quick in that move, right? Maybe if he had combined his account of theoretical terms with what he thinks about here, he would have stick to uniform probabilities, because as you will see, if you do things properly, they do allow for inductive learning. And here is how it goes. So along the way, of course, Carnap makes certain presuppositions. One is, and that's an important one, different individual constants designate different individuals, right? So if you have individual constants like this here, A sub I and A sub j with different indices, then they are going to denote, by fiat, different individuals. He just assumes that from the start, right? So an equality statement like that for different indices here will be a logical falsity, in a sense, for Carnap. And that's just, presupposed along the way. I will not make that presupposition, and you will see what's going to happen. So here's my setup, but otherwise it's very Carnapian. So I have this language, say it's a first order, but it can also be a second order language, doesn't matter. You have n individual constants, you have finitely many unary predicates. I also allow myself to have the equality symbol, okay? Then I have a domain with n objects, okay? So you can see I have just as many objects as I have in the individual constants, right? Like with Carnap, but I'm not assuming that A1 will necessarily denote D sub 1. So I leave that open, right? It might denote D sub 1, but it might denote D sub n or something else. And then, as my set of possible worlds, the state descriptions as it were, I consider all logically possible worlds given that language. That is all models that you can build, right? Given that domain and given that language. All right? Cardinalities I write like this, and when I say something like that, that's the power set of my set of worlds, right? The set of all sets of worlds. And then I introduce my uniform probabilities, right? As you would do. And it's apparently plausible, as Carnap said, right? So the probability of a set of worlds will just be the cardinality of that set divided by the cardinality of the set of all worlds. So this is a uniform probability measure that you get in this way. And it's logical, right? According to all sources. Okay? Well, it's based on a space of logically possible models. And it's as symmetric as can be, if you like. And then if you prefer probabilities for formulas or sentences, you get the probabilities for formulas by taking the probabilities of all the worlds that satisfy the formula, as usual. The usual move from models to sentences. So that's just a syntactic counterpart of my uniform and logical probability measure from above. And conditional probabilities you define in terms of ratios just as usual. So it's just the standard game that I'm playing here. And then you can, make some little combinatorial calculations. You can count the number of worlds that you have. And you can do the following. You can determine the probability of the last individual having property P sub I, given that all the previous individuals from 1 to n minus 1 have property P sub I. Well, you can calculate that. It's not important what the number is. But the important thing is the number that you get turns out to be greater then the probability of A sub n does not have property P sub I, given that all the others have property P. right? So this is the point where in the original Carnap account, you get 1/2 for this number and 1/2 for that number. But it's no longer like that for my uniform probabilities over a space of logically possible worlds. So inductive learning, strangely, is possible all of a sudden on the basis of a uniform and logical probability measure, right? So what on earth is going on, right? That's what the 3 question marks represent. Okay, so let me give you an example, and then this will become clearer. So very simple, 2 individuals, okay, 1 predicate, right? Let's assume that A1 has property P1, okay? So we now look at only the models in our little language now with 2 individual constants, right? A domain of 2 objects and 1 predicate, where P1 of A1 is satisfied, right? Because we are only interested in conditional probabilities, conditional on that being the case. So we only look at those models, that's the reason. And then you find these models here, right? So in one model, A1 denotes D1, A2 denotes D1, so they denote the same thing, right? And the interpretation of P1 of the predicate is this singleton set. So that's one model. A second model is you keep the references like this for the individual constants, but the extension of P sub 1 is D1 and D2. Right? There is no other choices because we assume here, we look at models in which A1 has property P1, so D1 must be a member of the extension of P1. Right? That's why we only have 2 sets left here. The singleton set D2 would not work because D1 is not included in there. And the empty set wouldn't work either. Right? Or A1 denotes D1 and A2 denotes D2, and you work through the possible extensions of P1, and so on and so on. Okay? So you get 1, 2, 3, 4, 5, 6, 7, 8 models. And then you check in which of these models is it the case that A2, the other individual, has the same property P1. And you find out in 6 of them, this is so, and only in 2 of them, the negation holds, right? So the probability that A2 has the same property is 6/8, which is greater than 2/8, right? So you get inductive learning. And the reason is really, have a look here, in those models where A1 and A2 denote the same object, then since this object has property P1, right, you also get that sentence satisfied, right? If 2 individual constants denote the same object, and this object has a property, right, then you get A1 has the property and A2 has the property. There's no other way of doing it, right? And then there are the models where they denote different individuals, and then you get a 1/2 situation. But overall, if you calculate all of that together, you got a bias towards P1 applies to A2. So you get inductive learning from uniform probabilities. All right. You might ask, where's the theoretical terms gone? They'll enter the picture very soon. So really, what happens here is Carnap didn't realize this because he rigidified the reference of constants, right? As a side remark. It wasn't really important for him, but it actually turns out to be quite important. If he hadn't done so, then what happens is that the referential apparatus itself makes uniform probabilities inductively relevant. It's sort of as if induction is built into our referential apparatus. Here's an alternative way of seeing what's going on. If you spell things out in terms of identity. So I think that's hopefully illuminating. So again, we assume A1 has property P1. And now there are really just 2 possible cases concerning A2. Either A2 is identical to A1, right, which is the case in some of these models. Then by the laws of identity, if A1 has property P1, also A2 must have property P1. Or they are distinct, and then we can't say anything, right? It might be either way. And since we have a uniform probability, the probabilities are 1/2 in each case. And overall, given A1 has property P1, that is more likely than this one. So if you think of it in that way, it's something about identity that plays the crucial role here. Okay? And of course, identity, the identity predicate, is not definable in terms of these predicates P1 to Pk. Sometimes it's done, it's purported to be definable, right? You find that sometimes. But it's not really the case, right? If you know the extensions of these guys, you don't know about identity, okay? And this invites the following thought. Well, maybe what's going on here is that the identity predicate really is something like a theoretical predicate. And P1 to pk could be something like observation predicates. And then, if theoretical terms are not definable, say, by observation terms, maybe you always get an effect like that from the uniform probabilities, you get inductive learning. And I think something like this is the case. So this is a slightly improved example where we move closer to our topic, theoretical terms. So it's the same setting, but now let's say these predicates P become observation predicates. And the theoretical predicate that I use now is not identity, but is something like this here. Say it's the predicate is of the same kind as. Okay? I'm not saying really what that is. I'm not telling you about natural kinds. It doesn't matter much. What I presuppose is that the models are models that satisfy this postulate, which I'm going to call an analytic postulate. And it's the counterpart for this predicate of the law of identity that we had on the previous slide. It says if x and y are of the same kind, let's assume that, then if one of them has an observational property O1, then the other one has so too, and so for all the observational properties. So the idea is, on a deep level, x and y are of the same kind, and this shows up on the surface level in terms of observational properties. You can't define being of the same kind in terms of the observational properties, because sometimes accidentally, things that are not of the same kind might still have the same observational properties, right? You can only say one direction. If of the same kind, then say on the surface level they look the same way. And I assume this is an analytic postulate. Okay, and one way of arguing for that would be, well, you know, do the Carnap thing. Ramsify it, actually turns out to be a logical truth, right? So the rest is the Carnap sentence, and the Carnap sentence in this case is then logically equivalent to the sentence itself. And the Carnap sentence is analytic, so this sentence is analytic. Okay, it's just the usual Carnap move tells you if this was the theory, then actually this would be an analytic statement. Okay, the Ramsey sentence is just logically true. There is no empirical content to it. And actually, in order to make this work, as you'll see on the next slide, I don't even need to assume anymore, you know, that A1 can denote D1 or D2 or D3. I can just make the Carnap assumption again, if I like. So I'm presuming here that A sub I really denotes D sub I, just for the fun of it, just because it's simple. Okay? It's no longer important that I can play around with the references of individual constants. I get the same effect because you can run roughly the same argument, right? Assume that A1 has property O1, then there are two cases concerning A2. Either it's of the same kind as A1 or it's not of the same kind. If it's of the same kind, then by the analytic postulate, the two of them share all the observational properties. And since A1 has property O1, A2 must have the same property. Or they are not of the same kind, then you can't say anything. And by our flat uniform probabilities, this means the one case is just as likely as the other case. And overall, if you sum up again, given A1 has property O1, A2 has property O1 is more likely than A2 has the negative property. Okay. So as you can see, here I'm spelling things out in terms of absolute confirmation, really. But actually, you can make the same point in terms of incremental confirmation. It works just the same way. It doesn't really matter. And the probability measure that I have here, I would call it still quasi-logical, if you like. Right? You know, for Carnap, it never was a very big deal to distinguish logical truths from analytic truths. It doesn't matter that much. Okay? The analytic statements are something like quasi-logical laws. Okay? So given that thought, you end up, well, not with a logical probability measure, but with a quasi-logical probability measure. And it's still uniform and so on. And more generally, and now we are back to the full picture, let's assume we have our observation predicates and say one theoretical predicate, or many of them, you know. And everything stays the same, and we have a theory that's given, say, in the first order fragment of our language, which is now supposed to be a second order language, say. And the models are all the models of our language as long as they satisfy the Carnap sentence, right? Because all the analytic postulates should be satisfied in all the models. Okay. And then we define a probability measure as before. It's determined uniquely, it's uniform, it's quasi-logical again, because the Carnap sentence is analytic. And for the same reasons as before, we get, in general, inductive learning and systematization as being given by the theory. So what that really means, what kind of inductive inferences we get going, really depends on the theory, right? More precisely on its Carnap sentence, right? If the Carnap sentence is so-and-so, some models are excluded. If the Carnap sentence is different, other models might be excluded, right? And then other probabilities emerge. So the measure is uniform and logical, but also theory relative. Okay? But that's to be expected, because the Carnap sentence is theory relative too. And the same for inductive systematization, and that connects the second part to the first part, finally, right? So here's a little example. Let's take again the Scheffler case. That's the Scheffler theory again, right? If T then O1 and if T then O2. And now, we said before, take the Ramsey sentence. That's just a logical truth. There's no empirical content. So that means the residue, the Carnap sentence, is actually logically equivalent to the full theory. And the Carnap sentence is analytic. Okay? So the models that we look at here are all the models that satisfy the Carnap sentence, and that is, they satisfy TH. Okay? And the probability of the Carnap sentence, or TH if you like, is of course 1, because all the models satisfy this statement, so the probability of the set of all these models will be 1. Okay, so that's the setting again. And then here's a little example. So here you can see the possible truth values in principle for A has property T, A has property O1, A has property O2. Right? You run through all the 8 combinations of truth values. You can throw away some of the models, namely those that do not satisfy the Carnap sentence. They are out. Okay, so you can see 5 of them are remaining. Okay, then let's assume, okay, by supposition or because you learn it, the statement A1 has property O1. Sorry, I can just say A here. A has property O1. Okay, so that's just true in amongst these 5 in these 3 models here. These other 2 make the negation of O1 of A true, so you can forget about them. So you're left with 3 models to look at, and then, as it turns out, in 2 of them, A has property O2, and in 1, it has the corresponding negative property. So that means, given A has property O1, the statement that A has property O2 is more likely than its corresponding negation. So in a sense, given the theory, or its Carnap sentence in this case, right, you get inductive systematization, again, on the basis now of logical and uniform probabilities. So logical and uniform probabilities, if combined in the right way, with the Carnapian account of theoretical terms, allow for inductive learning. That was about the previous examples, but it also allows for inductive systematization. Okay? And if we had used TH prime, where we had a negation sign here, this inequality here would actually be the other way around. So we would still get inductive systematization, but in favor of not O2 of A rather than in favor of O2 of A. Right? Because with TH prime, we did have a negation sign here. So you can see where the theory relativity plays a role. The logical probabilities, the uniform logical probabilities, are determined by the theory. And if the theory says not O2, then you'll get a bias here in favor of not O2 rather than O2. Okay, so conclusions, and then I'm done. Here is what I've not shown, just to remind you. Okay, it's good to remind you before the questions and answers session. I did not show that Carnap's account of theoretical terms is right, or is a good one, or anything like that. Okay, so some people in this room, okay, might say, well, do we get the causal aspects of reference right? Okay, so Stathis would, right? And Stathis might be right about that or wrong. Let's say he's wrong, just for the fun. But it doesn't really matter, right? I've not said anything about that. Right? Well, probably he's right. Okay. Again, I presupposed observational versus theoretical. You know, I just took that as a given. I have nothing to say about that here in this talk, about that. I also didn't vindicate logical probabilities, right? I'm not saying these uniform logical probabilities that I've determined in this way, right? They solve all the problems of induction or anything like that. Okay? There are lots of problems left. These logical probabilities are language relative, and you know you get the usual problems with that assumption. Okay? What about infinity, right? What if you have infinitely many individuals around? What about then concerning the probabilities of, say, universally quantified statements, right? Another row problem of logical probabilities. Nothing to say about that here. Okay, so there are lots of problems left. What I did show, I think, is while standard Ramsification may in fact destroy inductive systematization, Ramsification within Carnap's account of theoretical terms doesn't have that problem. Okay, so it's free of that problem. That is the only thing that I'm arguing for. And the reason is Carnap doesn't eliminate theoretical terms, but introduces them through the Carnap sentence. And secondly, what I wanted to show was, if you combine this Carnapian view of theoretical terms with uniform probabilities, contra Carnap, right, in a sense, one ends up with a non-arbitrary, quasi-logical, and theory-relative probability measure, which still supports inductive learning and inductive systematization. Okay? So maybe Carnap wouldn't have been forced to move to this continuum of inductive methods. He could have just stick to the uniform probabilities if he had applied the same account of theoretical terms that he had sort of in his deductive moments, if he had applied the same thought in his inductive moments. Okay. So as Hampel said, the point of theoretical terms might well be their inductive power, and in fact that's precisely or pretty much what follows also from Carnap's account of theoretical terms. Thank you very much.
I will speak today about the relationship between causality and theoretical terms in physics, or to be still more precise, in theoretical physics. Not in general philosophy of science or in all kinds of sciences, but only in physics. Since the times of Aristotle until David Hume, the notion of cause and the concomitant principle of causality were considered to be essential for the task of investigating nature. There were certainly some controversies about the best way to explicate this notion, but the general consensus, not only among philosophers, but also among natural scientists, about working scientists, was that at least one fundamental task of science is to investigate what causes of things and events in nature are. A prominent example for this standard causalistic understanding of the task of science, and more particularly of physics, is the most prominent physicist of his time, Isaac Newton, who in his main work, Philosophiae Naturalis Principia Mathematica, of 1687, in the last book of this work, there is a kind of mini treatise of philosophy of science under the heading Regulae Philosophandi, which in the English translation runs as follows. Rule 1, we are to admit no more causes of natural things than such as are both true and sufficient to explain their appearances. Rule 2, therefore, to the same natural effects we must, as far as possible, assign the same causes. Well, this implies first that the natural scientist has to be parsimonious in looking for causes of phenomena, but on the other hand, he has to look for them anyway. So Newton had no problem at all in viewing the search for causes as an essential task of physics, and he went even so far as propose as a genuine task for physicists to investigate all kinds of causes on all levels, so to speak, until the level of the supreme being. There is a Latin version of the Principia Mathematica where there is a scholium generale. Interestingly enough, this was not translated or not retaken into the English version, but that's not our point. That's not my point now. Anyway, there Newton states the following. This is a kind of general conclusion of his work. Et ec dedeo de quo utique ex phenomenis disserere ad philosophiam experimentalem pertinet. Ex phenomenis prodeunt proxime rerum causae, ex is causae superioris donec ad causam summam perveniatur. Since I suppose that most of you are not so fluent in Latin, here is the English translation. I have done more or less freely. And the same goes for God, to treat of whom, starting from phenomena, also belongs to natural philosophy, that is what we now call physics. From the phenomena we proceed to the proximate causes of things, from these to superior causes, until we reach the supreme cause. Now, leaving aside the proposal of doing a kind of physics of God, that's not my point now, but what is interesting here is that Newton sees as an essential task of physics to proceed by levels of causal investigation until eventually we reach God. But this idea of levels of causal explanation or causal investigation in physics, I think is an important point, and I will try to recover it later on. Well, therefore, in Newton's time, well, perhaps not all physicists of his times would have agreed with him that physicists have to investigate God also as a supreme cause, but they certainly would have agreed with him that looking for causes in physics is a very important task. So this was a wide consensus until that troublemaker of David Hume came into the scene, and well, he showed to be a rather skeptic about causes, as you all know, though we cannot really say that Hume proposed to eliminate causal talk from science. He just proposed what we now would call deflationist analysis of causality. And here's a quote of his Treatise of Human Nature, 1739. We may define a cause to be an object precedent and contiguous to another, and where all the objects resembling the former are placed in like relations of precedency and contiguity to those objects that resemble the later. So what he proposes is not to eliminate causal talk, but to, as we would say today, to reduce it to a purely spatio-temporal contiguity, to, we might say, kinematics. Well, it is historically interesting to know that Hume's deflationist explication, of course, was not very influential in his times, and people continued to think that causal talk, the idea of causality, is important for science. We see this in many very prominent authors like Kant, for example, or later on in John Stuart Mill and many others. Things began to change in the second third of the 19th century, the last third of the 19th century, with the rise of positivism, which affected not only inner circles in philosophy, but also working scientists, especially physicists. And as we'll see later, there was a whole current against causalism, and which became quite influential in the end of the 19th century and the first 2/3 of the 20th century, with some important exceptions like Hans Reichenbach, but most physicists and philosophers of science of the time had no good opinion about the idea of cause. Things began to change, let's say, around the 1970s with authors that tried to restore the dignity of causality in philosophy of science, like Salmon, Mackey, Pearl, and we heard in the talk before Boyd. But what is interesting for me now is that this resurrection of causality in general philosophy of science is undisputable, but in philosophy of physics, and particularly in the philosophy of theoretical physics, there are still many authors that are decidedly anti-causalists, and quite notorious, quite prominent philosophers of physics. I mentioned here only 4, which have been working the last decades, like Erhard Scheibe here in Germany, or Bas van Frassen, Hartry Field, John Norton, and some others. All these people are anti-causalists in physics, at least in physics. Some of them would accept nolens volens, that causal talk has some justification in common sense, or as John Norton puts it, in folk physics or folk science, or perhaps in some special sciences like biology, medicine, and so on, but not in fundamental physics. There, causal talk makes no sense, or is no good thing, has to be superseded. Well, there is at least one linguistic point in favor of these anti-causalists. Namely, all of them underline that causal terms don't appear explicitly in the formulations of the basic laws in contemporary treatises of theoretical physics. So they would say, okay, you are talking of causality in physics, now take, I don't know, direct quantum mechanics or whatever treatise you want to take, and tell me where you find the notion of cause among the fundamental equations of quantum mechanics or electrodynamics or whatever. There is no, this term doesn't appear. So at least they have a linguistic point. That's undeniable. And this is a point that was already hinted at by the patriarch of anti-causalism in the philosophy of physics, namely the great Bertrand Russell, who in an essay of 1918 on the notion of cause states a very famous passage. I suppose many of you know it already, but I repeat it because it is so markedly formulated, as most things in Russell. He says there, all philosophers imagine that causation is one of the fundamental axioms of science. Yet oddly enough, in advanced sciences, the term cause never occurs. The law of causality, I believe, is a relic of bygone age, surviving like the monarchy only because it is erroneously supposed to do no harm. So this is a very famous passage against causality in physics. Now, and this, as I said, this is a kind of source of inspiration for present day, for contemporary anti-causalists in philosophy of physics. Now, the first question one might raise at this point is this linguistic fact, namely that the term cause doesn't appear in the fundamental laws of physics, is this a linguistic fact, a knockdown argument against causality? Well, I don't think so. I mean, okay, the fact is undeniable, but what does it imply? It's not clear what it implies. After all, in many contexts, we may not use a term, but rely on the notion, on the concept behind this term. You, for whatever reasons, you might never want to use the term love in your life, but you might be terribly in love with someone. So the fact that the term doesn't appear in a context doesn't imply that the corresponding concept doesn't play any role in that context. So perhaps we have to look for deeper reasons why many authors defended kind of anti-causalism in the philosophy of physics. And well, I think in those cases it's always useful to have a look at the historical background of a given current in philosophy. And if we look back to the last third of the 19th century, we find a very strong trend against causalism, not only in philosophers, as I said, but also in prominent physicists. Here is one example. Gustav Kirchhoff, in his Vorlesungen über Mechanik, 1876, a very influential textbook on mechanics of the time. In the introduction, he writes, "Mechanics is often defined as the science of forces, and forces as the causes that produce motions. Certainly, this definition has been very useful for the development of mechanics, but it is burdened with the obscurity inherent to the concept of cause. For this reason, I propose as a task proper to mechanics to describe those motions that actually occur in nature, and to describe them in the most complete and the simplest way possible. I mean by this that the only thing that should interest us is to find out which phenomena occur and not to determine their causes." It's a clear statement against causality in mechanics, which could be, of course, generalized to other branches of physics. And this is what, by the way, a contemporary of Kirchhoff did, a bit younger than Kirchhoff, Ernst Mach, very well-known physicist and philosopher of science, who is responsible for the most systematic attack on metaphysical and particular causal notions in physics. The nutshell of Mach's position in this respect is, when we free the laws of physics from any metaphysical burden, we merely find correlations between several parameters describing regularities in the phenomenal world. We don't find any causes or things like that. So anti-causalism was not like expressed, for example, by Bertrand Russell, was not a kind of funny phenomenon of some cranks, but was really rooted in the spirit of the times. By the way, Russell, in many of his writings on physics, expresses his great admiration for Mach. So this was in the zeitgeist of the times, both in the philosophy, both within philosophy and physics. The culmination of this anti-causalism we may find in Ludwig Wittgenstein's Tractatus of 1921 in paragraph 5.1361. We read in the characteristic lapidary style of Wittgenstein, "Der Glaube an den Kausalnexus ist der Aberglaube." That is, the belief in the causal nexus is the superstition underlined in the original. So one cannot be harsher to the idea of causality than this. And so apparently Wittgenstein thought that if I believe that I had a car accident because the road was suddenly frozen, this belief has the same epistemological status as believing that I had a car accident because a black cat was nearby. So, and since reasonable people would like to found their worldview on superstitions, it immediately follows that the notion of cause, like that of black cats and so on, have to be dismissed from science. Now, let's go a bit deeper into the reasons why people like Kirchhoff, Mach, Russell, and so many others wanted to eliminate causal discourse from physics. So it was not just this linguistic fact that we don't see the notion of, we wouldn't read the word cause in the fundamental equations of physics, but has a deeper root, namely all these people wanted to purify physics from metaphysics. And the term cause for them was a clear case of a metaphysical term. So what they proposed is to rewrite physics so that well-formulated physical theories should contain only concepts referring to what is directly observable, and causal notions are not, do not refer in this way unless we reinterpret causality in this rather trivial sense of Hume, namely as a purely kinematic relationship of a spatial-temporal contiguity. But if we mean something more important, then this is just metaphysics. This, of course, implied also for these authors that not only the notion of cause had to be dismissed from physics, but also many of its more or less explicit instances. We have already seen that Kirchhoff wanted to kick out of mechanics the notion of force. But of course the same applies to many other concepts which are, so to speak, instances of causal talk in physics textbooks. Terms force, mass, energy, entropy, electromagnetic field, atoms, molecules, and so on. They should be either expunged from the text or else, since these people were perhaps not so bad as to want all textbook writers to rewrite their textbooks, but they would say, okay, you can still use these terms if you wish, but only as a kind of, for didactic reasons, only as a shorthand notation for the only thing that makes sense, which are observational concepts. So you have, if you want to use these terms, you have to show that they are strictly definable in purely observational terms. And this means, in the context of physics, essentially in kinematical terms. Because certainly kinematics is aligned to causality. So we can say with hindsight that there was here kind of a program, a foundational program for physics, which might be described as a kinematization of physics. I am sorry for the neologism, but I hope it is clear enough. Well, again, a very prominent example for this was Mach himself, who not just made overall statements against metaphysics, but also wanted to go to concrete business in reformulating fundamental laws of physics. And already in an article of 1866 über die Definition der Masse, but also in a more systematic way in his main book on Philosophy of Science, Die Entwicklung der Mechanik, historisch-kritisch dargestellt, of 1883, he invents a very ingenious procedure to reduce the notion of mass to purely kinematic notions. I will not give the details here, but the essential idea is that mass has to appear just as a coefficient of the relative accelerations of two isolated bodies. And furthermore, of course, then the term force is just strictly nominally definable in terms of mass and acceleration. So the equation F equals m times a is just a nominal definition of F. So Newton's second law becomes degraded to a purely trivial nominal definition. This was already a very concrete program, not just general philosophy, but a very concrete program to erase causal ideas from causal talk from physics. This was followed by some other people who tried to consolidate and make Mach's program more precise. And I mention here some of his followers in the later times: Heinrich Hertz in the 1890s, Hans Hermes in the 1930s, Herbert Simon in the 1940s, and Günther Ludwig in the 1970s. All these people tried to show that in the last analysis, dynamical concepts, and generally all concepts in physics that are not that do not refer to directly observable relationships, and this means essentially kinematic relationships, can be defined, really defined, by these kinematic notions. And, well, of course, you know that the Vienna Circle at the beginning also thought in general that all theoretical, what we now call theoretical concepts, should be reducible to observational ones. You already know, of course, that this program was confronted with very serious difficulties around the times of around the end of the 1930s, with Carnap's investigations on dispositional concepts, and then confronted with more general arguments why the really more abstract theoretical notions of physics cannot be expected to be reducible by semantic equivalences to purely observational concepts. So what we had then, let's say around the 1950s, was the rising of what some people call the standard view in philosophy of science, especially in philosophy of physics, namely that the conceptual reduction program of the theoretical with respect to the observational is not feasible, and in particular because, what people said, theoretical concepts have a surplus meaning. This means they are essentially more flexible and multi-applicable than observational concepts. So, for example, the term mass is not really definable in terms of purely in terms of accelerations, because you can use this term in very different contexts that are not necessarily tied with any ratio of accelerations and so on. Well, this was, as I said, it became the standard idea about the distinction between observational and theoretical terms, and which led to what sometimes is called the two levels conception of empirical theories. There are two quite well distinguishable levels in science, and particularly in physics, namely the theoretical level and the observational level. None is reducible to the other one, and in particular the theoretical level is not reducible to the empirical level. And one of the reasons, according to this view, why this is so is that theoretical terms are used for the formulation of theories having an explanatory power, for theories that explain phenomena which a thing that or a name that can be realized only if we use theoretical concepts. Otherwise, if we were limited to the purely observational level, we would not, our theories would not have, would just consist of, say, kinematical regularities, and would not explain anything. So if you want to explain what happens in nature, you have to use theoretical concepts which are essentially non-reducible to observational concepts. So what the idea which came out of this, and which I essentially agree with, but I will modify it later on for reasons that I will explain. But essentially, I think that's an important result of philosophy of science. And in spite of the efforts of the Machian camp, which lasts until today, perhaps, among certain people, but essentially this is true that you cannot reduce theoretical concepts to, of all kinds in physics to purely kinematical relationships. As I said, I will somehow, later on I will modify this a bit, but essentially I think this is a good idea. But now this, what this idea is, has the following implications. Namely, explanatory talk, at least in physics. I am only speaking of physics here. Explanatory talk in physics is, not always but very often, intimately tied to causal talk. We explain something by indicating its cause. That's already so in folk physics. We explain the car accident by indicating a cause, namely the frozen road. But, at all levels, if we want to explain something, not always, but very often in physics, we indicate a cause for that something. But at the same time, explanatory talk is also tied in physics, not always, but very often, to the use of theoretical terms. We use theoretical terms to explain things. We use theoretical terms like force and mass in mechanics to explain why the orbits of the planets are the way they are. So what we have here, more or less implicitly, is a kind of, I call it meta-theorem, and of course in quotations marks, it has not to be taken seriously as a formal theorem, as a kind of plausibility argument. Namely, it has two premises. Premise one, explaining is intimately tied to indicating a cause, and somehow, in some way, explaining implies indicating causes. It's not a formal implication, of course, but it's a very strong conceptual relationship. Premise two, using theoretical terms is intimately tied or implies in some informal sense explaining. Therefore, conclusion, using theoretical terms is intimately tied to indicating causes of things. A further, most plausible conclusion, if you are a scientific realist, I will come to this point later on, is that theoretical terms refer to causes of observed phenomena. Not always, but very often. Now, I would say this is a kind of implication that comes out by a sort of plausibility argument from the classical two levels conception of the standard view in philosophy of science, particularly philosophy of physics. Well, we have now to be a bit more sophisticated here because the so-called two levels conception, as you all probably have heard, has many problems, and one problem is that it presupposes a universal, absolute distinction between theoretical and observational terms, independently of the theories where these terms appear. That means that, for example, the terms velocity or entropy would be by their own semantics, so to speak, either observational or theoretical, independently of any theory where they appear. Well, it's a kind of universal absolute distinction within the two levels, and as you probably know, almost nobody believes in this anymore, in this absolute distinction, at least officially, though many authors still, in many discussions, we perhaps have seen some examples today here, is that in many discussions one still somehow assumes it unofficially. Yeah, we know, well, that's not a really absolute distinction, but let's do like that as if there were theoretical concepts, observational concepts. And, they are, of course, tied together somehow, but they stand for themselves there. Well, I would like to underline that this, I don't think this absolute distinction between the theoretical and the observational level is tenable, at least not in the philosophy of physics. In a sense, any physical concept appearing in any physical textbooks, even the most elementary ones, are theoretical. I mean, in the sense that they make sense only in a given theoretical context. In a more metaphorical way, in the 60s, people like Kuhn and Hanson and Feyerabend spoke of the theory-ladenness of observation. Well, it's a kind of metaphor, but anyway, I would say if we consider theoretical terms, if we consider physical terms, they are, in a sense, all somehow tied with some particular theories, not just theoretical per se. Not just observational per se. So I think we should replace the absolute distinction between theoretical and observational, but by something else. That's what does the structuralist view of theories in the tradition of Snead and Steckmüller, to which I myself hold. And the proposal is that the absolute distinction between theoretical and observational should be replaced by a relative distinction between T theoretical and T non-theoretical with respect to a given theory, capital T. Here you have a kind of definition, or at least explication, of what it means for a term to be T theoretical. A term lowercase t appearing in theory, capital T, is T theoretical even only if all existing methods to determine, for example, in physics, this would mean essentially to measure lowercase t, presuppose the applicability of uppercase T. All existing methods to measure the term are presupposing the applicability of T. What this exactly means, I can define it formally in the discussion if wished, but I hope you have at least an intuitive understanding. It means, of course, that the fundamental laws of capital T are supposed to be applicable in the context of measuring or determining that term, lowercase t. Otherwise, lowercase t is T non-theoretical. Note that the fact that a term lowercase t is non-theoretical in T doesn't imply that it does not appear in T or in capital T. Of course, it might appear in the fundamental laws of capital T, and that's the usual situation. But usually it is accompanied with other terms that are T theoretical. Yeah. So we have within a theory capital T two levels: the T theoretical level of concepts which presuppose the laws of this theory when they are measured, and the T non-theoretical, which also constitute part of the conceptual frame of capital T, but are measured by methods that, or determined in general by methods that do not presuppose the laws of capital T. Now, a consequence of this relativization of the distinction between theoretical and non-theoretical is that a given term lowercase t may be T theoretical in theory capital T, and T prime non-theoretical in a theory T prime presupposing T. For example, it is plausible to assume that the concept of force is T-theoretical within Newtonian mechanics. But it appears also in, say, classical electrodynamics, and there it is T-non-theoretical because there are methods there of measuring forces which do not presuppose Maxwell's equations, but just presuppose Newton's equations. So we have this relativization. The term is not T-theoretical universally, but in a given theory, and it may be non-theoretical in another given theory. But if we accept, in principle, this, in quotation marks, this meta-theorem I just mentioned before, that theoretical concepts are intimately tied to causal talk, and in some way theoretical concepts refer to causes that explain things and events, then of course this has the consequence that the notion of cause itself becomes relative. That is, the term lowercase t may denote a cause in the explanatory context of capital T because there it is T-theoretical, but it doesn't denote a cause in the explanatory context of T prime because there it is T prime non-theoretical. Well, perhaps some people might feel uncomfortable with a relative notion, a relativized notion of causality. Well, what can I say to this? I can only say I don't see any place for absolute causes, at least not in the context of a physical discourse. It seems to me rather that we have to take this Newtonian intuition I quoted at the beginning, namely that we have different levels of causality and in physics. And that, well, on a given level, we have some notion as a cause for something, but the next level, it's not. We look for more general causes. This is already so in folk science. I mean, in a given context, you consider that you had the car accident, that the cause of your car accident was a frozen road. But then, of course, you might ask yourself, well, what was the cause of the frozen road? You come to a meteorological consideration, and this, in turn, can be explained by some still more abstract general theory and so on. So we have levels here of explanation and of causality. And I don't see any problem with that unless one has a very essentialist idea about causality. Okay. So now we are in a position within this somehow reformulated frame of the interrelationship between causality and theoretical concepts and explanation. Namely, a cause in a given theoretical context is a referent of a term that is theoretical in that context and is used to explain through some fundamental laws, that's important, presupposed by the application of that term, why the non-theoretical data in that context are the way they are. So that's my official definition of cause, and of course we can discuss it later on. I think this summarizes within the structuralist relativization of the theoretical and the non-theoretical this postulated interrelationship between causality, theoreticity, and explanation. Well, here a side remark. I am not saying that all theoretical terms denote causes, either relative or absolute. Some theoretical terms are certainly fictional terms, as already Javier de Donato has pointed out, giving some examples. Center of gravity, lines of force, and so on. So they would not fall under my definition. But what I claim is that the most central terms of fundamental laws denote relative causes. Examples: mass and force denote causes, relative causes in mechanics. Internal energy and entropy denote causes in phenomenological thermodynamics. Electromagnetic field denotes a cause in classical electrodynamics. Space-time in relativistic, special relativistic theory, curvature in generalized relativity, molecule in the kinetic theory of gases, photon and spin, and many others in quantum theories. A further side remark about the ontology of the reference of theoretical concepts. Well, there are two kinds of theoretical concepts in physics, namely magnitudes and class terms. Magnitudes, that is, metrical functions, they are relations between things and numbers. Real numbers, complex numbers, so on. Examples are force, entropy, electromagnetic field, and curvature. And there are class terms that are also theoretical or de-theoretical in a given theory, like molecule, electron, black hole, and so on. Now, one might ask, is there an essential difference here with respect to causality? I don't think so. Both kinds of terms, they are certainly logically different. The first kind are, in terms of logic, are n-adic predicates for n greater than 1, and the second class are, the second kind are monadic, logically speaking, monadic predicates. But I think both are legitimate candidates for denoting causes that explain the data. Only the way of speaking changes a bit. The intuition behind changes a bit, but it's essentially the same thing. For magnitudes, we might say that a change in the value of a theoretical magnitude causes a change in the data observed. Observed in quotation marks. I forgot the quotation marks. That for the first kind. For the second kind, we might say the presence or absence of the referent of a class term causes the occurrence of some data. For example, here we might say that the change in a mechanical context, the change in the value of the force function causes a change in the accelerations observed. Whereas here we might say, for example, that the presence of electrons in in a two-slit experiment causes the occurrence of some shadows on a screen and so on. But well, there is a slight difference of discourse, but I don't think this is an essential difference. Both kinds of terms in physics are legitimate candidates for expressing causes that explain the data that appear to be T non-theoretical in a given context that have already been assembled. Well, I will make a last point. Well, a possible general objection against my approach is, of course, anti-realism. Because I'm quite honest about this, my argument has two more or less implicit premises. The first premise is some form of moderate scientific realism that would say that most theoretical terms refer to real relations or to real sets of things assumed as causes of data. And the second premise is explanatorism, to use a neologism again, which would say most physical theories are intended to explain some data. Now, of course, typical anti-realists would just say horror here. We don't want to buy this ballet. The typical anti-realist, be it in the classical form of Pierre Duhem a century ago or of Bas van Frassen today, denies, of course, both premises of my argument. For them, theoretical terms don't refer to anything, or if they do, we'll never know what it is. And secondly, theories are not there to explain anything, but just to save the phenomena, as the ancient dictum runs. Now, what do I have to say against this? Well, I have nothing to say about this because time is running. And I'm not going to embark here in the controversy, realism versus anti-realism, just because this would not fit into the frame. And also because I know that, well, you all know that this controversy is very complex, has lasted for many decades by now, and there are many arguments for and against scientific realism. Issue is quite complex, and I don't want to express here a particular stance, though I confess publicly that I tend to sympathize, taking all things together, tend to sympathize with a moderate form of scientific realism. But that's not my point now. My point is just a conditional statement, namely, if some form of scientific realism is the appropriate epistemology for physics, then I think we must accept that most theoretical terms of physics are to be interpreted realistically as denoting causes, in the way I have tried to explicate before. So to conclude, let causality live and prosper in physics in the form of theoretical concepts. And if this is a form of monarchism, then so much the worse for republicanism. Thank you.
I am talking about how to apply Falta's abstract objects theory to the analysis of theoretical terms and to the analysis of what I call ideal terms. So the idea is very simple and clear. It's the following. You have, suppose at the linguistic level, the set of theoretical terms. What I call ideal terms are a subset of the theoretical terms. An example of theoretical term would be, for example, electron or mass in the sense of classical Newtonian mass. Ideal terms could be, for example, ideal gas, rigid body or perfectly rigid body, harmonic oscillator, and so on. And my proposal is very simple. The reference of all theoretical terms, and of course of ideal terms, are abstract objects. So this is the linguistic, the set of the linguistic part, the linguistic stage, and then you have a set of abstract objects. Oops, no problem. So the set of abstract objects as accounted in the theory of Falta includes many things. For example, abstract objects would be mathematical objects. The number 2, or for example, fictional entities like Sherlock Holmes would be an abstract object. And even impossible entities like the round square. But in my proposal, not in Falta's, because Falta has not applied his theory, at least still, to scientific, to the analysis of scientific terms, and in particular of theoretical terms. Well, he has an example in his book on abstract objects, 1983, where he presents his axiomatic theory on abstract objects. He has the example of simultaneity in the sense of the classical mechanics. And he presents this as an example of property which could be in his theory understood as an abstract object. Abstract objects in the sense of Falta include not only individuals, but also properties and relations. Yeah? So Sherlock Holmes would be an individual, which is an abstract object in his theory, like number 2. But for example, simultaneity would be a property, which in his theory is treated as an abstract object. So my proposal is to understand the reference of the theoretical terms like mass or electron, as well as the reference of ideal terms like ideal pendulum, for example, in the sense of abstract objects. So this set will include things like number 2, Sherlock Holmes, and the reference of electron, the reference of simple pendulum. So this is the idea, and I think there are many consequences, interesting consequences of this application. Well, I have too much slides, I think. I will skip many of them. I'm sorry for this, but the first part has to do with the problems of the realist accounts of reference. I will skip this because that would be too much. The idea here is that I am not convinced by all these realist accounts, but I am following the idea of Thomas Kuhn of constituted kind, which is typically an anti-realist account. But I think my own account is neutral with respect to the scientific realism problem. That could be controversial, but that could be discussed in the discussion time. So recall that Kuhn, in his last publications, develops a series of ontosemantic considerations with application to the expressions of science. And his last hope was to provide a theoretical framework that accounted for the phenomenon of incommensurability. In this context, Kuhn proposes that the reference of scientific terms is provided by kinds, but these kinds are not natural kinds, but constituted kinds, constituted by human action. And because they are constituted by human action, we may assume that these kinds are abstract entities. Well, a nominalist interpretation of Kuhn's constituted kinds as merely extensional entities is problematic because, I will skip this, because here is the main reason. If the references of scientific terms were extensions, and mere extensions, the reference of each scientific term could change with the development of a theory. But another interpretation of Kuhn's idea is possible, the one that is given by Alexander Bird in his book on Kuhn. On Bird's interpretation, we have to distinguish between the reference and the extension of scientific terms. So following this idea, we have, on the one hand, the reference of a scientific term, which is a constituted kind, and in our sense, an abstract object. An abstract object which is characterized by satisfying a certain condition, which is established, of course, according to the theory for which the term is theoretical. While the extension is the set of instances to which the term is applied. It's a different thing. So what is an abstract object is the reference of the scientific term, not the extension. In fact, yes, it is. But I will speak about this later. This is a little bit more complicated. By adopting this proposal, we find a new kind of problem, namely, while the extensional entities are entities that enjoy respectability, so to speak, thanks to set theory, it could be suggested that constituted kinds are strange entities lacking theoretical support. What the hell are abstract objects? What the hell are these constituted kinds? And here comes my proposal. My proposal is to use Thalta's axiomatic theory on abstract objects, which is the only axiomatic theory I know on abstract objects, And I know that you are familiar with this because Falta was here in Munich as he was also in Santiago giving an introductory course on his theory. So we propose to use Falta's theory as a formal framework to understand the notion of abstract object in the context of the discussion on the reference of theoretical terms. So, I will skip this. Falta's theory starts with the consideration that although expressions like number 2, the fountain of youth, Sherlock Holmes, do not designate spatiotemporal existing entities in no possible world, it should be assumed that there are entities of a certain type which are denoted by such expressions. This is, so to speak, the main general idea. And Falta calls abstract objects entities that cannot be spatiotemporal, entities including entities traditionally considered to be abstract, like numbers or sets, fictional entities such as Sherlock Holmes, or impossible entities. And his theory, of course, has many applications to many different problems in the philosophy of language, in the philosophy of mathematics, and even has applications in the interpretation of philosophical theories. For example, Falta has a nice interpretation of Leibniz monadology or Plato's theory of ideas in terms of his theory on abstract objects. That X is an A object, that means abstract object, is expressed by A exclamation mark X. A disjunct set of the set of A objects is the set of ordinary objects, and he defines ordinary objects as possibly spatiotemporal. What it amounts to the same, they are possibly concrete. This is the definition in lambda notation. So you have, on the one hand, abstract objects, which cannot be in no possible world spatiotemporal, and ordinary objects, which can be in some possible world spatiotemporal. So abstract objects cannot be concrete. It's a modal distinction. Ordinary objects exemplify properties, and this is formally expressed by the customary predication. Yeah? Whereas abstract objects are determined by a group of properties, we can say that those which constituted it. Thus, the object denoted by Sherlock Holmes is determined by all the properties that are attributed to him in the novels of Conan Doyle. For example, being a detective, or living in London, for example. But in the case of abstract objects, there are important, in fact, essential distinction, which is the double predication possibility. Predication, in the case of abstract objects, could come in two forms, exemplifying properties or codifying them. And Falta says that abstract objects encode the properties attributed to it. For example, in the case of Sherlock Holmes, the property of being a detective, because it's the property which is attributed to him in the novel of Conan Doyle. And he expresses this formally through another type of predication. This would be the other kind of predication, where instead of having A first F and then A, you have first A and then F. But as I have said, while ordinary objects only exemplify properties, abstract objects, in addition to encoding, also exemplify properties. For example, Sherlock Holmes encodes, not exemplifies, encodes properties like being a detective, but also exemplifies properties like being a fictional character or being conceived by Conan Doyle. These are properties which are exemplified, not codified, by these entities. In a similar way, a mathematical object exemplifies the properties of being abstract or not having mass. In any case, although the abstract objects considered until now have been individuals, as I have said before, Falta also considers that certain properties and relations are abstract objects. And he explains this very rigorously because he has a type theory in order to distinguish the different kind of abstract objects in his theory. This is the general definition in type theory notation. Those properties denoted by words such as unicorn, hobbit, or, if you want, these examples are added by me, phlogiston and caloric would be abstract objects, insofar as they are not concrete, given their fictional character. So we can also accept that such properties are universals with instances, which in turn are fictional, and therefore at the same time are abstract objects. For example, think of a fictional story. It's possible to consider certain particular instances of Hobbit. For example, in The Lord of the Rings, Bilbo and Frodo would be those instances. Falta provides an interesting example, as I said before, of relation which, because it is fictional, must be regarded as abstract, namely that which corresponds to the term absolute simultaneity in classical mechanics. It's fictional due to the fact that it's rejected by the theory of relativity. According to this account, it makes sense to say Einstein discovered that simultaneity doesn't exist. This is the only example in his book on abstract objects, but in recent times, for example, in one of his last talks, he proposed that his theory could be applied to the case of scientific terms, typically, for example, phlogiston, of theories which have been rejected, but not for all theoretical terms. For example, not for theories which are accepted today. And this is my proposal, to use his theory to account for the reference of all theoretical terms, no matter if they belong to theories that are rejected or to theories that are, in fact, accepted nowadays. Abstract objects, be they abstract individuals, properties, or relations, are incorporated in his theory using an axiom of comprehension, which establishes that for any condition phi on properties of certain type, there is an abstract object, precisely such property, encoding precisely such properties and not others. I will skip the symbols because we don't need to come to the details. Given the axiom of comprehension, the following is a consequence in his theory. This is a theorem of unicity. This consequence asserts that there is a unique abstract object which encodes exactly the properties which satisfy the given formula phi. And how phi is established? Of course, by the theory which introduces the term in question. So the treatments given to properties designated by phlogiston, caloric, simultaneity, Newtonian mass, in the light of Falta's theory would be similar to which this theory gives to fictional entities such as Sherlock Holmes. A certain point of view on empirical theories favors extending that treatment to every scientific term. On this account, scientific terms would always denote abstract objects, properties and relations, typically in this case, and Kuhn's constituted kinds could be also, or could be at least also understood in these terms as abstract objects. We must take into account that every empirical theory is subject to being ultimately rejected, and at best, theories are considered to provide idealizations or approximate proposals about the world or parcels thereof. So these are the reasons because I want to extend Falta's theory to the case of the analysis of theoretical terms, and I think. So to speak, this application of his theory to the case of the analysis of theoretical terms has many interesting consequences. So under this interpretation, one can consider empirical theories as fictional stories which denote abstract objects thanks to their descriptive terms. The entities designated by scientific terms would be as much inexact properties or relations for certain ordinary properties or relations. In such cases, to each abstract object or property or relation denoted by a scientific term, a particular ordinary object would correspond. And under this interpretation, well, this I have. Okay. Now, this is important. We can consider theories as stories. Stories, in Falta's theory, is a technical term. It's not new. In an intuitive sense, there are many people who have said and defended that scientific theories are like stories. For example, here are some famous quotes. The first one is actually one of Van Fraassen, but he is describing what the realist is saying, not what he himself is saying. For example, Jonathan Turner says, theory is a story about how and why events in the universe occur. There are a lot of quotations like this. So this is not uncommon. This is not, so to speak, uncommon. But in Falta's, as I have said, a story is a technical term. Falta defines a story as a particular kind of situation, and situation is also a technical term. A situation is an abstract object, so scientific theories would be abstract objects too, more complex of course, but would be abstract objects, encoding only propositional properties. Where a property is propositional if and only if, for some proposition P, F is the property being such that P. He expresses this in lambda notation, but this is not important now. We can also say that for every propositional property P encoded by the situation, we shall say that P is true or holds in that situation. So a situation is defined as an abstract object. All of the propositions which encode or are encoded by X, by these abstract objects, would be propositional properties. And now a story is defined in this way. A story is no less than a situation in which, or for which there is a concrete object who authors that situation. So, and who would be this guy? Would be a scientist. In the case of stories like, because he applies this definition to the case of stories like, for example, Anna Karenina. Anna Karenina would be a story, would be a situation, would be an abstract object for which there is a concrete object, namely Tolstoy, who authors this, this story. And my proposal is to understand scientific theories in this way. So we will have a definition in Falta's terms in which a scientific theory is understood as a particular kind of story, a situation that is authored by some concrete object, the scientists of a given community, and satisfies some further conditions that distinguish theories from other fictional stories, of course. For example, that X, the situation in question, the story, which is the scientific theory, contains projectable generalizations. Not only that, for example, C that would be the member of a scientific community would aim to apply X, the theory, to a particular intended application. Y is the set of intended applications. Here I define first a relational definition in which I define X is a theory, a scientific theory of or for Y, where Y is a set of intended applications. And then we have a more general definition. And as a consequence, a scientific theory would be a story in Falta's term. So let now sigma t be an operator which is read according to the story t, and by means of which we can establish the entities just as they are conceived internally to t. So in the case for a theory t, where R1, Rn are its t non-theoretical terms, and S1 to Sn are its t theoretical terms, we will have that if S1 t is nt, name the corresponding constituted kinds for the t theoretical terms, then the term S sub I would be that abstract object, yes, that encodes those properties which are attributed to S sub I by the theory T, by the story T. So in Falta's terms, we can express exactly what, would be the abstract object referring to which refers the term as I. So, but the assumption of the axiom of compression is too strong to capture Kuhn's intuition, and I will skip this, although it is important, but in Falta's theory, we can have something very similar to the Ramsey sentence. This could be the properties that are encoded by the different theoretical terms of the theory. FLs are here the fundamental laws of the theory, and these are conditions express empirical conditions about the intended applications. I will skip this because it would take too much time, and it's not very important now. So we can define all theoretical terms in this way. I suppose you are getting this. If not, I can explain more about that, give the details of this. For reasons that I cannot explain here, the comprehension axiom in Falta's theory is maybe too strong for the case of scientific theories, and we have a restriction of this comprehension axiom that is perfectly, I think, suitable and adequate. I will skip all this now. This is a slide where we compare our results with David Lewis' method for the definition of theoretical terms through the Ramsey sentence, and everything is equal except for the fact that in Lewis' approach, all the theoretical conditions are required for the determination of the reference of a given theoretical term, and in our approach, this is not the case. We only require the fundamental conditions, namely the fundamental laws plus some important constraints that help to fix the reference of the theoretical term in question. So we extend this kind of considerations not only to theoretical terms. How many minutes I have?
3.
Okay. So not only for the reference of all theoretical terms, but also for what we call scientific models and ideal terms. So think of examples like, for example, rigid body, ideal pendulum, and so on. The reference of these ideal terms would also be abstract objects. And in the theory, we extend the theory, Falta's theory, in order to capture all these ideas. For example, we begin by defining a proposition as ideal in a very simple way. P is ideal when there is at least one Q which is accepted by SID, where SID is a member of a scientific community. Q is empirical. Q is an empirical proposition. And the idea is that P, which is the proposition which is ideal, is such that the conjunction P and Q is not possible. And why? Well, take the case of simple pendulum. Simple pendulum, or, well, yes, the case of simple pendulum, the law for the simple pendulum presupposes that there is no friction, for example. So there would be a proposition, in this case, there is friction in nature, and even in the laboratory, there is some friction and air resistance, for example. And this proposition, there is air resistance or there is friction, would not be compatible with the proposition P, which is ideal, which could be in the case of ideal pendulum, there is no friction, for example, there is no air resistance. Sometimes it's not a logical contradiction, would be simply that the conjunction between P and Q are not nomically possible. It's not nomically possible. So this diamond could be understood in restricted to nomic possible walls. I have no time, I think. I will end here, but I will maybe pass to the conclusions. We use these definitions in order to get some results, which now are, I cannot explain now, but this is the definition of ideal objects. For this definition, I need the definition of an ideal proposition. I will skip this, though this is very important, and I will pass to the conclusions. The idea is that the advantages of this approach could be that, sorry. I have no, the idea would be that this approach would not have the same problems of like realist accounts of reference. Is a proposal that provides us with a theory of reference which is appropriate for the idea that scientific theories are like fictions or something like that, like fictionalists say, and make sense of the idea that through the development of a scientific theory, the theoretical terms preserve the same reference. And I think it's neutral with respect to the scientific realism issue, but we can discuss that if you want. Thank you.
And let me warn you that this is, I started thinking about this issue about 20 years ago, but there hasn't been much progress since, so you'll judge for yourselves. It seems to me there is a real problem, and the problem is that there are two desiderata, if you like, that we want the theory of reference of theoretical terms to satisfy. One of them is that the burden of reference of theoretical terms should rest with the theory in the sense that what they refer to is determined, at least to some extent, maybe to a large extent, by the theory in which they feature prominently. But there is a second desideratum or intuition that theoretical terms should be trans-theoretical, in the sense that they can refer to the same entity even though they may occur in different theories. Or similarly, different terms may refer to the same entity. And things would be easy if we could just forget of one of the two desiderata. We could have a perfect theory of reference for the first, or perhaps for the second, but if we want actually to have a theory which puts both of them together, irrespective of whether one is a realist or not, then there is a tension. And the tension is that the standard description theories of reference satisfy one, but not two, the trans-theoretical element in reference, while the standard causal theory satisfy two but not one. So that's a starting point, and the starting point is, can we do better? Can we develop a theory of reference which tries to satisfy both desiderata, and what shape this theory of reference should have? That's what I call causal descriptivism. That's what I've been trying to formulate, working on and off on the issue since my doctoral dissertation about 20 years ago now. So I'm going to go through some basic revision, what these two traditional theories are. Most of them will be well known to most of you, but it's for the sake of the structure of the argument, it's nice to actually go slowly and see what the problems, identify what the source of the problem for the tension is. So description theories of reference, of course, it's theories. There are various theories which are descriptive, but the key idea, whichever way you look at it, is that reference, successful reference or reference requires knowledge of some identifying facts about the referent in order to refer successfully to it, where these identifying facts or marks are captured by descriptions of the reference. So if nothing satisfies the associated description, the expression does not refer to anything. And that's the key idea behind a very seminal thought Frege had, the idea of modes of presentation, that there might be different ways to present a certain referent or a certain object, and the same referent might be presented in two different ways by two different modes of presentation. Now, there's some discussion here, but I think it's essentially correct to say that modes of presentations are senses, or senses are modes of presentations, and senses are descriptive mechanisms that fix reference. The key descriptive idea, or descriptivist idea, is that first sense then the reference, or the sense determines the reference. Now, if you look at philosophy of science over the past 100 years, the description theories of reference were never actually assumed explicitly. To the best of my knowledge, no one says I'm using this kind of theory of reference to fix the meaning of theoretical or other terms, but they were operating in the background. Perhaps they're operating in the background because they were the only theories available until the late 1960s maybe. But if you think of famous attempts by Carnap, which turned out to fail, to introduce or characterize or define theoretical terms like explicit definitions initially, then reduction sentences, etc., they were all implicitly relying on descriptive theories of reference. Now, a well-known shortcoming, of course, this was coupled with a very strict, I mean, whether it was strict or not, it can be debated, but there was some adherence to the thought or to the claim that there is a special class of terms called observational, which get their meaning independently of theory. Okay? This was a dominant idea for many decades, and of course the description theories of reference of theoretical terms were coupled with this commitment to a distinction, to a semantic distinction between theoretical terms and observational terms. And the shortcoming or a shortcoming of this coupling is that nothing in the description theories themselves forbid the referent of an expression to be an observable entity. So the problem was not the description theories of reference themselves, but if you like, the attempt somehow to show that theoretical terms should be introduced by means of descriptions in such a way that the content is captured or fully captured or to a large extent captured by their observational consequences or by observational terms and predicates. Now, the demise of the distinction between observational and theoretical terms, this was in the early 1960s maybe, freed the description theories of a burden. And I think this was a big step forward. And the key thought there was that the burden of reference actually rests upon descriptive phrases, and this was freed from the redundant and ill-motivated extra condition that these descriptive phrases should be couched in an observational vocabulary. You heard this idea before in its probably first introduction by Hilary Putnam. He introduced this idea of low cluster concepts. All theoretical concepts of a theory are low cluster concepts. They get their meaning via a plethora of nomological statements in which they occur. And there are two well-known consequences of this view. The first is that since the nomological statements that constitute the low cluster are synthetic, there is no way to separate these statements into two cleanly divided camps: analytic, meaning fixing components, and empirical content or synthetic statements. The second consequence was that the meaning, and hence the reference of theoretical terms, is fixed in a holistic way. The theoretical terms are implicitly defined by the nomological statements that specify the network of the connections within a theory, more specifically by all these nomological connections. And that's a very well-known fellow. Semantic holism flourished in the late 50s, early 60s, and I think as an idea it contributed quite significantly to the wide acceptance of the claim that theoretical discourse is meaningful and that theoretical terms have putative factual reference. But semantic holism has actually two shortcomings of his own. The first has to do with the very idea of implicit definition. The second has to do with the extent of holism. Now, I'm going to come back to that later on, but implicit definitions are very useful, of course. They fix meaning not by analyzing already known and understood concepts, but by legislating in a stipulative manner the truth of certain propositions of which the defined concepts are constituents. Hence, in this sense, they create or constitute meaning. For something to be an F, that is, for a concept of F to apply to this, such and such conditions must be satisfied. But there is a chief drawback as implicit definitions. An implicit definition is what I think Slick early on called an indefinite description. Why? Because it defines a whole class, if you like, a class of classes of objects which can realize the formal structure as defined by a set of axioms. So there is no straightforward way in which unique satisfaction of the descriptions associated with implicitly defined theoretical terms can be assumed. You cannot actually get uniqueness out of implicit definitions right away. Now, this bothered a lot of people, but it bothered Slick quite early on, back in 1918, when he wrote the very, very nice book, General Theory of Knowledge. And there, Slick suggested that we can avoid this problem when it comes to the point of application of the theory to the empirical world. When we apply the theory, we say which of the various structures that realize the theory are those we want to pick out and define, if you like, the terms of the theory on the basis. But for this idea to work in the first place, we need to assume a distinction between the observational and the theoretical vocabulary, and this is a dodgy distinction. We need somehow to draw a distinction between what came to be known antecedently understood vocabulary, which is again not maybe theory independent, but independent of the particular theory we're looking at. The second problem is that even if we actually fix the observational vocabulary in an independent way, it is still an open possibility that the theoretical structure that is fixed by the implicit definition is multiply realized. So you don't really get unique realization by just fixing the observational vocabulary. More serious though was the problem of the extent of meaning holism. And it seems to me the otherwise liberating coupling of description theories with semantic holism became an unstable position. Description theories do warrant attributing reference to theoretical terms, but if semantic holism is rampant, if the meaning of all terms, including those that normally count as observational, is specified in a holistic way, then we've got a serious problem. Coupled with description theories of reference and their key point that since the term is reference, semantic holism yields as a further consequence an even more radical thesis, namely reference variance. In this sense, change of references becomes inevitable when theories change. Even slight changes of theories might change the reference of all terms of the theory, hence the denial of the view that theoretical terms are trans-theoretic. So these are the usual suspects. Kuhn, Feyerabend, I could have put up quotations here, but this move was associated with them. Now, I need to insist on this. The description theories of reference are not necessarily holistic. And I think it is holism that does most of the work in getting radical reference variance. In particular, the culprits are the following two views. First, the network of nomological statements specify the descriptive sense of a scientific terms in a holistic and undifferentiated manner. And second, changes in those networks are always and necessarily such that they yield incompatible descriptions of the same terms. I think there are good reasons to deny both of these claims. Very quickly, three of those are, I take it, very well known. First, radical reference variance theories entail that the referent of a term changes whenever there is even the slightest change in the network of descriptions in which the term is actually occurring. Hence, the theory leaves little, if any, room for sameness in reference. Second, the theory entails that all scientific disputes about the features of a positive entity were mere equivocations. They could have been avoided had the relevant scientists been prudent enough to point out that they were talking about different entities. Finally, it entails that there is no way to assess whether past scientists were right or wrong in their beliefs about the furniture of the world. So it was this kind of setting, if you like, that started to lend credence to this idea first introduced by Sol Kripke, which came to be known as causal theories of reference. And if you think of it in its initial formulation by Sol Kripke, it's a causal historical theory, as he put it, of proper names, in the sense that it rendered the causal historical chain of events that link current uses of a term to its introduction part of both the reference fixing and the reference transmission mechanism. So the theory, if you think of it, was causal in an oblique way. It was causal in the sense that the reference transmission mechanism is causal. The reference fixing mechanism is causal too, but only in the sense that the introduction of the name is done and hence its reference is fixed in the presence, that is, in the perceived presence of its bearer. So someone named Aristotle in the presence of Aristotle. Presumably it could have been even in the presence of Aristotle, saying my baby, my newborn baby will be called Aristotle, okay? And then this name got in a chain of transmission and it came down to us and we all talk about Aristotle, even though of course we're not acquainted with him. So causation is involved, but in an oblique way. Now, when Putnam reshaped this theory, things were quite different because then he actually wanted to make causation play a genuine role in the fixing of the reference. So Putnam extended this view to cover the reference of natural kind and physical magnitude terms. And then the relevant introducing event, for instance, the kind term gold, involved, Putnam thought, causal contact with samples of the dubbed stuff. But this is not clearly enough to fix the reference of a natural kind term, the reason being that at most it succeeds in making the term referring to the sample of stuff that was actually present. So something more was necessary, and this more was a principle like that. For all x, x is an f, e.g. an elephant, if and only if x stands in a specific similarity relation, for instance, sameness of nature, to this specific object picked out by ostension. And of course, it's well known, there was some interesting debate about how exactly we should understand this idea of sameness of nature, manifest properties or superficial characteristics or underlying unobservable nature of this particular entity. When Putnam talked about physical magnitude terms like electricity, it was a variation on the same theme. He spoke explicitly of an existential introduction of a referent, an entity causally responsible for certain effects to which the term T, electricity, refers. So one has asserted that there is a phi. Phi is causally responsible for certain effects, phi, capital Phi, and for all terms T, T refers to phi if and only if T picks out a causal agent or the causal agent of phi. Now, there is a chief attraction, and the chief attraction which made this theory, it seems to me, very popular, is that even though past scientists had partially or fully incorrect beliefs about the properties of the causal agent existentially introduced, their investigations were continuous with investigations of subsequent scientists. But there is a well-known major problem, and this is that referential success became more or less trivial. Insofar as there is a causal agent and one, then all terms refer to whatever this causal agent was, no matter how misplaced, wrong, extraordinary, or even false the beliefs associated with this entity were. So, in a lines parallel to what I said about description theories, where I suggested the culprit was the holism, not the idea that there is a descriptive component in reference fixing, I think the problem here is not with the idea that causation is involved in reference fixing. It should be clearly part of the story of the referential failure of phlogiston, that phlogiston did not cause the phenomena for which the term phlogiston was introduced. And it did not cause them because we now believe, probably with very good reasons, that phlogiston was never there to cause anything to happen. Okay? So referential failure should partly be attributed to the lack of the agent that was supposed to cause these things. So the problem, I think, is that the presence or absence of a cause in and of itself cannot be the total determinant of reference. So in other words, if we take a lesson from descriptive theories of reference, this should be that modes of presentation of the referent should be added to a theory which has some causal element as a key component. So that's how I think myself and other people came to the idea that there must be some kind of hybrid position known as causal descriptivism. And there are two basic ideas, one negative, the other positive. The negative idea is that the reference fixing mechanism should not be just a non-conceptual causal relation to the referent. If it were, referential success would be too easy to get and probably trivial. However, the reference fixing mechanism should not be just a conceptual description or description-based relation to the referent. If it were, referential stability would be hard to get. So the basic positive idea is that the reference fixing mechanism should have the following form: Rx equals x causes phenomena phi and dx. So the term t refers to x if and only if Rx is true, if and only if x causes phenomena phi and some description is satisfied. So the way I now think of the matter is that this extra constraint on the causes and this more specific causal description, if you like, of the agent and its properties puts a limit to the holism, to the holistic description introduced by the theory. So the causal relation with the referent plays an indispensable role in reference fixing, and this is meant to be captured by the claim that x causes phi. But the causal relation is not enough. A reference is fixed by means of descriptions of the causal role attributed to the putative referent. This is meant to be captured by this causal description D. Now, D is a causal description that is a description of the ways in which the positive referent is supposed to be causally connected with the phenomena phi that is taken to cause. Now, the causal component is required because the referents of theoretical terms are introduced as causes of certain phenomena. In most typical cases, you introduce a theoretical entity and you introduce a name to refer to it because you want to give a causal account of some observable or empirical phenomena. The descriptive component is required because the referent, the cause of phi, should be attributed some properties, those that capture its causal role, if cognitive as opposed to mere causal access to this agent is to be had. Both components are required. That both components are required may be seen from the fact that their verdicts may not match. They might be in disagreement. The entity that satisfies dx vis-a-vis phi might not be the entity that does cause this phenomena. And that's an instructive case, overexploited oxygen versus phlogiston. Is there a fact of the matter as to how they pronounce phlogiston? Probably phlogiston, I think they would say. But we say phlogiston, no, phlogiston, okay? So there is a mismatch between the two components of Rx if they are taken separately. The cause X of the phenomena phi of combustion was the presence of oxygen, and yet the phlogiston-based description dx of the cause could not single out oxygen as the cause. So the presence of both components of Rx makes sure of the following. A term refers to X only if it is the cause of this phenomena, phi. If the causal description X dx is satisfied by some entity X, but X is not the cause of phi, then T does not refer to it. Conversely, if something does indeed cause phi, but the X is not satisfied by this something, then T does not refer to it. So I claim you need both elements, this hybrid theory, to have a sensible theory of reference that satisfies both of the two desiderata that I started with. There are well-known objections. I'm going to go through them. Three, I think. The third one is probably the most important. So the first objection is that this hybrid theory is ad hoc. Its only motivation being to accommodate counterexamples to the two standard theories of reference. Now, my reply to this is that it seems to me, independently of this idea that we might want to avoid counterexamples, that a general plausible condition on reference fixing is that two elements, that it combines two elements that need not coincide in all cases. That is, a causal element and a cognitive element. Now, in ordinary cases of perception, when we fix the reference of proper names, or probably of some natural kinds, In most of these cases, at least when things go well, not always go well, but in most cases they do go well, these two kinds of access coincide. So we've got at the same time causal contact and cognitive contact. If only because perception normally operating is quite reliable, so it gives us some properties which give us cognitive access to this element. So perception is a process by means of which we're in causal contact with worldly objects and by means of which we can get cognitive access to them and their properties. So in the case of perceptual contact, Rx is independently plausible and as a rule correct. So there is some reason why we need both components anyway, despite of the counterexamples. In the case of fixing the reference of theoretical terms, these two conditions diverge. In most typical cases, there is no perceptual contact with the referent. It's an unobservable cause, though there is causal contact. If we are lucky and we successfully refer to something where we have some causal contact with it, with no conceptual contact with it, with no knowing what it is, the thing that we have causal contact with. Hence, there must be a way in which cognitive access to the referent is ensured, at least in principle. Otherwise, the entity that does the causing of phi might not be even in principle cognitively accessible. Then referent fixing would be a merely existential act. There is something that causes phi. The cognitive access to this something would require some kind of description of it, a description which would offer some identifying marks. So it seems to me this condition I put forward becomes independently plausible. It ensures the cohabitation of two elements of reference fixing, the cognitive and the causal. Now the second objection, some people put it to me and they've put it in print. The account offered is not really a hybrid account. It is in essence a descriptive account of reference fixing. The reference, it might be said, is fixed by a causal description. I thought hard about that for many years. On reflection, I think nothing much hangs on this objection. It's totally semantic. If the causal element in the original theory of reference is if the causal element in the original causal theory of reference is reduced to the role that causation plays in the transmission of reference of a term from those present in the act of baptism to its current users, this is a very thin causal theory of reference. If, as is more plausible, causation is said to play a more central role in reference fixing by linking the name with its referent without the need to interpolate an identifying description, then the objection noted above does suggest that there is more to reference fixing than causal contact. If descriptions are allowed to play some role in reference fixing, it's a semantic issue whether the resulting theory is really descriptive. The final objection is the most important one. I call it the too little, too much objection. So the issue is how rich the description should be, given that it is not the whole of the theory. If we forget about holism, how rich should the causal description be? If the causal description dx associated with a newly posited entity is very rich, even though it may explain in virtue of what mechanisms it is supposed to play its causal role, it will be difficult to be satisfied by anything, let alone to guarantee some referential continuity in theory change. If, on the other hand, the causal description attributed to a newly posited entity is too thin, it is quite likely that it will be multiply satisfied. Hence, there will be no guarantee that a unique referent is picked. So this is the too much, too little objection. And my reply to this is a bit cynical. Dx should have the right size. It should be neither too rich nor too thin. But how is this possible, one might ask? It is possible because descriptions associated with theoretical terms play a certain role in reference fixing. They are meant to offer enough identifying markers of an entity related to its causal role vis-à-vis some phenomena to allow the stable use of the term in certain inductive and explanatory practices. But they are not meant to asphyxiate the putative referent, that is, to leave no room for error, ignorance, and improvement. I take it theory development is an ongoing process, and it is an ongoing concern of the scientist to maximize the chances of referential continuity of theoretical terms without, however, making referential continuity inevitable. Hence, care is generally taken to associate with the term enough descriptions to pick out its reference uniquely and to ground its putative explanatory role, but not too many to forestall any referential continuity between different theories. There is evidence for this, and this is the fact that, as a rule, there is consensus vis-à-vis referential success and failure among scientists, which means that there is consensus as to which really were the reference fixing descriptions and which were not. Here is an interesting case, a difference between caloric and electricity. And to show that we don't just go back from the future to reconstruct what these terms picked out, I'll give you two slides with dictionary entries back in 1832, and I think one a little bit later or earlier. So, which is quite interesting to see the difference between the introduction in the same dictionary of caloric and electricity. Caloric in chemistry, a modern term introduced into philosophy to denote that substance by the influence of which are produced all the phenomena of heat, blah, blah, blah. Electricity, the name of an unknown natural power which produces a great variety of peculiar and surprising phenomena, the first of which are supposed to have been observed, blah, blah, blah. There is an important difference in the way that the referents are introduced, are described. In the case of the caloric, it is part of the identifying markers of it that it is a material substance. There is no such pretension in the electricity. Electricity is picked up by descriptions that allow refinement and of the putative nature of the power that produces certain phenomena. A few years earlier, Andrew Ure did more or less the same thing in another dictionary, the caloric entry and the electricity entry. Actually, what's interesting here is that in the case of the electricity, he was careful enough to note, in the case of the caloric, that there is an alternative account of the causes of heat phenomena, the vibratory motion of particles of common matter. Okay? So let's try to make the theory a little bit more precise. As I said, I worked on this many, many years ago, and when I first articulated it to my own satisfaction, I used this idea from Berend Ench, that the burden of reference is borne by kind-constitutive properties attributed to the positive entity. Hence, I claimed that the causal descriptions that fix the reference of a given term, what I now call dx, should capture these properties. But that's a bit too strong, because we have no theory-independent access to the kind-constitutive properties of a natural kind. And in any case, we have to rely on theories and their causal explanatory descriptions of the entities they posit. If we take this line, it's not the case that the whole theory is implicated in referent fixing. The kind-constitutive properties are those whose presence makes a set of objects have the same or sufficiently similar manifest properties, causal behavior, and causal powers. The specification need not involve the whole theory. So that's the idea I had back when I published my book on scientific realism, that you should focus on the kind-constitutive properties. This is not the whole of the theory. This is not the whole network of the properties attributed to the posited entities, but these are those that somehow explain manifest properties, causal behavior, and causal powers. And the thought was that if we assume that natural kinds have boundaries based on objective similarities and differences, not necessarily on a shared essence, we can see how causal descriptions succeed in fixing the reference of a term. The one and only entity to which the term refers is the entity which is characterized by the relevant kind-constitutive properties. So dx identifies the referent x of the term in such a way that if no entity satisfies this, if it is true of no entity, then t does not refer to it, and if an entity y does not satisfy x, dx, y and x cannot play the same causal role. So on this view, we have a readily available account of referential success and failure. We can say when there is genuine success, we can say when there is genuine failure. Now, lately I think I've started thinking that we need to broaden this idea a bit or relax it a bit by claiming that the burden of reference is carried by any stable identifying properties, provided that they are taken to contribute to the causal role attributed to the positive entity vis-a-vis the phenomena phi. It might not be the kind constitutive property, and it seems to me that's important because what properties are kind constitutive might be a matter that is settled at quite an advanced stage of inquiry, where a successful reference can be established at quite early stages. I hope, and it is hoped in general, I guess, that the identifying properties will be part of the kind constitutive properties of the positive entities, but this is not something that has either to be assumed ab initio or required in the end. Again, two objections to this idea. Can stable contingent properties play a role in reference fixing? Forget about them A. Relying on Kripke's well-known modal arguments against descriptivist theories, one may argue that in modal contexts where the referent does not possess these contingent properties, a reference may still succeed given the causal connection. Hence, there is a danger that the suggested account is descriptivist only in name. So that's the converse of the objection we saw before. Now it's a causal account, not a descriptive account. My reply is more or less the same as above. It is precisely an advantage of this account that a reference is not fixed by descriptions only. Causal contact serves the purpose of anchoring the descriptions to the referent, thereby rendering these descriptions of the referent in the actual world. Again, relying on Kripke's well-known epistemic argument against descriptivist theories, one may argue as follows. If we are wrong about the descriptions which concern putative contingent properties, but still in causal contact with the referent, do we succeed in referring to it? If yes, doesn't this show that it is the causal element that is essential to reference? If not, why not? My reply to this is that referential success is not merely a matter of causal contact, since it requires that the theoretical terms track their reference, which is achieved by securing identifying marks of the reference, however contingent. To put it succinctly, causal contact anchors the descriptions of the referent. Descriptions enable tracking the referent. Now, when I was thinking about that, I started looking at the case of chlorine. It was a bit of an accident, but it's an instructive case, because the term chlorine was actually introduced in 1812 by Humphrey Davy. So he legislated. And he introduced it to refer to what was taken to be dephlogisticated muriatic acid. I don't quite know what this is, but it was a real thing. And this real thing had been isolated by this gentleman over here, Michele, which was what we now call chlorine, of course, already in 1774, but being based on the phlogiston theory, he described it as dephlogisticated muriatic acid. He produced it by heating manganese dioxide with hydrochloric acid, which was called muriatic acid. The idea was that the heating had removed phlogiston from this muriatic acid. Now, there was some controversy as to whether dephlogisticated muriatic acid was an element or a compound. Davy experimented with dephlogisticated muriatic acid, became convinced that it was an element, and called it chlorine. So he rebaptized it. Actually, the very term chlorine, unbeknownst to me before a few months, was introduced to capture the greenish, yellowish color of the gas from the Greek word chloros, which means green. Yes, chlorine. I didn't know that. So Davy was aware of two things. One, the gas he had isolated was the same gas that Michele had isolated. There was no doubt about that. Michele's description of it was flawed. David believed that. The key problem was that dephlogisticated muriatic acid did not contain oxygen. It was an elementary substance. Okay? So there was something there which caused this phenomena he manipulated. He was in causal contact with it, he thought, but Michele had identified it the wrong way. He had actually given wrong descriptions of it. And Davy was fully convinced about that. So he decided that he should change the name, and he baptized this chlorine because of this situation, to mark that now we get the description of this causal agent right also, not just the presence of this whatever it is, gas. The change of name was meant to suggest not a change of the reference, but a change of how the referent was identified via appropriate properties of it. There is some story which I've got in a paper I've published on this in a volume with a few quotations by Davy and others. The bottom line is this: chlorine is an element, not a compound. It does not involve oxygen. It has bleaching power when water is present. It is a constituent of sea salt. It unites with hydrogen in equal volumes to produce hydrochloric acid, etc. So this is roughly an example of what I call DX, an associated description. It is a description of a causal agent of a certain sort. It is a description by means of associated properties and relations, enough to identify an entity and make sure we talk about the same entity when we do science about it, but without saying that it is simply this agent, whatever that is. So Davy was open to the fact that this might prove wrong, or some of them at least. He was almost certain that they would need refinement, and that's a very interesting point, it seems to me. Ultimately, the reference should be fixed by the kind constitutive properties of chlorine. Here's a quotation: as chemistry improves, many other alterations will be necessary, and it is to be hoped that whenever they take place, they will be made independent of all speculative use, and that the new names will be derived from some simple and invariable property, and that mere arbitrary designations will be employed to signify the class to which compounds or simple bodies belong. But until this is done, in future time, there is no reason to think that reference has not been fixed by means of stable characteristic properties. Indeed, it is clear that all subsequent discussions relied on the fixity of the reference of chlorine to an element, not to a compound. And there is a well-known story with chlorine, of course, because the atomic weight had this peculiar 35.5 value, and it was an anomaly to Prout law of definite proportions. It turned out that samples of chlorine contain two stable chlorine isotopes, 35 and 37, in a certain ratio, not ration. Now, I take it that this development is instructive when it comes to reference refinement, which also plays a big role in science. Isotopes are atoms with the same number of protons, but different numbers of neutrons in the nucleus. Isotopes of the same element have the same chemical properties, but different physical ones, that is atomic mass. The very term isotope was introduced to refer to entities, atoms, with different causal roles vis-à-vis various radioactive phenomena, but located in the same place in the periodic table, that is having the same atomic number and chemical properties. It turns out that the two kinds of chlorine play the causal role specified by the initial description, dx. They were different in virtue of properties that differentiated nuclides. A nuclide is an atom with a specific number of protons and neutrons in its nucleus. Hence, there are two chlorine nuclides, and it is arguable that they capture a finer division into two kinds of chlorine. So the initial term chlorine admits of reference refinement, which is achieved when the original identifying properties are defined in such a way that there is a better matching between them and the kind constitutive properties. Okay, no reference is changed, but reference is actually refined. So, am I okay on time? Okay. The foregoing account has a number of genuine advantages. It does not make referential continuity inevitable. It explains both referential failure and success in a non-trivial way. it allows for a further determination of the referent by means of added-on descriptions. It leaves open the possibility of re-identifying the reference of a term, e.g. when it turns out that x equals y, even though dx is different from d prime y. This is likely to happen where there is a unifying description that brings under its fold both dx and d prime y. I think something like that happened with the case of optical waves and then electromagnetic waves. It shows how the associated descriptions dx track the referent of the term. This happens when they do succeed in identifying the causal agent of the phenomena. Now I've got to make a decision now, but I think I've made it already. I mean, I can stop here with the last slide, but because the conference has spent so much time on Ramsey sentences, I need to say something because I'm partly responsible for the revival of interest in Ramsey sentences 20 or so years ago, and I feel already guilty enough. So here is a big question. Can a Ramsey sentence approach to theories dissolve the issue of the reference of theoretical terms? Can we go home after this conference, and sleep happily ever after, that we don't have to worry about this problem anymore? Now, you all know about Ramsey sentence a hell of a lot, so I'm not going to say what a Ramsey sentence is, what a Carnap sentence is, what a theory is, and how it is partitioned, but you all know this by heart, okay? I use the traditional Carnapian way to write a theory, TC, that's a theory in correspondence rules, okay? And this should have to be an exponent, but there's something wrong in the formatting. So you all know this, okay? This is something that Carnap proved himself. Actually, I've seen the proofs, in the archives. So that's not something you find in Ramsey. The idea is that given this equivalence, we can think of the theory as implicitly defining its theoretical terms. So the Ramsey sentence says that there are classes of entities which are correlated with the observable events in the way the postulates of the theory describe, but it does not say what exactly those entities are. It does not pick out any such class in particular. I use the term correlated because there is some debate here. That's what Carnap thought, and he spoke neutrally about correlation. Maxwell talked about causation, but causation is a theoretical concept in a sense. Therefore, causation should be Ramsified away, not be part of the cement of the Ramsey sentence. But the Carnap sentence is more interesting. If anything satisfies the Ramsey sentence of the theory, then the entities posited by the theory do. That's Carnap's. Somewhere he said that, I don't quite know. Recall where. Hence, the theoretical concepts of the theory are implicitly defined by the Carnap sentence in such a way that they refer to whatever entities satisfy the Ramsey sentence. Now, that's an implicit definition. It stipulates meanings without defining them explicitly. Modulo the Carnap sentence, the theory is equivalent to its Ramsey sentence, but no theoretical terms occur in Ramsey sentence of the theory by construction. That's its big advantage. It might be thought the problem of the reference of theoretical terms is actually dissolved with a this in brackets, of course. And it seems to me there are two ways to proceed. At least there are two ways people think about the issue. One is eliminative, the other vindicatory. So the eliminative way says the issue of reference of theoretical terms vanishes. We don't use theoretical terms. There is nothing to talk about. Let's go home. The vindicatory way is more theoretical terms friendly, and it says the issue of the reference of T terms is solved once and for all. Okay? We specify the meaning of theoretical terms, end of story. Again, we go home and have a beer. Now, the key difference between the two, the vindicatory and the eliminative way, concerns the status of the Carnap sentence. The eliminative approach associated with my supervisor of all people and Pierre Cruz, David Papineau and Pierre Cruz, takes this Carnap sentence to be devoid of cognitive content. The vindicatory approach takes it to be cognitively significant. In fact, Lewis did a lot of work on this, as is well known. The Carnap sentence is strengthened by the uniqueness of realization requirement. It now reads as follows: if anything uniquely satisfies the Ramsey sentence of the theory, than the entities posited by the theory do. And I call that the Lewis sentence because it's got this extra content of uniqueness. Okay? So the theoretical terms are fully defined. In fact, they can be explicitly defined and their reference is fixed. And that they can be explicitly defined, we've seen it already in a few talks using the idea of epsilon operator. So there is a clear difference here because the original Carnap sentence does not imply uniqueness of realization. Actually, Carnap was very clear on that. He wanted it to be so. It is fully consistent with the fact or the claim that there might be multiple realizers of the theory TC, even mathematical. Actually, Carnap presented it in such a way, okay, that it refers to mathematical entities. It turns out, and that's a big turns out. John and I have fought for years over this, but I'm with those who think that it does turn out, that the Ramsey sentence of the theory is bound to be multiply realized unless restrictions are imposed on the range of its second-order variables. Actually, it's even something stronger than that. Suppose the Ramsey sentence of a theory is empirically adequate. I'm not claiming, and I say that explicitly to be recorded, I'm not saying that the Ramsey sentence cannot be falsified. The Ramsey sentence has empirical content. It can turn out to be false empirically. I'm saying if it is not falsified, if it happens from a God's eye point of view to be empirically adequate, then subject to certain cardinality constraints, if it is empirically adequate, it is true. End of story. I mean, sorry, I'm with those guys who say end of story. In other words, there is at least one realization of it, and given plausible assumptions about the universe of discourse of the second-order variables, a multiplicity of them. The result, this result, it seems to me, has a straightforward bearing on both the eliminative and the vindicatory approaches. I think it simply undermines the eliminative approach. For it is not just the issue of reference that drops out of the window, the issue of realism goes out of the board too. Empirical adequacy collapses to truth. And not just that, there is simply no way to tell even what kind of things the second-order variables of the Ramsey sentence range over. So if you're an eliminativist, okay, say goodbye to realism too. It's plausible, maybe sensible, but let's come out and say that explicitly. When it comes to the vindicatory approach, things are somewhat more complicated. It is in the spirit of this approach that there should be ways to exclude various interpretations of the Ramsey sentence variables, aiming to constrain them, at least in principle, to just one. This might not be possible, but there might be hope that there are some external constraints. The way to do it is, as there is some parts missing here, but you know this debate very well, at least as well as I do, as Lewis emphasized in later work, after he published his paper on theoretical terms, is to impose causal constraints on the admissible interpretations of the language. That is, it is necessary to move away from a purely descriptivist account of reference fixing. Even if you go the Ramsey way, you need to add a causal claim, something like a causal external constraint on the admissible interpretation. There is now a way to eliminate many of the possible realizers of the Ramsey sentence. Only those that are eligible remain, where the eligibility of a realizer is a function of the eligibility of the classes over which the variables of the Ramsey sentence vary. And we can have different ways to think about what makes a class eligible, a natural kind, or whatever. So, conclusion. From a realist point of view, an important constraint on the theory of reference, if not the raison d'etre of a theory of reference, is the accommodation of linguistic practices to the causal structure of the world. Given that this accommodation is, as a matter of fact, a historical process, it is vital for a realist view of science that the theory of reference allows for convergence in the scientific image of the world. At least it's not inconsistent with the possibility of convergence. Theoretical terms are necessary for scientists to talk about posits not given in experience. but they should be taken to be trans-theoretical, to have actually trans-theoretical robustness. Unless continuity in theory change and convergence are established, past failures of scientific theories will act as defeaters of the view that current science is on the right track. The causal-descriptivist approach to the reference of theoretical terms is fit to strike a balance between, on the one hand, the theory dependence of theoretical terms, and on the other hand, viewing theoretical terms as relevantly trans-theoretical. This is reason enough to be worthy of development. Thank you.
I'm going to talk to you about a very interesting and famous case of existential prediction in contemporary physics. I'm talking about the prediction and then the discovery of the omega minus particle that is made by Gell-Mann and Niemann independently in 1962. And what is interesting in this, what is puzzling in this interesting prediction is the fact that they predicted not only the existence of this particle, but even the properties it would have had. And apparently the prediction was based only on considerations about the mathematical formalism. So there is a puzzling role for mathematical formalism here. And I will take in consideration some remarks by Sorin Bangu about this case, and he logically reconstructs the reasoning that led to the discovery of the omega minus particle in two distinct works. The first is a 2008 article, and then a recent book, in which he, after comparing the prediction with some other cases of existential prediction in science, he concludes that this prediction cannot be assimilated to these standard cases and that it is absolutely peculiar. And according to him, what makes this reasoning peculiar is the fact that it is based on a principle which he calls Reification principle. In a 2012 book, he changes the name, he calls it identification principle, but it is absolutely the same formulation. Anyway, this Reification principle is quite controversial, and we will see why. So my aim in this presentation consists in offering a different reconstruction of this reasoning without using the Reification principle. And for doing this, I will first introduce an account of the application of mathematics based on the notion of structure-preserving relation. So let me first give you a very short historical account of this prediction, of this discovery. It is generally based on the employment of group theory in particle physics due to the works of Weil and Wigner, and the particular group here involved is the special unitary group of degree 3. So in 1961, this was the situation. Only 4 spin 3/2 baryons were known: delta minus, delta 0, delta plus, and delta plus plus. And physicists had a theory that called the eightfold way that predicted that these 4 baryons could be either part of a decuplet scheme or of a family of 27 particles. A decuplet would form a triangle in the strangeness isospin plane, while the 27 particles would be arranged in a large hexagon, always in the strangeness isospin plane. In the same year, 3 new resonances, sigma star minus, sigma star 0, and sigma star plus, were discovered with strangeness -1 and probable spin 3/2, and they could fit well either into the decuplet scheme or the 27-member family. In 1962, 2 new resonances were reported, Xi star minus and Xi star 0, with strangeness -2 and electric charge -1 and 0. And they also fitted well into both our schemes. And finally, during the same year, Gerson and Shulamit-Goldhaber reported a failure in collisions of K plus or K0 with protons and neutrons. They did not find resonances, which would indeed be expected if the family had 27 members. So, of course, this failure pointed out that the solution lay in the decuplet scheme. I'm very sorry for the quality of the picture, but this is the decuplet scheme, the situation before the prediction. And you can see we have all the characteristics of the particle. We can spell out all the characteristics of the particle from this scheme. We have on this line, we have the charge, so delta minus, sigma star minus, xi star minus, and eventually this question mark will have a charge of -1. Then we have the isospin, the strangeness, and the average mass in mega electron volts. So, of course, when Gell-Mann and Niemann saw this scheme, they quite easily, we can think, they made the prediction, namely, instead of the question mark, there should be a new particle. They called it omega minus because it was the last spin tree half baryons to be found. And actually, okay, and of course we can also spell out the characteristics. So omega minus will have a charge of -1, isospin 0, and strangeness -3. And actually, 1 year later, in November 1963, a group of 33 physicists of Brookhaven laboratories were able to photograph the predicted particle, thus confirming its existence. And here we have, on the left side, the photo, and here we have a schematic representation of the tracks of the particles. And here you can see this short track is the track of the omega minus particle. It's very short because it decays very rapidly. So let's see Bangu's reconstruction. He points out some premises and the conclusion. So we have a first premise. Each of the upper 9 positions in the symmetry scheme has a physical interpretation. Then we have the hypothesis that spin tree half baryons actually fit the symmetry scheme. Then another premise that the apex is formally mathematically similar to the other 9 positions. Then another premise, the physical existence of a baryon having the predicted characteristics is not forbidden by nature, we can say. And here we have the reification principle. If gamma and gamma first are elements of the mathematical formalism describing a physical context, and gamma first is formally similar to gamma, then if gamma has a physical referent, gamma first has a physical referent as well. And so we can draw the conclusion that the apex position has a physical interpretation, has actually a physical referent, and the coordinates of this position describe a 10th spin tree half baryon, omega minus, of course. And we have a quotation from Bangu. This line of reasoning is supposed to answer the question asked by the experimentalist physicist ready to perform the detections, namely, what are the grounds to believe that A, there is an entity, and B, there is an entity having the predicted physical characteristics. Bangu compares this case of existential prediction with some apparently analogous cases. The Urban Le Verrier and John Adams prediction of the planet Neptune in 1846, and the Wolfgang Pauli's prediction of the neutrino in 1931. And both these cases of existential prediction can be considered as standard predictions according to the deductive nomological model. And because we have an anomaly and the prediction is made in order to explain away this anomaly. Well, can the same be said for the prediction of omega minus? Bangu says that similarly to the standard cases, the prediction of omega minus is made for explanatory reasons. There is an anomaly that must be explained away, and the anomaly here consists in the fact that if no 10 particles were found, then there would be an anomalous empty place in the decuplet scheme. Notwithstanding, there is an important difference between the standard predictions and the prediction of omega minus, because in the standard predictions, the characteristics of the predicted entity are based on the calculation of the parameters of its interactions with other elements of the system, while in the omega minus case, its characteristics are entirely spelled out from the formalism by means of RP. Now, I don't completely agree with Bangu on the first point about the anomaly, and for 3 reasons. The first is that I think this is not, I could say, an actual anomaly. The anomaly here consists in the fact that if no 10 particles were found, then there would be an anomalous, then there would be an anomaly. But this is, we could say, a potential anomaly. I mean, there is a first difference between this case and the cases, the case, for example, of the planet Neptune, where the anomaly was real, was actual. And moreover, I think, and I will try to show these later, that actually there are no anomaly. Even if no 10 particles were found, I think this is not an anomaly. And the third reason, I don't agree with Bangu on this point, is that it seems to me that we can see an anomaly here only if we previously assume the validity of the reification principle. So there is something like a vicious circle. So we see an anomaly only if we accept the reification principle that we use to explain away the anomaly. We can go on. Thus, what distinguishes the omega minus prediction from the other standard cases of existential prediction is the crucial employment of RP, according to Bangu. Anyway, Bangu himself admits that RP is quite problematic because it cannot be generalized, and moreover, there is no naturalistic explanation of why RP works. So it's quite problematic to accept RP. Bangu's conclusion is that neither the standard DN model accounts for the omega minus prediction, nor could a Pythagorean model be used as a substitute for it. A Pythagorean model is a model in which the reification principle is accepted as a real principle, as a real working principle. So this is Bangu's proposal to adopt a weaker approach that he calls mathematical opportunism, according to which the working scientist should not be inhibited by epistemological considerations. And here we have also a quotation. This kind of puzzle should not be allowed to interfere with the practice of science, as no attempt to offer a principled, systematic account, either standard or non-standard, of those episodes should be followed too far or taken too seriously. Well, I agree with the first part of this claim, namely that this kind of puzzle should not be allowed to interfere with the practice of science, but I don't completely agree with the second part of this claim, that no attempt should be no attempt should be offered for a systematic account of those episodes. So in order to avoid these difficulties, I'm going to present a different account of the applicability of mathematics, by means of which I hope to to show that it is possible to account for this kind of existential prediction without employing RP. So the basis is given by a structuralist account, namely we can summing up it as with this claim, the applicability of mathematics is accounted for by means of the notion of structure. Namely, when a mathematical theory is applied in empirical science, it is because the mathematical structure captures some relevant structural relations of the system at issue. In other words, applicability is possible under the condition that it is possible to set a structure-preserving relation between the physical system, let's call it S, at issue, and the mathematical structure, let's call it M. Here you can find some places where this structuralist account is, where you can find this structuralist account. I'm not saying that Shapiro or French or Pincock would agree with this specific formulation of the structuralist account, but I think this is the core idea, we can say, of this kind of account. So the first problem is what is a structure-preserving relation? The most obvious candidate is, of course, isomorphism. But here we have a problem because to impose an isomorphism condition is too much restrictive. And we can consider, for example, the case of the Navier-Stokes equation, where we have a set of equations and they work very well in describing the behavior of a fluid substance, but they seem to assume that the fundamental composition of the fluid substance is continuous, and we, at least according to our best theories, we know that this is not possible. Another possibility is homomorphism. So we say that M is a suitable representation of S if there exists a homomorphism, let's call it phi, from S to M, from the physical system to the mathematical structure. So when this condition is satisfied, we have that any relevant element and relation in S is represented by M. But this condition is too slack. It's not too tight because it doesn't exclude the trivial homomorphism. We can always have a homomorphism in which any element and relation in S is sent on the unitary element and the identity relation in M. So we would, in this case, we could have something like a Aleph. If you know Borges, you know what I'm saying. And so we want not only that any element and relation in S is represented by M, but also that it is univocally represented. So this means to ask that the structure-preserving relation is a monomorphism from S to M. So if monomorphism is the right condition, we can have a situation like this, in which M is richer than S. So sometimes we can try to shrink M to M first. Sometimes it is possible, sometimes it is not possible. For example, in the case of the previous mentioned Navier-Stokes equations, it seems we are not able to shrink our mathematical structure to a closer mathematical structure that could fit better with our empirical structure, with our physical system. So we can say that when we have a situation like this, M is redundant, but it is still suitable in representing S. So we can still working with M, and this is a good representation of the physical system anyway. in a situation like the previous one, it can happen that the mathematical structure predicts 2 or more possible solutions, and not all of them can be considered as valid in the physical system at issue. And this is a very stupid example. If we take, suppose we want to calculate where a projectile launched from the cliff of a hill will land. We set our mathematical structure that will consist substantially in the equation for a parabola, and we know that the positive solution, namely the points where the x-axis intersect the parabola, is our solution for this problem. But we have 2 solutions. In this case, one will be positive and the other one will be negative. So we know that we have to consider only the positive solutions. But what about the negative solution? We reject it just because we interpret the mathematical structure, and we know that the negative solution is a physically meaningless solution. But this poses a problem for the structuralist account, because the previous example shows that the simple fact that a possible mathematical solution has no physical interpretation does not necessarily invalidate the whole mathematical structure. So what can invalidate a mathematical structure as a suitable representation of a physical system is that a physical element or relation is not represented by the mathematical structure, namely that the monomorphic condition is infringed. So the structural account is not able by itself to tell us which of the possible choices is the right one or are the right ones, and which is not. So we need to integrate this structural account, and I think that in order to integrate this structural account, we have to take into consideration the process by means of which the mathematical terms are interpreted on the physical structure. Okay. And here is a very schematic representation of the account that I'm going to present. I don't have the time to describe it in all its details. So the idea is that the monomorphism relation is not between the so-called physical structure, which is not clear what it is, but it is between the data model and the theory model. Data model is probably a wrong term. I could maybe call it a raw model or a raw data model, and that this data model is linked to the phenomenon. Phenomenon is a very generic term, but that's why here we can have, for example, empirical observations or a previous previous theory, for example, so it's very generic. And the first step is a denotation. We denote terms within here by means of mathematical terms in order to build up a data model. So here we have something like a hidden mathematical structure. And this relation of monomorphism, if there is a monomorphism relation, we can be granted that we can work with the mathematical theory, drawing deductions and making demonstrations, and then we can go back to our empirical world by means of interpretation. So, but how this work concretely? How the interpretation works? The basis is given by the initial denotation, of course, and as far as the terms for which we have a denotation are concerned, the interpretation is simply the inverse of the denotation. But how can we extend this initial partial denotation? In extending this denotation, it seems to me that empirical verification is the only judge for interpretation, and so there are no type prescriptions to be rigorously followed. But we can try to make some suggestion. For example, we usually extend interpretation in conformity with a general principle of coherence. And of course, we will have to maintain a certain coherence also with our experience. So
Yeah, but we have like 2 minutes.
Okay. So the point is that the impossibility of finding an interpretation for a mathematical term or relation does not invalidate the whole mathematical structure. So let's suppose that gamma first, here I'm using the same terms used by Bangu in his reification principle, so we can make a comparison. Let's suppose that gamma first is a mathematical term deducted from the mathematical structure M, and suppose that we don't know how to interpret such a term. We have two possibilities. Either to hazard an interpretative guess for gamma first and then check its correctness, or if we have no idea concerning how such a term could be interpreted, we can say that gamma first is just a mathematical sign having no interpretation, depending on the fact that the structure-preserving relation is not an isomorphism, but a monomorphism. So this is a redundant mathematical structure. And if there is an interpreted gamma formally similar to gamma first, the suggested interpretation for gamma first will be analogous to the one for gamma. One might say that, okay, but the reification principle is still at work here. I don't think so, because it must be noted that gamma suggests only how to interpret a formally similar term gamma first, but it does not say that there must be an interpretation for gamma first too. So there's no need to employ RP. By the way, the reification principle talked about physical reference, while here we are talking only about interpretation. So this explains why the omega minus particle has been interpreted similarly to the other already known particles, but it does not explain why the experimentalist physicists were reason to believe that such a particle existed. So, well, we said that if the monomorphic condition is satisfied, then the mathematical structure is suitable in representing the physical system at issue, but here there is a problem. How can we know that the structure hidden in the data model is actually monomorphic to the mathematical structure of the theory model? It seems to me the only solution is to force this monomorphical condition and to suppose that the mathematical structure we want to adopt is actually isomorphic to the data model structure. If these hypotheses were true, so if we work with this hypothesis, we could be sure that any consequence in the mathematical structure has a correspondence in the data model structure, and hence that it represents a fact in the phenomenon. Thus, we can empirically check any consequence in M. If it is confirmed, then we can carry on with the isomorphism hypothesis. But if it is not confirmed, you can shuffle off the guilt of such a failure upon the isomorphism hypothesis. So, experimentalist physicists were reason to search the particle because they were reason to believe in the isomorphism hypothesis. They had no nothing is against to this isomorphism hypothesis. Okay, we can jump directly to the conclusions. So summing up, the discovery of the omega minus particle is not a standard case of existential prediction. This is right, but not because of RP, for it can be accounted for without using RP. So let's go back to Bangu's questions. Why experimentalist physicists were reason to search this new particle? Because they were reason to believe that the decuplet scheme satisfies the monomorphism condition, and nothing excluded that the isomorphism hypothesis was right. So they could work with the isomorphism hypothesis. And why experimentalist physicists were reason to believe that the new particle would have had the characteristics predicted by the formalism? Because it was, because it was the most coherent interpretation of the formalism itself. So this is the end. Sorry, I was a bit confused.
Okay, the title of my talk is Leibniz Equivalence. When I was first asked to talk, I felt a bit of a fraud because I was not going to talk about theoretical terms. I did originally think about talking about Ramsey sentences, but then I thought they will appear for one slide or maybe two slides, but I was more interested in talking about Leibniz equivalence and stuff to do with structure. But as it turns out, there's a huge overlap with what some other people have been saying. So what Georg was saying in his earlier talk, there's some fair bit of overlap with that. Anyway, so I should start. So Hannah's had 21 slides. I have 80. So I'll go quicker. Okay. So Leibniz equivalence, and that's me. That's the same thing again, and that's the abstract. So there are two topics. The first is about Leibniz equivalence of space-time. Well, actually, the first topic is just some explanation of the mathematics. The mathematics is not very complicated. It's just very basic, discrete mathematics. Very simple models. You have a model with some relations. You have mappings on the domain of the model, and those mappings lift to tuples from the model and functions and relations, and you apply those mappings and you get some stuff there. The second part after that is to discuss the notion of Leibniz equivalence of space-time models. So there's a principle in accepted by people who work in general relativity, physicists themselves, that diffeomorphically equivalent space-time models represent the same possible physical world. And that's something I've been interested in for years, and I've got some ideas about that. But it really turns out that the notion of diffeomorphism, which looks as if it's very special here, in fact actually kind of drops out. It's really just saying that isomorphic models represent the same physics. You can just see how that works. The next part after that this gradually starts with stuff that I'm confident about and gradually becomes more speculative and metaphysical. And the second part is to try and explain the notion of an abstract structure. And I'll explain an abstract structure as being something like a propositional function, a second-order propositional function. And then I try and explain what possible worlds are as the result of saturating a propositional function with a sequence of relations. And then the hope is that that automatically implements Leibniz equivalence. Okay, so that's the abstract. So here's the mathematics. You just need to know what a model is, what a mapping of the domain is, how to extend such a mapping. So here's my notation for a model. You have a calligraphic A, and you have the domain, and you have a sequence of relations and a sequence of functions. Okay, I just use that notation. Okay, that's the domain, carrier set, base set. Those are all used more or less synonymously. The vector R is a sequence of relations. Vector F is a sequence of functions in the model. So suppose you have pi as a permutation or bijection of the permutation of the domain, as a bijection of the domain to itself, and you have an n-tuple, and R is a relation, F is an n-ary function. Then you can, starting with the bijection, this bijection determines an action on these other entities. They're kind of in different types, if you like. But once you've got the mapping on the basic type, it lifts to all the other types, like functions between the types and operations on the types and relations on them. So on a tuple, the bijection just acts pointwise, and on a relation you just take the image of the relation, and on a function you just take the image of the function. If you have a sequence of relations, then you just take the result of applying the bijection to each. You just apply it pointwise or over and over again. That's what you do. Now, okay, so this is the idea, one of the ideas. So you have a model, and you have a permutation. Then I define this thing I call the Quine transform, because it really comes from the ideas that Quine is using in some of his arguments about referential inscrutability and indeterminacy of meaning. And these bijections are what he calls proxy functions in some of his writings. So given a model, what you do is you you consider a permutation of the domain to itself, and if you take the distinguished relations and functions, you just apply the operation to it, to all of them. Okay? And that's the Gauvain transform. Okay? So here's an example. So I like these little simple examples with a very simple domain and so on and so forth. They're very vivid illustrations. So here's the domain 0, 1, 2, and the distinguished relation is indicated there as well, and the structure is just that domain and that relation. So that's a little picture of it. Notice that this model has a categorical axiomatization. Okay. So this model, calligraphic A, you introduce a primitive binary symbol, P, and then you take the language with P as primitive, and then you express it like this. You assert the existence of 3 distinct entities. You assert that the domain consists of precisely those 3 entities, and then you write down this conjunction at the end, which is what model theorists call the elementary diagram. Okay, you write down the atomic sentences and they're the negations. Okay, you write down and those are the literals. Okay, you say that, and that's that category. So in fact, it's categorical. That means if any other model satisfies that formula, it's isomorphic to the original one, and that's kind of completeness. That if theta is true in the model, then it's actually a logical consequence of the axiomatization. Now here's an example of a bijection. You take the transposition that just swaps 0 and 1. The domain is 0, 1, 2. You take the transposition that swaps 0 and 1, keeps 2 fixed. So that's the new that's the image of the relation. What's happened is that 1 and 2 have just been swapped. Obviously, they're extensionally distinct, but they're clearly isomorphic. Okay. Because we have for any tuple in A2, you have the image of the tuple is an element of the image of the relation, even only if the original tuple is in the relation. That's just the ordinary isomorphism condition. In fact, that's what it looks like. You've just swapped 0 and 1, but it's still isomorphic, even though you've swapped the elements of the domain. So, in fact, you go through that, and then you can see that this is the result that you get. It's mathematically really trivial. If you have any bijection, then the Gauvain transform is isomorphic to the original one. It's just falls out of the definition. It's kind of really, any model is isomorphic to its Gauvain transform. This notion also allows you to express the notion of an automorphism. Automorphism of a structure or a model is a mapping that leaves the relations and functions actually invariant. It leaves them the same. So in the general case, when you apply pi to the relation, you get a new relation extensionally. But if the relation is invariant and the functions are invariant, then pi is an element of the automorphism group. So you can express the notion of an automorphism group. Pi is in the automorphism group when its Gauvain transform is the same as the original thing. Okay, now, so a little bit of philosophy. This is the famous review of Russell's analysis of matter by M.H.A. Newman from 1928. So it's a criticism of Russell's structuralist view of representation. All we could say is there is a relation R such that the structure of the external world with reference to R is A. Now, I have already pointed out that such a statement expresses only a trivial property of the world. Any collection of things can be organized so as to have the structure A, provided there are the right number of them. Hence, the doctrine that only structure is known involves the doctrine that nothing can be known that is not logically deducible from the mere fact of existence, except, theoretically, the number of constituting objects. So that's Newman's famous criticism of Russell. And here's the mathematical point. Suppose you have a set. Okay, a set is the thing that you're going to project onto. That's the world, the set. Okay. Suppose you have a model, and you have an injection from your model, the domain of your model, to the set. Well, you just define now those relations on the set, and then it just follows that that's the mapping that takes you. That injection actually is an embedding. So it's purely by construction, you've embedded the model into the set. Okay, you've projected. So consequently, given a model on a sufficiently large set, one can project the structure of this model onto the set. So the only condition that you need really here is this, that this is an injection. So the fact that it's an injection just imposes that B must be at least as large as A, okay, if that's going to be an injection. Okay. If we restrict it to a bijection, we get that between the domain and an arbitrary set, then you get that it's isomorphic. And if you map to the same set, but it's an arbitrary permutation, so it needn't be the identity, then you just get the Quine transform thing again. So the whole thing is basically, this is just the Quine transform lemma again. So the Quine transform lemma is simply a special case of Newman's projection lemma. So I'll go back to that's the basic point. That's the underlying thing that you use to prove things. It's very simple, mathematically speaking. There's nothing particularly deep about it. Why should these rather trivial, mathematically trivial notions from discrete maths be interesting for philosophers? Well, they are interesting because they pop up in various places. Leibniz shift arguments. This is the argument that Leibniz had, the idea that God, when I tell everybody to blink, you all blink. While we blink, God picks up the physical world and moves it along 1 meter. When we open our eyes again, there's no difference. So the movement, that everything is moved rigidly, so all these spatiotemporal relations, spatial relations amongst pieces of matter are the same. And perhaps that gives an argument that there's no such thing as space. There's no container that the physical world is in. That's the Leibniz shift arguments. That goes back to Leibniz and Clarke, who was a defender of Newton. We have this notion of Leibniz equivalence of space-time models related to the whole argument in debates within foundations of space-time theories and debates between substantivalists and relationists about space-time. We have ideas about permutation invariance of quantum states under permutations of indiscernible particles. I'm not quite sure exactly how this works precisely, because it's a bit complicated. You have symmetrization and anti-symmetrization. You have this Newman objection, which I'm going to come on to in a moment, and then you have permutation arguments in metasemantics. And in this talk, I'm going to examine the significance of 1, which is the Leibniz equivalence, but I'm going to briefly mention 3 and 4. So, Ramsey sentence structuralism. So this will actually tie in with what some other people have said. So this is just... okay, so Ramsey sentence structuralism, the synthetic content of a scientific theory is adequately captured by its Ramsey sentence. So the analytic content is, as Hannah's mentioned, given by what Poincareans call the excess content, which is the conditional of the Ramsey sentence and the theory. And the claim is that that's actually analytic. That's Carnap's claim. And in fact, as a realist, I would claim it isn't analytic, but even so. Newman's objection to this is sometimes related to the other debates listed above, but the connections have not been made so clear. And I just think the common mathematical content is Newman's projection lemma. That's the basic piece of mathematics. And this is some of the literature, Demopoulos and Friedman. Stathis has a formulation of this in his book on scientific realism and stuff. So here's the basic idea. You have a formalized scientific theory. It has to be finitely axiomatized. In fact, you can get around that. If you have an infinitely axiomatized or recursively axiomatizable theory, then actually you can finitely axiomatize that by special tricks. But you have a formalized scientific theory in an interpreted language. R theta is its Ramsey sentence. The projection lemma, if you go into the details, allows you to prove this. The Ramsey sentence is true if the theory has an empirically adequate model whose theoretical domain of its theoretical, the cardinality of its theoretical domain is the same as the original interpretation. Okay, so this is one formulation of this thing. So if the theoretical, if the synthetic content of a theory is its Ramsey sentence, then the truth condition of the theory is the same as its empirical adequacy condition. And this is the fundamental dividing line between realists and empiricists. When I discuss this with empiricists, they just don't get it. I said, this is the dividing line. This is it. You said, no, I don't get that. No, that's it. Empirical adequacy is not enough. Truth goes beyond empirical adequacy. So that's Ramsey sentence structuralism is constructive empiricism. That's a theorem. It's not an opinion. You can debate the formulation of Ramsey sentence structuralism, but once you've got the precise definitions of empirical adequacy, constructive empiricism, you can just prove using mathematical reasoning that one is equivalent to the other. And the only really plausible way of blocking this is to change the semantics of the second-order quantifiers, which is why I mentioned in the case in Holger's talk, Holger's Ramsification had, the informal Ramsification had, there are natural functions, and that's one way of blocking this, because although this will follow if your second order, if your semantics is full, because you've got so many relations and functions to play with, if you've only got natural relations, you can't play around with those. This is a kind of gerrymandering argument, and if you can't play around with those, you can't get them. Okay. So, but to do that, you then have to say what these natural things are, and that brings you into metaphysics, and I don't think you can avoid it. Okay, there's another line of argument one can give in relation to the Newman objection. That's based on this idea of glubby nominalism. The mind-independent world is a kind of structureless, amorphous glub. You get a Newman-style objection as well here. I mean, whether people actually believe this is a separate question. I think I do know some people who actually do believe this. So suppose that representation is defined as follows. So when people who advocate the model theoretic view of theories, or the idea that theories are collections of models, I always ask them what represents means. What does represent mean? When you say you have a mathematical structure or model, you say it represents the world, but what does that mean? If it means represents the world even only if there are relations, so this is a Ramsification here, there are relations on the set of things in the world such that the model is isomorphic to these, and you make no assumptions about which ones are natural, then you end up with, you can place any structure on the world at all, anything you like. The world is anything you like, a Boolean algebra, it's a ring, it's a module, it's anything you like. So this is the formal version of it. So suppose you have a model and kappa is the cardinality of the domain, then A represents the world even only if the cardinality of the world is at least kappa. So actually, about 10 years ago, I did write a manuscript about this called Physics Without Physics, but discussing it with Roy Cook, he said that, he put it like this: physics has been reduced to counting. There's nothing more to physics except counting, which is, okay, so these are trivialization results. And I'm going to say here at the end, so that's the Ramsey sentence, that's the glub lemma. These are mathematical theorems, they're not opinions. So you really can't have your cake and eat it. There are a lot of people who want to have their cake and eat it. You cannot have your cake and eat it. At least if you try and have your cake, I'm going to take it off you and say you can't eat it as well. I'm going to put it on the mantelpiece and not let you eat it. If you want to eat it, I can't let you have it as well. So if you want to have science and mathematics, you're stuck with a certain level of metaphysical guilt. Metaphysical guilt is unavoidable. Okay, so permutation arguments. I'm not going to go over the permutation arguments because I don't really have a great deal of time. But they're the same kind of argument. You can just permute the language and you get issues about determinacy of reference. I'm not going to go through that. Okay, so that's, okay, so on to Leibniz equivalence. So Einstein's theory of general relativity, possible physical worlds are represented by space-time models. And I'm going to go a little bit through what manifolds are. Manifolds are not just point sets, they're point sets with additional topological structure on them. So what is a topological space? Well, unfortunately, manifolds are never really presented as topological spaces. They're always presented parasitically via the topology of Rn. So you don't define what a manifold is topologically. You define, first of all, you say what Rn is as a manifold. As a topological space, what its topology is, and then you explain what a manifold is parasitically by saying that a manifold is something that is locally like Rn. So a topological space is a pair consisting of a base set and a set of subsets of the base set satisfying certain conditions. So the conditions are that the elements of this collection of subsets of X are called open sets, and it has to contain the empty set, it has to contain the whole set, and it satisfies certain closure conditions. It has to be closed under intersections, countable unions. And the elements of the topology are then called open sets. So it's easy to define topologies given a set. You can take a set, say 0, 1, 2. A topology will be a set of subsets containing the empty set, the whole set, and some other sets, so long as they're closed under these two conditions. Okay, a manifold is not, however, defined in terms of a base set and a topology, but rather a base set and a system of charts, what's called an atlas of charts. So you have a base set X and what's called an atlas of charts. Don't worry about what complete means. An N chart is a function, an N chart is on a set. The set can be anything. It could be a set of eggs or something. It wouldn't work for eggs because you don't get the continuity, but if you had sufficiently many eggs, it would happen. So it's a function from a subset of X to an open set in Rn. Okay. So what are the open sets in Rn? You have to take the standard topology in Rn, and that's defined by taking unions of balls in Rn, which are spheres around a point. And those are the open sets. And that's what an N chart is. An atlas is a collection of N charts which satisfy, they may overlap. So that's the function phi, and that's the domain of the function, and that's the image, the open set in Rn. And this is the collection of N charts. If you take the union of their domains, that has to be the whole space X, the whole point set, and they satisfy certain overlap conditions that I'm not going to go into. And intuitively, what that does is sets up the idea that a manifold is a topological space with topological structure that is locally the same as that of Rn. So you can't, in general, do the whole thing with a single chart. That's the point. So it's locally like Rn, but it may not globally be like Rn. So the two-sphere, for example, is locally like R2, but you actually need at least two charts. You can't cover the whole of the two-dimensional sphere with a single coordinate chart. So in sum, that's a manifold. This collection of charts is a kind of distinguished structure, but it's not really in the standard form of a first-order model. It's a kind of second-order structure. In fact, it's kind of many-sorted, really. It's got a hidden field built inside of the real numbers, and it's okay. But it corresponds roughly to the topology, a collection of subsets of the power set. Sorry, a collection of subsets of the base set. Okay, so now I'm going to define what I mean by a diffeomorphism. Suppose you have a manifold and you have a bijection between the base set of the manifold and some other set Y. Suppose you have a coordinate chart in the atlas. You can compose the coordinate chart with your bijection, actually with the inverse of the bijection, which will now give you a function from the set Y to Rm, and it turns out that if you start with a bijection and an N chart, then the composition is also an N chart. You have to check various conditions, but it turns out that's also a chart. And in fact, if you have a bijection and you start with a manifold XC, then if you take all of these composed charts, that gives you a new atlas. And in fact, that turns out to be a manifold. We say that if you have two manifolds, XC and YC prime, they're manifolds. We say they're diffeomorphic if there's a bijection taking you from one base set to the other base set, such that the image of the original atlas is the new atlas. It's the same atlas. It's a kind of isomorphism condition. And then we say that it's an automorphism if you have a bijection of the base set to itself, which leaves the atlas invariant. Okay. So the charts may change, but the atlas itself is invariant. General relativity describes nature using space-time models, which look like this. You have a base manifold, and then you have these extra things up here, which are tensors on the manifold. This G is a special tensor called the metric tensor, which determines locally distances in space-time. And these capital T's are usually called, they're tensor fields, but they're called the matter fields. Tensors are kind of generalizations of vectors. Tensors are like little n by n matrices at each point in space. Whereas a vector is like a little column vector at each point in space. It's like a little pointing in a certain direction. You might wonder what the space is. Well, it's usually the tangent space. Every manifold has, an n-dimensional manifold has a tangent space at each point, and that tangent space is just Rn. And that's the reason why, if you know this trick about why space is three-dimensional, everybody who's done a maths degree knows this. So you can point your fingers like this. So if you start with one, you can make another one at right angles to it, and then you can make another one at right angles to both. But you can't stick a pencil or something at right angles to all three. Okay? So this is a basis for the three-dimensional tangent space, basically. But it's not four-dimensional. That's the reason you can't do it. It would be linearly dependent on one of the other three if you try to do that. Now, it turns out that once you've got G of the tensor fields, you can do all kinds of other stuff. You can differentiate them and all kinds of other stuff. And you get these, you get these other tensors, the Ricci tensor and the Ricci scalar, and you can combine the tensor fields to get what's called the energy momentum tensor. You put them all together and you get an equation, Einstein's field equations, which are, for completeness, that. But I don't care about that, because we're just talking about what representation means. So what the models have to satisfy to be physical is irrelevant. So the physicist, implicitly or not, makes use of this notion, space-time model represents a possible world. If you have the condition that what they represent are unique, then you can express the idea of being physically equivalent. So S1 is physically equivalent to S2 if they represent the same world. I can now formulate Leibniz equivalence. This is how it's formulated. There are two formulations by Norton. This is from the Stanford Encyclopedia entry written by Norton. If two distributions of fields are related by smooth transformation has to be, that's a diffeomorphism, then they represent the same physical systems. For any space-time model M, and he writes the geometric objects as O1 up to On, but they're the tensors. And any diffeomorphism, then Leibniz equivalence asserts that any two models like this represent the same physical system. Okay. The main thing to note is that in such formulations of Leibniz equivalence, these transformations are required to be diffeomorphisms. So his formulation is essentially this. If you have a space-time model and you have a diffeomorphism, then the Quine transform, which is really what's being applied here, is physically equivalent to the original. I call that the single model diffeomorphism formulation. But in fact, I'm going to say it doesn't need to be a diffeomorphism, actually. In fact, it can be any permutation of the base set. And I gave this talk in Oxford to the philosophers of physics about 3 or 4 months ago, and I think I got a majority agreed with me, but a couple of people said, no, that can't be right. You can take any permutation of space-time points. Simon Saunders was just baffled that I was saying this. But it's clearly what the intention is in formulations, standard formulations. Let me go through the argument. So in many formulations, it's required that it be a diffeomorphism, but in fact, it doesn't need to be a diffeomorphism. So I'm going to argue that it's not necessary, and I'll argue by authority. I'll use the standard textbook, which is by R.M. Wald. He says that if phi from M to N is a diffeomorphism, then M and N have identical manifold structure. If a theory describes nature in terms of a space-time manifold and tensor fields Ti's defined on the manifold, then if phi from M to N is a diffeomorphism, the solutions phi Ti and phi and N phi star Ti, that's just the action of the mapping on the tensor fields, have physically identical properties. I'm not going to read the rest of it, but this is his formulation. So it writes out one direction. This is Wald's formulation. So let H from M to N prime be a diffeomorphism such that the image metric is equal to the metric built into this is equal to the image under the mapping of the original metric. Then the two space-time models are physically equivalent. So it does look like he's appealing to diffeomorphism. But in fact, that's because he hasn't broken this down into an underlying base set and a chart. But in fact, the underlying base set and the chart can in fact be different. And if you rewrite it like this, is that a mapping from M to M prime be a diffeomorphism is equivalent to saying that you have a bijection from the base sets satisfying the chart condition. And if you go through it, World's formulation is equivalent to this. If there's a bijection from the base sets which maps one chart to the other and maps one metric to the other, then they're physically equivalent. So in actual fact, all that says is that if the space-time models, if you now make the charts, the topological structure explicit, all you need is that they're isomorphic, because these subparts are actually automatically diffeomorphic. Then if they're isomorphic, then they're physically equivalent. So Leibniz equivalence just comes down to this. There's nothing to do with diffeomorphisms. All that is a bit of a red herring. Isomorphic models represent the same world in symbols like that. And of course, extensionally distinct models can be isomorphic, but that's it. Now, I've got a few more comments here, but I'm just going to go over them. If we weren't dealing with manifolds, but splogifolds, the relevant notion actually for automorphisms of a splogifold to itself would be a splogimorphism. But in a way, it's irrelevant. Leibniz equivalence just requires that isomorphic representations represent the same physical world. Okay, I'm not going to read through this because it's basically making the same point. So what is the significance of Leibniz equivalence? Is Leibniz equivalence a substantive metaphysical claim about modality? That is it a genuine substantive modal fact that things couldn't have been isomorphically different? In metaphysics, this is connected to hexietism. For a particular thing, the hexiety of A is the property of being that particular thing, and these are non-qualitative properties. Hexietism is the claim that swapping all the qualitative properties of two objects, one obtains a genuine new possibility. And anti-hexietism denies that. Leibniz equivalence is essentially a form of anti-hexietism. Now, how do we make this more precise? What the possible worlds are that automatically implement Leibniz equivalence? In some very difficult, hard to articulate sense, the identities of the points of the base set have no significance at all. Only the structural patterns imposed on the base set have significance. So we're going to change focus and now focus on the notion of abstract structure. I'm going to try and explain the notion of abstract structure in terms of propositional function. And that's going to lead to some interesting metaphysics. Now, mathematical structuralism comes in two kinds, eliminative and anti-rem. Eliminative associated with Hellman, anti-rem with Shapiro. Eliminative structuralism says, for example, in the case of arithmetic, there's at least one omega sequence and an arithmetic sentence. This is Goldbach's conjecture. Every even number greater than 2 is the sum of 2 primes. Nobody knows if that's true or false. In some sense, they're about all omega sequences. It's eliminative because there's no commitment to a unique special structure or omega sequence that arithmetic is about. It's about all omega sequences modulo the assumption that there is at least one. Anti-Ram structuralism associated with Shapiro, arithmetic is about a special omega sequence, the natural numbers n. And the natural numbers are nodes or positions in this structure, but it's very mysterious what these nodes are. So in the account I want to develop below, the nodes are going to correspond to existentially bound first-order variables. Okay? And individuals in a possible world will correspond to Skolem constants. Okay, so I keep telling people that you are Skolem constants. That's really what you are. Okay, there's a view, and this is you can relate this stuff to. There's a view in the philosophy of science called scientific structuralism, or sometimes ontic structuralism, associated with Lederman and Ross. The problem, as I've always seen, and it's sometimes the idea is to eliminate relata, and this is what people have always said. This doesn't make any sense. How can you have a relation without relata? It doesn't seem to make any sense. And that seems to be the problem. So a model in the ordinary mathematical sense is something like this. You have a domain, A, and then you have a sequence of relations. The relations are built up, tuples and stuff, from the domain. But that's not structuralism in the required domainless sense. So scientific structuralism and mathematical structuralism face a similar problem to articulate a notion of abstract structure more general than that of a model. So the intuitive notion is that all isomorphic copies of some particular model have the same abstract structure. So what we want to do is identify something as the abstract structure of a given model, or somehow getting rid of the specific domain. And I know of 3 approaches. So one is what I call the Skolemization approach of Richard Pettigrew, but other people have come up with similar ideas. But this was discussed by Georg earlier. There's the isomorphism type approach, which identifies the abstract structure with the isomorphism type. And then there's the propositional function approach, which is the one that I'm going to defend. Okay, so the scholomization approach is this. As soon as one's proved that there is, say, at least one omega sequence, like Dedekind did in his famous Theorem 66 by a thought and a thought about a thought and a thought about a thought, you get an omega sequence. You can introduce a Skolem constant for that, say n, and from now on we use that constant. If you're an eliminative structuralist, that's quite attractive. It's kind of quasi-linguistic. The isomorphism type approach is the abstract structure is its isomorphism type, the equivalence class of the model under the isomorphism relation. But I think that both approaches are unattractive for the modal purposes that I'm interested in. So I want to connect a theory of abstract structure with a theory of modality. I'm going to skip through this because this is Lewis's mereological view. So the intuitive notion is that all isomorphic copies of a particular model have the same abstract structure. So you end up with this Leibniz abstraction principle that the abstract structure of A and B are identical, even only if they're isomorphic models. So one wants to think of the abstract graph associated with all isomorphic copies of some given graph. But the definition of a graph is a vertex set and an edge relation. So you have a particular vertex set. So here's an example. That's the vertex set, and that's the edge relation, that's the graph. And you can picture it like that. And if you look on the net, or in textbooks, you'll see this kind of explanation of what a graph is. And then you'll also see an explanation of what an abstract graph is, because people like to explain what an abstract graph is, and they just remove the labels. And they say that's the abstract graph, but I mean, everybody understands that intuitively, but nobody understands what it is. So we're somehow left with just 3 nodes, but we've removed the labels. Are they labels? Or have we removed the domain? How did we remove the domain? If we remove the domain, we must have removed the relation, because the relation is built up from the domain. So how can we remove the label? What have we removed? It doesn't make any sense. So what is that, mathematically speaking? So somehow the circles represent the nodes. Okay, I'm just repeating here what I said a moment ago. What is the domain of the abstract graph? Okay, there's a result in the model theory of infinitary languages, which says that given a specific model, A, there's an possibly infinitely long sentence in the infinitary language. This specifies the numbers of kappa and lambda, or the numbers of Boolean conjunctions and disjunctions you're allowed, and lambda specifies the number of existential and universal quantifiers you're allowed in variables. You can actually uniquely categorically axiomatise that model in such a language. So I'm going to show you how to do it. So you consider a language which has a constant for each element of the model. And for simplicity, suppose that it's purely relational. And we let the PIs denote the relations and the CAs denote the elements. Then you just take what is essentially delta sub A is the conjunction of the elementary diagram. It's all the literals that are true in the model. And then you need a top thing that says that the domain consists of one of the constants. And then you just take the conjunction of those 2 things. And then that formula categorically axiomatizes the structure. Now, okay, so here's an example. You have 0, 1 as your domain, and the relation is 0, 0, 0, 1. That's the formula. That categorically axiomatizes it. Okay, 0 is not 1. P holds of 0, 0, 0, 1, does not hold of 1, 0, does not hold of 1, 1. Everything is either 0 or 1. But, and this tells you everything you need to know, but this formula's got the domain built into it, so I need to get rid of the domain now. So I get rid of the domain by first order Ramsifying it. So I'm just going to quantify 0 and 1 with new variables. Okay? So this is the general way to do it. You have an enumeration of all the constants. You have an enumeration of variables of the same length. You then do this horrible infinitary substitution. Okay, you substitute constant c is replaced by constant y. Well, each constant is replaced by a corresponding variable, and then you existentially quantify with a possibly infinitely long quantifier. That's my formula phi, and that gives you a formula that categorically axiomatizes the structure that you started with. So here's the, there we are, we've now existentially quantified it there, and you get the formula. That defines the model up to isomorphism. It defines the isomorphic type, but it's a syntactic entity. In order for this to work, you have to keep identity as a primitive. Okay, so but it's syntactic now, and you could, of course, change the syntax in various ways, which you want to get rid of. You want to quotient away from those. So what I suggest is that you take the propositional content. So that's the formula that you start with for the axiomatization of this model, where P denotes the given relation R. You replace P with a second-order variable like that, and you now think of this as expressing a second-order propositional function, that's the formula. Its propositional content is the proposition that there are exactly two things, such that one of them bears x to itself and to the other, but the other does not bear x to itself or the other. And the proposition is indeed true of the relation. Okay, so this suggests a way of construing abstract structures as second-order propositional functions. So what we say is that the abstract structure is the propositional function that formula expresses. So the abstract structure of our model A is the unique propositional function phi sub A, such that for any given argument relation, we have phi A applied to R is the proposition that there are exactly two things, such that one of them bears R to itself and to the other, but the other does not bear R to itself or the other. You don't want to use Russellian structured complex as your propositions here, because Russellian structured complexes are built up from objects like Mount Blanc and so on, if you remember the debate between Frege and Russell. These propositions are saturated senses. They're Fregean propositions. They're Gessättigt senses. So here's the definition now in the end. So phi A is the propositional function expressed by this formula, and that's our proposal. The abstract structure of our model is this propositional function, and that's the construction. Now, I think that this works in giving you the Leibniz abstraction principle. This approach seems to yield the required abstraction principle. I write seems because there are three possibly quite significant problems. One is the problem of identity conditions for propositional functions. I haven't said when they're the same. Okay, they apply to arguments. Maybe they're the same when they give the same outputs for the same inputs for the arguments. I'm not sure. How do we understand these relations which are going to saturate the propositional functions? They somehow have to be understood as primitive intentional relations, like Platonic universals. And there might be a Russell paradox problem lurking here as well, just as there is in the isomorphism type approach. Okay, let me talk about the Skolem business. So take this graph here, which is categorical axiomatization, is this thing. So you've got 0 related to 1, and I quantify away the constants, and this expresses the edge relation, the x, but it's now second-order variable. And it's categorical in this sense. If any model satisfies this formula, then it's isomorphic to the given one. So it expresses the propositional function. And I claim that, that this is the abstract structure of the graph. Given the formula, we can Skolemize it. So when we Skolemize it, we take the existentially bound variables and we introduce constants, one by one for each of them. So we will get A, B, C, like this, and they're pairwise distinct. We'll get the diagram of them, and we will also get the universal claim that everything is one of A, B, and C. And it breaks into three formulas like that, and we picture this, we get that. That's it. Right, so the labels actually are labels. They're Skolem constants. That's what the labels are on these diagrams. The labels are Skolem constants. So an unlabeled graph is the abstract graph, understood as the second-order propositional function, and a labeled graph is a Skolemized description of the abstract graph. Notice that the Skolemization is completely arbitrary. You could use any constants you liked when you Skolemized the description. So the labeled graph is quasi-linguistic, in a sense. It's got some linguistic, and that seems to be applicable quite generally. Okay, this is the notion of abstract cardinality structures. You can just apply these notions to have the idea of a pure cardinality structure. Shapiro talks about these structures and mentions his children exemplifying these pure cardinality structures. So this pure cardinality structure is the proposition that there are exactly three things in A. So it's basically this propositional function. You can apply it to, okay, next, finally, modality. How much time do I have now? Do I need to stop very soon?
You have a couple of minutes.
Couple of minutes. Okay. So now I want to, this is where things get really speculative and metaphysical. So this is a quote from Frank Artzinius's recent book called Space, Time and Stuff, I think it's called, discussing Leibniz equivalence and Leibniz shift arguments. The Leibniz shift argument is just not a good argument, for if it were, it would tell against electrons, indeed against all objects. Now, some might be willing to bite this bullet. Well, I would like to see how one then proposes to conceptualize the world instead. The bullet is this some kind of elimination of objects in general, not just space-time points, but everything. My guess is that the best one can do is to use a quantificational logic stripped of constants, and this hardly strikes me as denying the existence of objects. He mentions work by Ted Sider and Dasgupta. The more important point is that this no longer has anything to do with substantivalism versus relationism. It's just a view about the existence of objects in general, and I agree with that. I do think this issue of Leibniz equivalence actually generalizes very broadly if one takes it seriously. So the intuitive idea is that a possible world is the result of applying an abstract structure to a sequence of relations, the result being a categorical first-order Ramsified proposition. So that's my definition of what a possible world is. Okay, a possible world is the result of taking some propositional function of this kind, categorical second-order, first-order Ramsified, and then applying it to some sequence of relations. And then you can define what it means for a model to represent a world relative to those relations. Well, that's the definition. Now, relations amongst concrete entities are not reducible to sets of the concrete entities anymore. In a way, that doesn't really make sense. The relations have to be understood as unreduced primitive intensional entities somehow, which can saturate the propositional functions. So consider a world in which there are just three distinct concrete things. You might think this is complete nonsense, but a world in which there are just three, all there is to this world is there are three distinct things. That's the world. Well, that's the description of the world. There is Y0, Y1, Y2, they're distinct. They're all concrete. I'm using C as a abbreviation of the interpreted concept, concrete. And everything in that world is one of them. So that's the proposition that there are exactly three concrete things. And in fact, for each cardinality kappa, we have a possible world which is the proposition that there are exactly kappa many distinct concrete entities. The concrete entities in them have no internally or externally distinguishing features, except pure brute difference. There's no way of labeling them or anything like that. Or you can by Skolomization, but that's arbitrary. Here's something that's a bit more interesting. It's a space-time world with just 6 points. So there are exactly 6 concrete space-time points, P1 up to P6. The betweenness relation has this extension. I should really have written this in as atomic formulas, but I've written it like this because it's easier to write. And the before temporal relation, before it has this extension, and everything is one of these points, where bet is the betweenness relation and before is the beforeness relation. So on our current approach, this is that possible world. So if somebody says, consider this possible world in which there are exactly six space-time points with these relations, on a Lewisian view, this world consists of the 6 points as a kind of mereological aggregate. On my view, the world is propositional. It's the propositional claim. It isn't built up from the points themselves. In a sense, the points don't really exist. So here's another example. This is a quote again from Artzinius. Consider a world containing only 3 material objects, 3 electrons A, B, and C. Suppose that A is 3 feet from B, B's 4 feet from C, and C is 5 feet from A. Now imagine switching these electrons around so that B is 3 feet from C, and C is 4 feet from A, and A is 5 feet from C. Okay, so here's my categorical sentence expressing that world. But I've now quantified it. So that's got no labeling in it. And it says there are exactly 3 electrons, everything is one of those 3 electrons, and here are the distance relations. I can then Skolomize it like that, which is the way that Artzinius recommends. but then I can apply a permutation to the Skolem terms and Skolemize it like that. But they're just distinct Skolemizations of the same possible world, and that's why they're the same world, because they're distinct Skolemizations of the same world. So on this approach, we're not swapping the inhabitants of a world, we're just swapping names in a Skolemized description. Okay, so there's a little bit more. Oh, this is when I finally try and apply this to space-time models. But for space-time models, I need an infinitary quantifier prefix saying that there are exactly 2 to the Aleph-0 distinct entities, P1, P2, P3, through all the points of the space-time model. And then at each point, I have to state what its metric and topological properties are. I know that sounds crazy, but it's really long, 5 minutes. Taking this proposition to be the possible world represented by S, we've now eliminated any need for a distinguished domain as such. We don't have a domain of space-time points. It's the possible world is a proposition. We just have very, very long sequences of quantified variables. And of course, the categoricity of this proposition ensures that if S prime is another space-time model isomorphic to it, then it represents this world as well. Okay, so now finally, this is the most metaphysical bit. If you make this identification of abstract structures with second-order propositional functions and possible worlds with the saturation of those functions with relations, you get anti-hexietism just comes out because of the quantification. Now, in fact, you could put hexieties back in by introducing hexiety properties as primitive things. So there are these extra Mundell entities which have hexiety properties, the property of being God, the property of being the Archangel Gabriel. And you could put these properties back into the worlds by saturating them, the worlds with those properties, if you want. You don't have to, but you can put hexieties back in by having hexiety properties. But in any case, anti-hexietism is essentially built into this. The individuals in a possible world or an abstract structure are thin. So this is, I sometimes joke with people who are anti-Platonists, who believe in concrete things but don't believe in abstract things. And I say I'm more inclined to disbelieve in concrete things than abstract things. So this is a sense in which concrete things are thin. They correspond to bound first-order variables. And that's really what structuralists, I think, mean by nodes or positions in a structure. The introduction of new constants by Skolemization of the syntactic description of a world yields what seem to be sort of thick individuals. You can now take the domain of those things, like a kind of Henkin construction. If you know Henkin's completeness theorem, you have constants witnessing all the existential claims, and the domain is then built of the constants. And in fact, ideas along these lines are developed by Das Köpter in a paper in 2009. And finally, there are a number of different ways of explaining the distinction between the concrete and the abstract. And I think the right way to analyze the distinction is modal. Intuitively, concrete entities, such as me and Norbert, we change our relations mutually through time and possibly modally as well. And that's why we're concrete. But abstract entities don't change their relations mutually. So 2 doesn't change its relation to 4 as you go across possible worlds. So in a sense, abstract entities are kind of modally invariant in their interrelations. But concrete entities keep changing their properties relative to each other. So in a sense, pure abstract entities are genuinely thick, preserving their identity modally, and I'll stop there.
And this is implicitly defined mathematical terms. According to a traditional account that connects implicit definitions with a priori truth, an implicit definition is a stipulation of a sentence that contains the definientum as true. On this account, we take a sentence or a range of sentences that contains an unexplained expression and other previously understood expressions, and we stipulate that sentence or those sentences as true. The definientum is to have the meaning it needs to have for the sentence in question to express a truth. So, if such an appropriate meaning for the term f is available, then the outcome of stipulation is that we acquire an a priori true proposition. Horowitz has showed off some serious difficulties, however. When we assume that the term f should have the meaning it needs to have for the sentence in question to express a true proposition, we presuppose that, first, there is a meaning such that if the term has that meaning, then our sentence becomes true, and second, there is at most one such meaning. Those points made by Horowitz set the discussion of the existence problem and the uniqueness problem respectively. Hence, if the appropriate meaning is available, then stipulation gives a true proposition. But there may be no such meaning for the term f, or there may be more than one such meanings. So Horowitz believes that we have to reject the traditional account of stipulation and that it would be more precise and better to say that the meaning is accrued to the definiendum f so that the sentence in question is held to be true or it is merely accepted. This suggestion aims to provide a solution, especially for a difficulty that emerges in case of scientific terms like phlogiston, ether, etc. Such terms had occurred in scientific theories that eventually were falsified and abandoned. This fact raised questions concerning the very issue of the truth of the sentence that bears the implicit definition of the term, for example, phlogiston. Horowitz offered a proposal according to which a meaning is accurate to a term means that a certain pattern of use is established for that term. According to Horowitz, we need a use-theoretic account of meaning, according to which a regularity is established by the postulate that concerns the use of the term in question. However, there is a critique from Hale and Wright to that account of Horowitz. They have objected that no therapy of the problem is achieved in this way. I agree with them that Horowitz's proposal does not solve the problem he has raised, but rather it bysteps it. Horowitz speaks about stipulation in terms of a sentence that is accepted as true, so that it constitutes a meaning, instead of speaking about the meaning that is required in order that the sentence in question expresses a truth. So, the questions that this paper deals with are, first, whether the existence problem pointed out by Horowitz with regard to definitions of scientific terms emerges also in case of systems of axioms and abstraction principles in case of mathematics. Second, whether axiomatic systems and abstraction principles are purely stipulative. Third, what form should mathematical implicit definition have in order to be purely stipulative, in the sense that the outcome of the implicit definition is truth by mere stipulation. The recent philosophical discussion concerns implicit definitions of various kinds, especially postulates of scientific terms and mathematical implicit definitions, that is, systems of axioms and abstraction principles. A system of axioms is regarded as an implicit definition of certain mathematical terms which obtain their meanings collectively on the basis of mutual relations that they are taken to satisfy by a series of postulates. This idea of treating systems of axioms as implicitly defining certain mathematical terms comes from Hilbert. For example, the system of Euclidean axioms define collectively the geometrical terms point, line, and plane by laying down mutual relations that points, lines, and planes should satisfy. The other case of implicit definition is abstraction principles. Although Frege did not like implicit definitions at all, and he was in disagreement with Hilbert about this issue, the Fregean abstraction principles have been construed and have been studied as a kind of implicit definition the last decade in the context of the Neo-Fregean program. I think that Horowitz's worries have been discussed mainly with regard to definitions of scientific terms, not so much of mathematical ones. A postulate of a theoretical scientific term like phlogiston may turn out to be false since there is no phlogiston in the world. So the proposition that stipulation expresses may be falsified for empirical reasons. So the world seems to set restriction on the range of available meanings. Yet, in case of mathematical implicit definitions, the stipulations in question do not give empirically falsifiable propositions. So, mathematical implicit definitions are expected to work successfully by giving true propositions. The paper, however, argues that an analogous with Horowitz's existence problem emerges in case of mathematical implicit definitions concerning the availability of appropriate meanings for the definienda, so that the vehicles of those kinds of definitions express true propositions. The a priori status of mathematical definitions is not at stake. I do not doubt the a priori status of mathematical postulates. But what I think is at stake is the purely stipulative status of mathematical implicit definitions. So, though not empirically falsifiable, the alleged mathematical stipulations suffer by a difficulty similar to that pointed out by Horowitz. This difficulty does not concern their a priori status, but the truth of the propositions that arise from the process of stipulation should hold just in virtue of stipulation. However, that truth is not just by mere stipulation, but, as we will see, depends on independent of us semantic or metaphysical facts. Consider the case of Euclidean axioms. The system defines more than one term simultaneously. The system lays down certain relations that the definienda, point, line, and plane must satisfy. Horowitz's worry can arise in this case too. According to the traditional view which Horowitz has criticized, we stipulate a range of sentences as true. The definienda should acquire the meanings they need to have so that the postulates become true. But what does guarantee that appropriate meanings for the terms FGH are available so that the propositions that are expressed by the system of axioms are true? Of course, the main difference between a mathematical system of axioms and a postulate of a scientific term like electron or phlogiston is that an empirical disconfirmation is not expected in the mathematical case. However, the alleged truth that we believe to hold just in virtue of stipulation proves to depend on certain independent of us semantic and further metaphysical facts. If only the very requirement of satisfiability is fulfilled, possible meanings are available for the definienda so that the postulates are true. Hence, the appropriate meanings are available only with regard to the models of the system, not with regard to other interpretations of it that are not models. Consider the case of an abstraction principle. An abstraction principle is taken to define implicitly an operator S and through it the terms SF and SG that are formed by that operator. So suppose F and G are terms of a language which is already in use, and this one is a relation predicate that expresses an equivalence relation among F and G. The already familiar language is extended by an operator S that applies to the already known expressions F and G and produces new terms SF and SG. The biconditional settles truth conditions for the identity context, which is on the left-hand side of the abstraction principle. An abstraction principle accrues meanings to the operator S and through it to the newly formed terms SF and SG. The biconditional of such a principle is stipulated as true according to the Neo-Phrygians. Now, the definientum should acquire the meaning it needs to have in order that the effect, the outcome of the definitional procedure is true, is a true proposition. So the same question that cropped us in the previous cases of implicit definitions can arise again in this case, that is, whether a meaning for the definientum is available so that the very postulate in question becomes true. Nonetheless, in this case, an abstraction's empirical disconfirmation is not expected. However, what does guarantee that the appropriated meanings are available? This depends at least on semantic facts such as satisfiability. If the abstraction principle in question is satisfiable, then there are models of it and there will be meanings for the definientum, the operator S, so that the stipulation results in truth. Yet, the existence of satisfiers does not immediately follow, but only in those interpretations of the language that are models of the abstraction principle. It is obvious that if the abstraction principle in question is not satisfiable, then there are no available meanings for the definienta and there are no semantic interpretations of the language in which the abstraction principles becomes true. This is the case of law V from Grudge-Sedge of Frege. Law V is not consistent at all. Yet there are other conditions too that abstraction principles should fulfill in order to work properly. The Neo-Phrygians have presented such conditions like conservativeness, modesty, etc. Yet it is not my aim to examine those presuppositions or complete the Neo-Phrygian list. Nonetheless, one can take those abstraction principles that Shapiro presented in one of his papers and raise the question whether there are meanings for the definienta in each case. Those principles are taken to be satisfiable and conservative, but incompatible. The first one is satisfiable on the limits in the series of inaccessibles, whereas the second one is satisfiable on the successors in the series of inaccessibles. The first one entails that the universe has the size of a limit, whereas the second entails that the universe has the size of a successor in the series of inaccessibles. So if the universe does have the size of a limit, then the second abstraction principle, though satisfiable and conservative, accrues no meanings to the definienta of it. Yet my point does not concern the bad company question here. My point is that the availability of meanings is not irrelative with certain facts, metaphysical facts. The stipulation of an abstraction principle as true results in a proposition that conveys a factual, though not empirical, content. So the truth posed by stipulation depends on broadly metaphysical facts. In similar words, the truth abstraction principles express does not hold just by means of stipulation. Abstraction is not purely stipulative. Does the conditional form secure pure stipulative status? I should deal at this point with some remarks made by Hale and Wright concerning the conditional form of implicit definitions. Hale and Wright have remarked that stipulations often lead up to arrogance. They call arrogant any stipulation of a sentence whose truth cannot be affirmed without a posteriori epistemic work. This is Hale and Wright's notion of arrogance. I will call it arrogance according to Hale and Wright. They assert that to avoid arrogance, implicit definitions should be conditional in form. Stipulations given in the form of conditionals are not arrogant, since they do not need a posteriori epistemic work to affirm the truth of the postulates in question. Hence, Hale and Wright hold that abstraction principles, in particular, avoid arrogance because of their double conditional form. In the first place, I agree with that claim, granted the notion of arrogance put by Hale and Wright. In fact, the conditional form of abstraction principle safeguards their resistance to any empirical disconfirmation, so their epistemic a priori status is not at risk. However, this paper makes the further claim that the fact that abstraction principles do not need any a posteriori epistemic work is not adequate enough to confirm that their truth can be a matter of mere stipulation. Avoiding arrogance, according Helen Wright, is not adequate enough to safeguard the stipulative status of abstraction principles. I do not doubt the a priori status of them, but what is at stake is that a stipulation of the truth of the sentence in question is possible, that the truth of that is indeed something which we can settle only in virtue of stipulation. Avoiding arrogance, according Helen Wright, is not adequate enough in case of mathematical implicit definitions, since they may suffer from another difficulty. Horwitz's existence problem still arises in this case, since, as it was earlier argued, the existence of meanings of such a kind so that the very stipulation leads up to a true proposition depends on certain conditions that have to be met independently of us. I believe that those kind of definitions may suffer from another kind of arrogance. I call it arrogance X. I call arrogant X any stipulation of a sentence whose outcome is a proposition with a factual content that can be detected by Ramsey's method. When I say factual content in the mathematical cases, I do not mean empirical content, of course, but broadly factual content, that is, metaphysical content. A proposition may have strong metaphysical commitments, that is, it has a broadly factual content, though not empirical. This notion is broader than the notion of Helen Wright, since implicit definitions that avoid Helen Wright's arrogance may be arrogant in sense of arrogance X. In order to detect the factual content of propositions in which our implicit definitions lead up, we have to apply the method of Ramsification that was introduced by Ramsey and articulated by Carnap. Recall, to cut a long story short, Carnap held that the scientific theory is logically equivalent to the conjunction of two components, from which the first one is the Ramsey sentence of the theory, and the second one is the Carnap conditional of it. He aimed to distinguish the analytic from the factual part of a scientific theory. The Ramsey sentence is an existential sentence we get if we replace the theoretical terms of the theory T by variables, and then bind those variables with existential quantifiers. Then the Ramsey sentence says that there are entities or classes of entities that realize the theory. Yet the Ramsey sentence never specifies the entities it asserts in a unique way. On the other hand, the Carnap conditional says that if there are entities that satisfy the Ramsey sentence, then those entities render the theory true. It so implicitly defines the theoretical terms of the theory as satisfying certain conditions that are established by it. As Carnap put it, the conditional, the second component, is not subject to either confirmation or disconfirmation, and it is devoid of any factual content, that is, it has the status of a meaning postulate. Although Ramsey-Carnap method is regularly applied to theories, I will apply it to the cases of implicit definitions under investigation. The aim is to show off the arrogance X of the relative postulates and their extra commitments that block their ability to be purely stipulative. Lewis first applied the Carnap-Ramsey method to postulates, but only to postulates of scientific terms in his discussion of the stipulation issue. My point is different, however. First, I am applying the Ramsey-Carnap method to mathematical postulates. Second, I aim to show that the propositions that arise from stipulation convey an excess content that is captured by the Ramsey sentence's components. Third, I seek the form of mathematical implicit definition that has a purely stipulative status. Fourth, I will claim that the required implicit definition is the Carnap conditional of the initial postulate. Before doing this, let us see what happens if the Carnap-Ramsey method is applied to a postulate of the theoretical term F, like phlogiston. Then the postulate can be taken to be equivalent to the conjunction of two components, from which the first one is the Ramsey sentence, which says that there are entities or classes of entities that realize the initial postulate. The Ramsey sentence captures the factual content of the postulate in question. This content may be empirical in this case, in this particular case. Particularly in this case, the postulate is arrogant in the sense of arrogance, Helen Wright put it, since it needs a posteriori confirmation. The proposition that arises from the stipulation in question may be empirically falsified, as in case of phlogiston. On the other hand, the second component, that is the Carnap conditional, says that if there are entities that satisfy such and such conditions, then F satisfies those conditions. It accrues a meaning to the scientific term F by denoting whatever, if anything, satisfies the alleged conditions. Thereby, it accomplishes the task of defining the initial definienda while it is devoid of any factual content. Now, let us apply the Ramsey-Carnap method to an abstraction principle. No. No. Let us apply the Ramsey-Carnap method to a system of mathematical axioms. Then we have again two components, from which the first is the existential Ramsey sentence of the system that replaces the theoretical terms by the variables x, y, and z and binds them by existential quantifiers. It says that there are mathematical entities that satisfy certain conditions laid down by the postulates. Hence, the postulates have a broadly factual content that is captured by the Ramsey sentence. Of course, that content is not empirical in this case, yet it is broadly factual since it concerns existential commitments to a domain of abstract entities. The truth of the system of postulates requires the truth of its Ramsey sentence, but the latter depends on semantic and metaphysical facts. Nonetheless, granted that the Ramsey sentence is not empirically falsifiable and it does not bear any empirical content, the a priori status of the axiomatic system is not at stake. However, it asserts the existence of abstract entities, allowing at the same time for multiple semantic interpretations of them. If the system of axioms is satisfiable, then it has at least one model. In those interpretations that are models of the system, and only then, the existential component, the Ramsey sentence, is true. Hence, the stipulation in case of mathematical axioms is arrogant, not in the sense that Helen Wright put it, but in sense of arrogance X. However, there is a second component, that is the Carnap conditional of the postulate. This conditional implicitly defines the terms, the mathematical terms FGH, by asserting that if there are entities that satisfy such and such conditions, then FGH satisfies those conditions. It is a minute postulate and accomplishes the very task of the axiomatic system to define FG and H, that is, the initial definienda, point, line, and plane. Let us apply now the Ramsey-Carnap method to an abstraction principle. For simplicity, consider Hume's principle, a well-known abstraction principle. Hume's principle is a second-order universally quantified biconditional, which says that for every f and g concepts, the number of f's is identical to the number of gs, even only if f and g are one-to-one correlated. By Carnap-Ramsey's method, an abstraction principle can also be split up into two components, from which the one is the Ramsey sentence of it, and the other one is the relative Carnap conditional of it. The Ramsey sentence of Hume's principle is a higher-order existential sentence which says that there is an operator S that works in such and such a way, and it can be formulated as here. And here is the matrix. The second component is the Carnap conditional that implicitly defines the standard numerical operator n. And it says that if there is an operator S that works such and such a way, then the standard numerical operator n works this exactly way. Quantification here is over operators. So Hume's principle has a component with a broadly factual content, not empirical but metaphysical in this case, that is a higher order existentially quantified sentence that asserts that there is an operator S that works properly. S is a second level function that correlates concepts f and g to their images sf and sg in such a way that S of f is identical to S of g even only if f and g are one-to-one correlated. So abstraction principles convey an excess content too that is captured by the Ramsey sentences. Here again, the truth of an abstraction principle is not something that holds just in virtue of mere stipulation, the existence of appropriate meanings for the definientum, so that the postulate in question expresses a true proposition does not immediately follow, but only to those interpretations of it that are models. This depends on certain semantic conditions. Moreover, the truth of the postulate in question requires the truth of the first component, which conveys rich metaphysical commitments to domains of abstract entities. Hence, although the a priori status of an abstraction principle is not really at risk, the truth of it depends on metaphysical facts. It is not arrogant in sense of arrogance hell and right posited it, but in sense of arrogance X. On the other hand, the second component, the Carnap conditional of the abstraction principle, defines implicitly the initial definientum, for example, the operator n, by saying that if there is an operator S working in the way indicated, then the standard numerical operator n works exactly this way. Hence, it accomplishes the task of implicitly defining the initial definienta. The mathematical postulates, in each case, have a factual and a stipulative component. The results that I have come across up to now can now be summarized in the table below by presenting in different columns the two components of the implicit definition in each case. In the first column we see the postulate. The second and the third case is in my concern, the mathematical cases. The first case is the case of a postulate of a scientific term like phlogiston. In the second column, we see the factual component in each case, the factual component of the initial postulate, and in the third column, we see the definitional component, the Carnap conditional of the initial postulate. So, though the a priori status of mathematical implicit definitions is not at risk, mathematical postulates seem to be arrogant in sense of arrogance X. They have a factual content captured by the Ramsey sentence of them. The truth of the systems of axioms and abstraction principles requires the truth of the Ramsey sentence, which depends on further semantic and metaphysical facts. Up to now, the view was defended that implicit definitions, even in case of mathematics, are not purely stipulative. Each one has two components, from which the first is factual, where the second is purely stipulative. This second component, the Carnap conditional, accomplishes the task of defining implicitly the initial definienta. The suggestion made here is that the definitional role of each one of the implicit definitions under consideration should be assigned rather to their Carnap conditionals. It has been argued that avoiding arrogance in sense of Hale and Wright's notion does not safeguard any stipulative status, that is, the fact that some postulates do not need a posteriori epistemic work for their affirmation is not adequate enough to safeguard that their truth is a matter of mere stipulation. So we seek for a form of the vehicle of implicit definition so that the postulate has a purely stipulative status. I argued that the conditional form in general safeguards a prioricity, however, it does not guarantee pure stipulativeness. Even in case the initial implicit definition in question has already a conditional form, for example, an abstraction principle, their Carnap conditional should accomplish the definitional role instead of them. This is due to the fact not merely that the Carnap conditionals avoid epistemic arrogance, but that they convey no factual content at all. The point that is stressed here is that what we need is to find such a formulation of the vehicle of implicit definition that excludes any factual content from the candidate postulate. A Carnap conditional has a purely stipulative status that is due to some special characteristics that are described below. Recall that Carnap himself characterized those conditionals as meaning postulates. First characteristic, the way stipulation has to work is to assume that we let the definienda meaning, if anything, whatever will make our postulates true. A Carnap conditional has such a form that not only prevents any empirical disconfirmation, but it safeguards that it is factually empty. Let's stipulate that Carnap conditional as true in general. The postulate in question has a Ramsey sentence that is trivially true, hence it is devoid of any factual content. This characteristic of factual emptiness makes an important difference between a Carnap conditional and any other kind of implicit definition. A second characteristic of Carnap conditionals is related what can be regarded as an unconditionally assertable principle in the sense that Sellers has indicated in an article of him. Sellers characterizes as unconditionally assertable those principles which are neither empirical generalizations nor deduced by other principles. Those are regarded as constituting certain conceptual frameworks. Hence, they define implicitly certain theoretical terms, they are implicit definitions. It is true that Carnap conditionals are not derived either by deduction or by induction. After stipulation, the Carnap conditionals do not make any factual claims and we can unconditionally accept them. Carnap conditionals state a choice of names that are given to a sequence of values of the existential variables that occur in the antecedent of the conditional. They assign meanings to a range of terms by laying down the assertion that the definienda should acquire meanings according to certain conditions established by the Ramsey sentence. Accordingly, Carnap conditionals have the proper formulation in order to work as pure stipulations. In particular, Carnap conditionals of the implicit definitions that were under consideration accomplish the very task of implicitly defining the initial definienda. According to the above characteristics, Carnap conditionals have a purely stipulative status. Hence, the definitional role of the alleged implicit definitions in question should rather be assigned to their Carnap conditionals. It's okay. This is the end.
I will be talking about definition, and as you sure know, definition is one of the oldest jobs of philosopher. Socrates himself spent his time trying to define stuff with his fellow Athenians. And in the field of philosophy of science and epistemology, the question of definition is the following: how can we define theoretical terms, scientific concepts introduced by theory? One case shows that this problem is not just a problem for philosophers, but also for scientists, for physicists. This is the classical case of the definition of mass. I don't know if you have experienced that, but as a young student in history and philosophy of science, one rainy Sunday, I told myself, okay, let's go, I'm going to read Newton's Principia Mathematica. And I first opened the book, and I found this definition: the quantity of matter, which I took to be the mass, is the measure of density and volume conjointly. Well, if density is defined by mass, then this definition seems circular. And I was really disappointed. And there was another man who was really disappointed by this definition. It's Marr, and Marr in his mechanics has Professor Moulines told us yesterday. Marr tried to pursue a project of kinematization of mechanics. And for him, the notion of mass was a theoretical term, and the kinematical notion were observational terms. That's why he tried to give definitions of the dynamical concepts with kinematical concepts. All that I'm going to say today depends on the fact that there is a distinction possible between theoretical terms and observational terms. But the way you define this distinction is not relevant. You can define it any way you want. All that I'm going to present is still correct. And you can have a relativist definition of theoretical like Professor Moulines. It doesn't change what I am going to say. So Marr proposed this definition. All those bodies are bodies of equal mass, which mutually acting on each other produce in each other equal and opposite acceleration. There are two interesting things about this definition. The first one is that you can derive it from Newton's axioms, from the third laws and the second laws. It means that Marr tried to reformulate the axiomatic of Newton in order to derive a definition. And the second thing, which is very interesting about that definition, is that you can see that it's a if and only if formulation of the definition, mass A equal mass B, if and only if their acceleration is equal and in opposite definition, opposite direction. In logic, this kind of definition with an if and only if formula is usually called an explicit definition represented by an equivalence symbol. An explicit definition is a definition where a predicate T, the definiendum, is equivalent to a definiens, here U, which have the following requirements. It is not contradictory, it contains the same free variables than T, and it contains only primitive term, and so it's not, the definition is not circular. If you try to define not class term but function term, you have to add some requirement, but for the sake of simplicity, I will just examine the case of class terms. Many authors regard explicit definition as the only proper definitions. Why? Because explicit definitions are eliminable. You can, in every sentence where T appears, replace it by U, and because it is eliminable, it is non-creative, which means that adding T to the vocabulary of your language does not allow you to prove anything else, any new theorem. And once you have this notion of explicit definition, you can reformulate Marr's problem into a much more general problem. Is it possible to give, for each T term individually or for all T terms altogether, an explicit definition with definitions couched exclusively in O terms? If yes, then T terms are just abbreviations of observational sentences. Well, you may know that it is the classical problem of a certain kind of logical positivism, and since at least Carnap testability and meanings, and ample theoretician's dilemma, we know that it's going to be difficult to find explicit definition. And we can think that it's not possible at all. But Ample himself, in the theoretician's dilemma, in the section 7, where he analyzed this question of explicit definability, say that the present section, in the present section, we have yielded no conclusive argument for or against the possibility of explicitly defining all theoretical terms of empirical science by means of a purely observational vocabulary. In fact, we have found strong reason to doubt that any argument can settle the question once and for all. My goal here is trying to prove you that we can, in fact, settle the question once and for all. We can, in the classical case, where we define explicit definition as eliminable definition, we can see that there is no explicit definition of T-term available. However, we can still give explicit definition if we accept a broader version, a broader meaning of the notion of explicit definition. But in that case, we lose the property of eliminability. So how can we prove that a term or a collection of terms is not explicitly definable by the other term appearing in the same theory? There is a classical procedure for that. You use Bethe theorem and Padua principle, which are the converse of each other, to say that explicit definition equals implicit definition. If a term is implicitly defined by the axiom of a theory, then it is explicitly definable. Explicit definition, well, you just heard a talk about that, so I'm not going to speak in details of the notion of explicit definition. Here I have a semantic notion of implicit definition. The idea is that if a term of a language is defined implicitly by the other term, it means that its interpretation is dependent from their interpretation. So if you change the interpretation of all the terms of the language except the term T, then the term T interpretation will change also. And Padua principle ends up saying that if you find two interpretations of a term satisfying the axiom of your theory, then without changing the interpretation of the other term, then you have shown that it is neither implicitly nor explicitly definable. That's the precise formulation of that. Another example is given also by the case of mass in particle mechanics. You may know that Sulpice proposed an axiomatization of mechanics in his introduction to logic. And he said his very weird phrase, a very weird sentence, my definition of mass is a definition only in some Pickwickian sense, which, for a non-native speaker who used to sleep during English literature class, doesn't mean a lot, because Pickwick is, in fact, one of Charles Dickens' characters, and it only means that my definition is not a good explicit definition. And Sulpice shows it by applying Padua principle. For him, there is six primitive terms in classical dynamics, mechanics. You have three kinematical terms here, the set of particles, the set of real number measuring elapsed time, and the function, the position function of the particle. And you have three other dynamical terms in which you have mass and forces, internal and external forces. Well, you can find very easily two interpretations similar with respect to P and T, if you just choose, for example, two particles P and Q. If you choose an arbitrary measure of time, like from 0 to 1, and if you choose to let the two particles at the same place during this time, and you say that the position of P and Q are both constant, well, you can change the interpretation just for the term of mass and say that in the first interpretation, mass of P is 1, mass of Q 2, and in the second interpretation, mass of P is 2, and mass of Q is 2, 2. So we have two interpretations. Believe me, they satisfy both the axioms of the mechanics from supers, and so it means that we cannot define mass in terms of S, T, and P. The idea is to give something like the proof that mass is not definable by the kinematical concept, but for a general proof for all T terms of scientific theories. Can we do that? Yes, I think we can do it if we look at some result from Winnie. Winnie was a teacher at the Hawaii University during the 60s and the 70s, and he proposed two theorems in a paper named the Implicit Definition of Theoretical Terms, in which he defines scientific theories in a very classic way. For some people who know Carnap's work, you have T terms, you have O term, you have mixed term, which is important, and they are interpreted purely extensionally as sets or entropes of dt, do, and dt and do respectively. dt being the class of theoretical entities, do the class of observational entities, such as dt and do are distinct. They are non-interpolating. So if you have such definition of scientific theories, then a possible model for L will be a model of this form, which should remind some things to all of you. You have the domain, then you have do dt, you have the interpretation of your observational term, theoretical terms, mixed term. And what you can do, I will propose, it's to, you can find another model in which only the interpretation of the theoretical term and of the mixed term change. How do you do that? Well, that's really just a sketch. And you make a permutation of dt, which is not a permutation of do. Well, in fact, it's the identity permutation for do. And as a matter of fact, if the permutation of dt changes the interpretation of at least one of the theoretical terms, one of the extension of the theoretical term, you have changed the interpretation of one theoretical term without changing the interpretation of the observational terms. That's the official proof by Winnie. So the idea is exactly the same that the one we have found in the case of mass in Super's axiomatization. You can show that we have the same interpretation for O terms and changing the interpretation for T terms, which means that by Padua principle, you can say that there is no implicit definition of T terms by O term, and then no explicit definition of T term by O terms. You must say that some T terms are primitive, that there is an interdefinition of T terms, and you must say that there is some kind of indetermination of T terms interpretation. All of that is equivalent to a simple requirement, which is to have a distinct domain of theoretical entities. It seems to be the final point. Yes, we cannot have an explicit definition of T-term couched exclusively in observational terms. However, there have been some proposition of explicit definition given by Carnap and Lewis using Ramsification to try to provide explicit definition. Let's take a look at it, but quickly, because Georg Schimmer will give a talk just after me. Is going to talk about the procedure from Carnap, so I'm not going to detail it. I'm just going to sketch it. The idea is quite simple. You take the Ramsey sentence of a theory. You know that the Ramsey sentence of a theory is T-term free, but conserves the extension of T-terms with the help of predicate variable. Then it should be possible to introduce a meaning postulate which says that the first T-term of the theory is the name for the first variable of the Ramsey sentence. The second T-term is the name for the second variable of the Ramsey sentence, etc., etc. Carnap did it by using Hilbert's epsilon operator. So you have some strict definition, very precise definition of Hilbert operator, which you will see, I think, after that. Just for my joke, it's important to see that the epsilon operator say that it designates the representative of a set. So the idea behind Carnap's proposition is to define T-term as the epsilon representative of theta, the theory, the Ramsified version of the theory theta. So that's exactly what is said there. And then you can define each T-terms independently as the representative of one of the subset. Carnap is very clear, as always, about what he is doing. He says clearly that instead of the operator epsilon, we could use here the customary description operator iota, since the formula in square bracket fulfills the uniqueness condition with respect to x. As you can see, there is a uniqueness condition in the square bracket. That is exactly what is going to do Lewis a few years after. In How to Define Theoretical Terms, he uses the iota operator to define, of definite description to define the T terms. But as you can see it there, you can see that it looks a lot like a Carnap proposal, but the difference is the uniqueness condition. The uniqueness condition is that the theory theta must be uniquely realized. And well, we'll see that it gets Lewis in a lot of trouble. So these two procedures of definition are different, and yet they have a common feature, is that they use indeterminate constants. Carnap explicitly says that it could be very weird to see that we have explicit definition of T-terms, but the frequently made assertion that it is impossible to define T-terms is indeed correct if and only if the primitive lexical constant of the language used have a well-determined complete interpretation. If a language like L epsilon is used, the situation is radically different because the symbol epsilon was intentionally introduced by Hilbert as an indeterminate constant. And in fact, the iota operator is quite the same. The iota operator implies that if theta, in Lewis' case, if theta is not realized or is multiply realized, then the T-terms do not name anything. The problem is this uniqueness condition. You see that for Carnap, it is possible that you don't fulfill the uniqueness condition. Not for Lewis. Lewis said that a good theory, a well-confined theory, should be mono-realized. And it clearly goes against Winnie's result. And Lewis knows it. So he tried to criticize the Winnie's results by saying that Winnie's proof does not apply to his case because his conception of O terms includes Winnie's mixed term. For Lewis, the O terms are just the older terms. They are the terms not introduced by the theory. So when you say that they are mixed terms for Lewis, it means that they are observational terms. So as you have seen in Winnie's proof, you have a change of interpretation of mixed term. At the same time, you have a change of interpretation of T-terms. So for Lewis, it means that Winnie's result does not prove that you can change the interpretation of T-terms independently from the interpretation of observational terms. However, I think that the requirement of uniqueness is too strong. We can come back to that during the discussion, but you can prove that as long as there is two elements which do not belong to the domain of any observational terms, Winnie's result still works. It still holds. So, and I think that Lewis will agree that we can show that there is two theoretical entities, at least two theoretical entities. I think that the requirement from Lewis is too strong, and that we can even accommodate Jeffrey Ketland's proof of Newman objection in 2004 to prove that Lewis' requirement is too strong. We can come back to that later, but I would like to present you some generalization of Bayes' theorem in the theory of definition, which could help us provide explicit definition for T terms. Well, because the theory of definition did not stop with Bayes' theorem, some people proposed other kind of definability and some broader sense of the explicit definability. And I would like just to show you here that they don't have eliminability of the definiendum. For the sake of simplicity, let me just define what we could call the degrees of indetermination of T. The degree is just the number of different interpretations of T term which leave the interpretation of a term fixed and still satisfies the axiom of the theory T, theta. The first generalization of Bayes' theorem is Kueker's theorem. Kueker said that if the degree of indetermination of T term is inferior or equal to some n, which is a positive integer, then there are formula there are some formula O and U such that we can have this formula. Well, this formula says what? It says that we have a disjunction of bilateral reduction sentences. You know, bilateral reductions and sentences have been defined by Carnap, discovered and defined by Carnap in Testability and Meanings. And the first thing that Carnap says about this kind of formula is that they are not explicit definition because they have no eliminability. So Kueker theorem is very interesting because it shows you that you have this kind of definition possible, but it's not explicit definition. It's very interesting for another fact that Carnap, it's coherent with Carnap results in Testability and Meaning, where he shows that we can transform the postulate of a theory, the postulate and the correspondence rule, in fact, in a set of reduction sentences, which means for him that T terms are easily introducible in a scientific proof. The second result of the theory of definition I would like to present is Chang-Mackay theorem. The Chang-Mackay theorem asserts that if the degree of indetermination is inferior to 2 to the power of the cardinal of D, and if the cardinal of D is some infinite number, then we can draw from the axiom of theta a finite disjunction of explicit definition. Here you can see we don't have a conditional definition, we really have explicit definition. Yes, we still have the problem of the disjunction. If we have this disjunction of explicit definition, we have a piecewise explicit definition in which definiants cannot replace in every statement where appear T the definiendum. And there is another problem, which is the paramability problem, that you have some other variables over which you have a quantification, but let's put that aside. However, the Chang-Mackay definition, the CMD, what I would call the CMD, is very interesting for philosophy of science, because if you have a Chang-Mackay definition of a term T, and if you have an independent proof that T applies to some element C, then you know that you have this disjunction of observational sentences. And that's interesting because I think it's a good way to look at the open texture of theoretical terms. The idea behind the notion of open texture, well, what I understand as open texture, is that you cannot find for sure a complete list of all the observational equivalents of a theoretical term. And that's exactly what is said here, because you don't know how much of definiants you will have. You don't know that if all of them would be true or just some of them, you just know that at least one is true. So I think that Chang-Mackay proves the claim that the indetermination of T-term is responsible for their open texture, which makes them such powerful heuristic tools, because they tell you that you have at least one observational consequences from your T-term, but they do not tell you which one. They just tell you the range of equivalence, observational equivalence in which you should search. So, let's do it quickly. Yes, if you put the two results together, I think it proves that T-terms are easy to introduce in scientific proof and yet difficult to eliminate, and that is why this asymmetry between introduction and elimination, that is why we can think that it is heuristically more efficient to speak as if T-terms were really existing in nature. That is why it is more efficient to talk about magnetic field, for example, and not about their observational equivalence. Okay, that was just to show you with natural deduction how you can show that with Quaker, with the Chang-Mackay definition, you don't have an easy way to eliminate T-terms, but I'm going to move on because I want to see if we can draw any conclusion of all that regarding scientific realism. For me, the debate of realism and anti-realism is kind of like football. I like to watch it, I don't like to play it. I like to study the strategies, and I like when there is a good team, a good argument, but I'm not so fond of getting into it. I think that the Beth and Winnie, the interest of patching Beth and Winnie together is not to give a good argument in favor of the realism, of a certain version of a realism. It's just to draw the attention over a dilemma, which is a dilemma which is kind of a new theoretician dilemma, an upgraded theoretician dilemma, if you prefer. A dilemma which is, which every defense of realism must solve. The dilemma is the following one. We have shown that we could not find eliminable definitions of T-terms. It should seem that it is a good argument for a realist. A realist could say that, okay, yeah, we cannot dispense from theoretical terms. It must mean that they generally refer. But we have also seen that indetermination is linked to non-eliminability, so that the non-eliminability of T-terms come from their indetermination. And this seems like bad news for a certain version of realism. Why? Because if you say so, then if you say that T-terms are indeterminate, then you have to say that there is some kind of non-reference from the T-terms, not fixed reference from the T-terms. Okay, as I told you, I don't think that the dilemma is unbreakable. I think that every defense of realism tries to solve the dilemma. And one of the first way out of the dilemma, the most simple, I think, is to argue that this indetermination is trivial. We just change two entities. Yes, okay. The problem is if you said so, you have to admit that there is a true physical interpretation. If there is a true physical interpretation of theta of the theory, then there is a true numerical interpretation of the theoretical term, which means that you only you say that a theory just applies some structural constraints over the domain dt, and you are in some kind of epistemic structural realism, which is fine for certain people, and others find it a bit worrying. And the second way out would be to dissolve the indetermination by taking into account a new criteria, such as a stronger kind of novel prediction than the prediction which tells you that your theory is empirically adequate. So finally, I would just like to say that you may have found that talking about definition and model theory can be like Van Fresen said in the 80s some kind of purely self-generated problems, and all of them are solutions to purely self-generated problems. So much for the theoretical terms. But, however, in 2011, he kind of make an amendment and said that logic sometimes made it possible to refine philosophical problems and in some cases to solve them definitively. And the example it took is precisely definability. So thank you very much for your attention.
As Paul said, I'm defending structural realism again, which I'm sure will come as a great shock to you. And I know that nobody in this room needs to be reminded of what structural realism is about, but I thought it might be a nice, light way in what's been a very interesting but hard-working conference, very dense material that we just had a little bit of fun to begin with. So this is what structural realism is about. Now, I hope Thomas is going to help me. Now music and then back to the slides.
Induction got me. Yeah, in the middle of the night, the pessimistic induction got me. It seems the realist can't handle theory changing history. So I tossed and I turned till I thought my mind would rupture. Yeah, I tossed and I turned till I thought my mind would rupture.
Guess what's coming?
And then I heard the word, and the word was structure. I say, think of Fresnel, think of Maxwell. Oh, my theory fits so well. You see, the equations are completely preserved. So come on and give structural realism a whirl. Metaphysics
Poincarean, of course.
comes and it goes. Yeah, metaphysics, it comes and it goes. But the contents and the structure it just grows and grows. So if you wanna have the very best of both worlds, yeah, if you wanna have the very best of both worlds, come on and give structural realism a whirl.
Come on and give structural realism a whirl.
Come on and give structural realism a whirl. Yeah.
You're too kind. Okay, well, back to business then. I'm sorry if some of you may have heard that before by download. To impose it on you twice would be pretty cruel, but I hope some people hadn't heard it before. Okay, well, I mean, most of the people no, that's not right. I'm not expecting an easy ride with this attempt to defend structural realism again, because this conference uncovered very many disagreements that I have with people who've been talking before. So, for example, I don't believe that we can fit. There's been a lot of talk about fixing reference. I don't think that we can fix reference, at least with respect to fundamental theories. I don't take it that, as Holger said at the beginning, scientists should know what they're talking about. I don't think they can know what they're talking about with respect to fundamental entities. And I'm going to deny Pache, Putnam and others that a realist needs to assert that theoretical terms in successful theories refer, albeit that she can then allow on Putnam's view that what the theory states about these allegedly definitely existing entities may only be approximately true. I'm going to deny that a realist needs to assert that theoretical terms in successful theories refer. Instead, it seems to me clear that there's no reason why a fallibilist realist, and I'm not talking about fallibilism from some sort of general skeptical doubts, but from the history of theory change in science, recommends a very conjecturalist, fallibilist view. I don't see any reason why fallibilist realists shouldn't be just as fallibilist about the mode of reference of its theoretical terms as it is about the theory's truth value. Indeed, it seems to me perverse not to be. After all, the claim that electrons exist, say, is just a consequence of the theory of electrons. There's nothing special about existence claims, and the claim is taken to be true that electrons exist, or rather to have evidence in its favour, because of the great empirical success of that theory. So I take it as clear then, on top of that, that on this I think there is widespread disagreement about, that if we accept that theoretical terms are characterised exclusively by description, not by acquaintance or some other way, a direct way of knowing them, then subject, if Holger's analysis was correct, to not wanting to land up in conventionalism, the Ramsey view, which states that the full cognitive content of a theory is captured by its Ramsey sentence, is a direct consequence of that descriptivist position, which I certainly take. So if we're asked, for example, what electrons are, or rather, again, in my proper fallibilist mode, what we currently have the best reason to think they might be, if there are any, then we can only say that they are, or again, or rather that we think they are, they may be the sort of things, or maybe sorts of things, I'll come back to that very shortly, that do this, that and the other in accordance with our current theory of electrons, and that's just an informal representation of the Ramsey sentence, or the Ramsey view that the full cognitive content of the theory is captured by its Ramsey sentence. It's the maximum amount of knowledge that we can claim, even in a conjectural sort of way. So if that's true, then it seems clear that to avoid the Ramsey view, you've only got two options. Either you assert that we can have some sort of direct knowledge of theoretical terms by acquaintance as opposed to by description, independently of any theories, or we can develop some rival linguistically based theory of reference of theoretical terms. No one seriously thinks that one is tenable, though I think it creeps back in all the time in terms of what people want from a truly realist position, which I'll reflect on several times as we go through. But I think everybody accepts Putnam's remark that this would be mystical if we thought that this was true. There's no, as I put it, out of theory experiences for the fundamental building blocks of the universe. As for the second possibility of developing a different, or at least somewhat linguistically involved theory of reference for theoretical terms, there seem to be only two candidates, namely the causal theory, some version of the causal theory, or some hybrid of the kind that Stathis talked about yesterday. I've never understood how anybody could think that Kripke's theory could apply directly to the case of theoretical terms. Putnam's account is different, but it's quite explicitly externalist. That is, well, I take it to mean that we don't know what we're really referring to. It doesn't matter what we think. It's a question of what we are objectively, as it were, referring to. And so that means it seems to me that any version of the causal theory in the end amounts to a confession that we have ultimately no knowledge of what our terms refer to, if anything. And that's fine by me. I mean, let's take an example. I think the nearest to the most straightforward and the one that's closely tied to historical examples is the version articulated by Hardin and Rosenberg, who famously recommend that Fresnel, for example, to take that case, should be taken as referring to Maxwell's electromagnetic field when talking about the ether, because that's the entity that we now believe plays the role that Fresnel mistakenly believed was played by the elastic solid mechanical medium that he identified the luminiferous ether to be. So that's because that's what I've already said, but that's wrong. We don't believe that. We long ago abandoned Maxwell in favour, for example, of Lorentz. Maxwell, after all, remember, believed in an electromagnetic ether that underpinned the field. In the Lorentz theory. The field is sui generis, it's a primitive, it just happens to be not as a result of any contortions of any medium, the fact that at every point in space there's a well-defined value of the electric and magnetic field vectors. And of course that's been replaced in turn by the photon theory, and then by various elaborations involving quantum mechanics, quantum field theory, quantum electrodynamics and so on, and, which are entirely different kinds of animal from anything that Maxwell was talking about. And that's what presumably now we'd have to say that Fresnel was referring to some sort of quantum field phenomena when he talked about light effects. But then, of course, the fact is that we've got the pessimistic induction, which at least is compelling for me as far as a possibility of replacement. So tomorrow we might believe that Fresnel was referring on this causal theory to something that we don't know anything about. So it is all externalist, it is all of this kind, and as I've already said, so what Harding and Rosenberg ought to say is that Fresnel's term ether refers to whatever it is that's associated. I think the quote from Carnap yesterday that Stathis had, not caused by, but associated with, who knows? For me, at any rate, cause is a theoretical term. It's up for Ramsification like anything else. We don't know what the ultimate theory will never have. The ultimate theory, even if we did, we won't know where we got it, but we certainly can't guarantee that cause will be an important part of it. So I think associated is a better term. So what they ought to have said is that Fresnel's, and I think Putnam as well in the end, Fresnel's term ether refers to whatever it is that's associated with the range of optical phenomena concerned in the ultimate true theory. Now, as I already indicated, I'm okay with this as an account of real reference, what we're really referring to as opposed to what we think we're referring to. But we also need surely a notion of what we think we're referring to, an articulation of what that means. We want something more effective. We want to be able to say what we currently believe is the best shot at what underlies the range of optical phenomena that Fresnel was trying to. And there, it seems to me obvious that we're back with descriptivism again. We've lost all the causal bit as an account of effective or conjectural attempts to characterize what we may be referring to when we talk about these phenomena. As for Stathis' hybrid, I find it very inadequately characterized, and anyway aimed at a non-problem. It seems to me perfectly reasonable for a fallibilist realist, again, to be entirely happy with meaning change at every stage in the history of science, so long as it doesn't spread, as Kuhn and Feyerabend sort of suggested that it might, to the bottom's observational levels, and they never gave the slightest real reason why it should. So that we can compare, and we obviously can, that we can say that there's better evidence for Einstein's theory, special theory of relativity than there is for classical physics, for example, in the form of the prediction of the Michelson-Morley negative result as opposed to the ad hoc accommodation within classical physics that Lorentz and Fitzgerald effected. That means that there's better, in my book, that there's better evidence for the special theory of relativity, despite the fact that terms like mass, it's nothing to do with semantic holism, the very concept of mass on its own is completely different. It's a constant in Newton, as you all know, and it's a function of velocity in Einstein. That seems to be not at all a problem. Indeed, it's to be welcomed as a reflection of how wonderful scientific change can be, despite the accumulation at the empirical level. So anyway, I won't go on more about Stathis' position since he left. What I take this to mean is that we're stuck, very happily, in my case, stuck with descriptivism, and hence stuck, very happily stuck, not surprisingly for me, with structural realism, which says that the theoretical terms of our theory are known, of course, remember, in this conjecturalist sense, only, and I put that in scare quotes because what else could it be? The idea of knowledge by acquaintance of theoretical terms seems obviously nuts to me, known only through the way that they jointly structure themselves, that is, other theoretical terms and the phenomena, and that's basically the Ramsey view. This structural realism is totally committed to. Just on a historical note, this is just a bit of irrelevant stuff for the rest of you, but I didn't make it explicit that structural realism is committed to the Ramsey view, if you like, in the 1989 paper, though I think it is pretty clearly implicit, and it's made explicit in Zaha and Worrall 2001, where we take it as given and then start to worry about whether there are bad consequences of that. Let me just mention briefly, since it's come up very many times, why I don't accept the Lewis definite description amendment, but rather the old-fashioned, as it were, Ramsey view. Lewis has been remarked several times, goes for a definite description view. He replaces the existential quantifiers in the original account with uniqueness quantifiers. That seems to me, it can't be the case that a theory guarantees that there's only one sort of thing that satisfies it. And I think there's a little thought experiment underlies why you wouldn't want to say this. Suppose it turned out that the next theory is sticking with electrons. The next theory of electrons says that there are in fact two quite separate types of things, which would then probably would get different names, but let's say for the purpose of this illustration, electrons 1 and electrons 2. It happens that with respect to all the properties that our current theory uses, that electrons 1 and electrons 2 both do all those things. But then the theory goes on to say, moreover, electrons 2 do some different things. I think you'd want to say, without correcting anything about electrons 1, it seems to me that you would want to say, in that case, that this hypothesized future theory extends, without correction, the previous theory. But of course, if it was a definite description operators, definite description, if we took our theory now to be a definite description of electrons, we'd have to say that was false. The Lewis sentence for the new theory would contradict the Lewis sentence for our current theory, and that seems to me clearly wrong. Anyway, that's by the by, really. Okay, so what have we got? We've only got descriptivism. Descriptivism entails Ramsification, and structural realism is deeply committed to. It is just the Ramsey view with a few bells and whistles to do with the correspondence principles to deal with theory change and so on. So everybody is now ready to say, of course, that means that structural realism is hopeless because it entails that the full cognitive content of a scientific theory is captured by its Ramsey sentence, and we know that to be hopeless, don't we? Everybody knows that the Ramsey view succumbs to the Newman objection. This is not a question of philosophical discussion, it's just a theorem, Jeff told us yesterday. And so I'm just trying to fight against formally proved theorems, which doesn't sound like a very good idea. So the agenda for today is to show that everyone's wrong. And the line is a sort of standard one in a way. It's a reflection of the old adage that one man's modus ponens is another woman's modus tollens, or in this case, one woman's modus tollens is another man's modus ponens. In other words, what people think demonstrates the obvious falsity of structural realism just seems to me to emphasize one particularly important aspect of it, as we'll see. Okay, so what I want to claim, what I want to argue is that once various meshes have been cleaned up and once you understand what structural realism is, then there's no objection to structural realism here at all. Okay, so what are the confusions that I think should be cleared up? Well, people say funny things. So James Lederman, for example, in his entry on structural realism in the Stanford Encyclopedia of Philosophy, at one point says this: it's a mistake to think that, sorry, it's a bit small on the screen. It's a mistake to think that the Ramsey sentence allows us to eliminate theoretical entities, for it still states that these exist. It's just that they're referred to not directly by means of theoretical terms, but by description, that is via variables, connectives, quantifiers, and predicate terms whose direct reference are allegedly known by acquaintance. That's absolutely correct. But then a few lines later, he says, Demopoulos and Friedman conclude that reducing a theory to its Ramsey sentence is equivalent to reducing it to its empirical consequences, and thus that Russell's realism collapses into, quote, Russell's realism collapses into a version of phenomenalism or strict empiricism. After all theories with the same observational consequences will be equally true. It seems that if we treat theory just as its Ramsey sentence, then the notion of theoretical equivalence collapses onto that of empirical equivalence. Well, at least there's some sort of tension there. If the theory on the Ramsey view does still assert the existence of theoretical entities, it's hard to see how it can collapse into strict empiricism. And it's because he misinterprets what Demopoulos and Friedman say because of that notion of all the observational consequences, of course, as I already gave away in various discussions, but we'll underline it today. Okay, the second confusion, which starts with Newman, who completely ignored Russell's difference between theoretical terms which were known by description and exclusively, and observational terms which were known both through the interconnections established between them and theoretical terms in the Ramsey sentence, but also by acquaintance, famously for Russell. Newman completely ignored that and assumed that you were going to quantify over, theoretically, you were going to existentially quantify over all the predicates in the theory. And that's why it's always amazed me, and therefore came up with this view that if structural realism were correct, then it would just impose a cardinality constraint. It's not even that, but it certainly would just be a consistency claim. It's always been unaccountable to me why Russell, for whom this distinction between knowledge by acquaintance and knowledge by description was so central, should have given in and said, oh yeah, thanks Max, that shows my structural realism is completely useless. What he should have said is you misinterpreted it, you've forgotten about that. We don't quantify over the observational terms. We'll come back to it. Demopoulos and Friedman play around. First of all, they tell you it's a triviality, and they finish up telling you it's a triviality, i.e., that is the Ramsey sentence of any theory is a triviality. It's reducing physics to mathematics. In between, they take what's the sensible view, namely that some sort of claim to the effect that what the Ramsey sentence says over and above the empirical consequences of the theory is too trivial to be accepted as a version of realism. That's the sensible claim, but they sandwich it between claims that don't make any sense. And the worst offender in this respect is, of course, my former PhD student, Jeff Ketland, who, having explicitly recognized the obvious fact that the Ramsification of a theory and the theory itself are co-empirically falsifiable, and therefore there's no way that the Ramsey sentence of a falsifiable theory can be trivial, can be purely mathematical, finishes up saying in his famous paper, this leaves the structural realist in a sticky position, given that the impossibility of contention was to provide an interesting third way between anti-realism and realism. The position collapses to something very close to anti-realism, although this isn't anti-realism. As Friedman and Demopoulos put it, Ramsification trivializes physics. Well, he must have known that that was wrong. He just was irritating me, I think. It threatens to turn the empirical claims of physics into merely mathematical truths, but it's empirically, it's co-falsifiable with the Ramsey sentence. So we better stop jumping backwards and forwards as some of the discussions here have between. It's the middle bit that we need to focus on, as I'll say more clearly in a minute. The third confusion is about Carnap sentences. Let me not say anything about that again. Both Stathis and Hannes went in anyway. I've got more than enough material. Okay, so let me clarify first, rather confusingly, the second confusion, which I think just demonstrates that structural realism is ineluctably committed to a theory-observation distinction, however difficult that may be to draw. So again, remember that Russell's version is centrally predicated on this distinction between theoretical terms knowable only by description and observational terms that are also known by description, but they're also known by acquaintance, and hence that a complex theoretical system S is of that form, as we've had several times in various different structural variants, or for ease, using bold for the vector of variables. Implicitly then, the corresponding Ramsey sentence is that where the quantification over T just acknowledges that these are known not by acquaintance, but only through the way that they impose a structure on the phenomena and other theoretical predicates, that is through that matrix S of T1 through Tn, O1 through OM, but where the observational predicates are definitely not quantified over because they're taken to be known also by acquaintance. So as I say, it's always been a mystery to me why Russell conceded to Newton's disproof, which completely ignores that distinction. What Newman does implicitly in the original paper is assume that the O set of observational terms is empty, as if observational predicates is empty, and hence that the Ramsey sentence of S is that, everything quantified over, and that it does indeed say that S is satisfiable and therefore can't be, if that were the correct Ramsification of the scientific theory, then of course it would be true that the thesis was absurd, that the full cognitive content of a genuine scientific theory was captured by its Ramsey sentence, because it isn't just a consistency constraint. But as we've already seen, it's very different when we take the proper Ramsey sentence. As I mentioned several times, that's provably co-falsifiable with S, and hence the claim that it reduces to a mathematical triviality is absurd, Jeff. So what Newman showed was that, if we regard all predicates and functions as all of them as theoretical and therefore known only by description, then our theories would float above reality, not anchored in it, and would supply merely consistency constraints. So a structural realist has got to draw that distinction. How we draw it, as we've reflected several times during the course of this distinction, and why we draw it where we do, are tricky questions, and it would obviously take us the whole discussion and much longer than that to deal with it. It seems to me that there are two main contenders. One would be to be honestly phenomenalist and say that the stuff that's known by acquaintance is really at the phenomenal level. Of course, you'd have a massive Duhem problem or massively complex theoretical structure in that case, because you have to have lots and lots of auxiliaries that tie you not just to basic, we would normally think of as basic observational facts, but then some sort of psychophysical principles that take you to the phenomena. Or you stick at the level for the observation statements of what Poincaré called crude facts, which are basically coincidences. So the needle in the meter, don't take the meter seriously, just or needle. The thing there points to something like 5 on the scale, give or take a little bit. The computer printout at the end of this whole process reflecting what we think was going on in the laboratory was 0, 1, 1, 1, 0, 0, whatever. These sorts of the mark on the rigid rod coincided with the end of this mark on the rigid rod coincided with the end of that. That's what we know by acquaintance, and then all the rest is. But if you don't like that, you can take the Lewis view, although I think it is a cop-out, because namely that the observational terms are somehow, or the stuff that you don't quantify over is the stuff that's antecedently understood, because it seems to me the obvious next question is, well, how are they antecedently understood? And in the end, it seems to be obvious that you're going to get either an infinite regress, which we don't want, or you're going to have to come to some base point where you say, well, way back then, no doubt be very far back, these new terms were introduced against the background of purely observational ones. But I'm only, like everybody else, having said that we're assuming a theoretical observational distinction, they're not going on really to defend it. But it just shows, I think, that structural realism needs to do that. So we do need to regard some terms as antecedently understood. That's understood independently of the theory that's Ramsified. Okay, so let's forever eschew any claim that the Ramsey sentence of a sensible scientific theory S is a mathematical triviality or just amounts to a cardinality constraint, and concentrate on the meat in Demopoulos and Friedman's sandwich, namely the idea that what the Ramsey sentence says over and above the purely empirical part of S is trivial. And you won't be, again, surprised to know that I'm going to say that that's wrong. Indeed, I'm not sure that one can make sense of it. If it were right, then, of course, the claim would be that structural realism is not really realism. Okay, so then, clarification 2 of confusion 1, the James Leitgeb thing. As I mentioned when presenting them, it seems to me the first claim that Leitgeb makes in the Stanford Encyclopedia of Philosophy entry on structural realism is correct, that it's a mistake to think the Ramsey sentence allows us to eliminate theoretical entities, for it still states that these exist. It's just that they're referred to not directly by means of theoretical terms but by description. And we all know the rest. That seems to be absolutely correct. And it was recognized in a paper that's been quoted many times in this conference already, but by Hempel in his Theoretician's Dilemma. You remember that a central aim of that paper is to investigate ways in which theoretical terms might satisfactorily be eliminated, and it's clear that Hempel would very much welcome a result that gave elimination. But he's very definite that such an elimination is not achieved by Ramsification. He says something very similar to James. The Ramsey sentence associated, in fact, he allows himself a little joke, I think, sort of unusual for Hempel. Although he's a very nice man. The Ramsey sentence associated with an interpreted theory T' his terminology, avoids reference to hypothetical theoretical entities only in letter, replacing Latin constants by Greek variables rather than in spirit, for it still asserts the existence of certain entities of the kind postulated by the theory without guaranteeing any more than T does. T' does that those entities are observables. It seems to be on the contrary, it says that they're theoretical, that's what they are. So Hempel explicitly recognized that it would be an error to think that Ramsifying involves eliminating theoretical entities, and he implicitly recognized that the view, often attributed to Carnap, but I wouldn't attribute anything to Carnap in these circumstances where people know Carnap scholarship a lot more than me. But anyway, the view that any sentence expressible in purely observational language vocabulary automatically counts as itself observational. Although I think that's a tempting view, Hempel implicitly recognised that that's even more erroneous. And what I'm going to claim is that the later results of Newman, Demopoulos and Friedman, Putnam, Ketland are just root reiterations of that tempting error. That the error being, remember, that if it's expressible in observational vocabulary, then it can't be theoretical. Or rather, what I really mean, of course, not the results, the claims made about the impact of those results, because I'm not going to claim, obviously, that correctly formally proved theorems are up for debate. They're correctly proved formal theorems. It's a question about the impact of those results on structural realism or any version of realism. They seem to me to be just iterations of that tempting error. Okay, so that brings us to the most important clarification, the clarification 3, so important that I've written it in capital letters. Lots of sentences in purely observational vocabulary are clearly theoretical on any sane view of the matter. And I think, although my regard for Popper has steadily decreased over the years, in fact, sometimes lurched downwards at a great rate, on this I think he was right when he said, right from the beginning, that the epistemic status of a sentence depends at least as much on its quantificational structure as the vocabulary that it uses. So an example that was much discussed in Popperian circles, John Watkins had several papers about mixed quantified sentences like this. Every metal has a solvent, which obviously formalizes like that. Taking it that, for the purposes of argument, that being a metal and being a solvent are observational terms, then a sentence is still, I think, clearly not observational, at least in the sense that there's no finite set of singular basic statements that can either verify or refute that statement. Hempel actually mentions that example himself, again in Theoretician's Dilemma, and adds another one that he thinks should be counted as theoretical on any sensible view. He introduces this sentence, P of A, that's equivalent to, I couldn't find an equivalence thing when I was doing, anyway, never mind. P of A equivalent to, there is an X such that for all Y, if X and Y are distinct, then SA XY, where SX, Y and Z holds if and only if X is farther away from Y than from Z. As he points out, it states that there's an object such that A is further away from that object than it is from any other object. And again, it's an expression of the observation language, taking it just that further away as a three-place relation is a straightforwardly observational one. And yet it surely counts as theoretical, again in the sense that it's provable that no finite set of data can either verify or refute P of A. But even aside from any special examples, it should have always been clear, I think, that genuinely theoretical differences can arise over sentences expressed in purely observational vocabulary. An example that Imre Lakatos first gave me in my very first lecture from him, namely that there are unobservables, at least if we have finitely many observational predicates, direct observational predicates, then that's a straightforward sentence, that's expressible straightforward in the object language, in the observational language, but it's obviously theoretical. There's something that isn't O1 and it isn't O2 and it isn't O3 and it isn't ON. I think we've been misled by the tempting error of everything expressible observational vocabulary is theoretical, and by failure to make a distinction between what I called in a massively disregarded paper in Synthèse a couple of years ago, I thought it would set the world alight, a distinction between empirical equivalence and data equivalence. That's related to this issue very clearly, as we'll see. So people take it to the standard definition, certainly when Loudon and Leplin are discussing in their famous paper under determination of theory by data, so-called. They take it that this is the standard definition that everybody accepts, that two theories are empirically equivalent just in case every consequence of T expressible in the observational language in the observational vocabulary is also a consequence of T dash and vice versa. And people then think that that's what the standard examples that we all think should be distinguished, but in terms of one being much better empirically supported than the other, standard examples of theories which, however, are allegedly empirically equivalent. But they aren't, as we'll see, examples. So Copernicus and Ptolemy you worry about, at least with respect to a restricted set of data points, namely the apparent astronomical positions. It's well known that you, by dint of of suitable epicyclic constructions, even phenomena like the planetary stations and retrogressions that drop straight out of Copernicus can be accommodated within Ptolemy. For every datum that Copernicus yields about apparent astronomical positions, you can construct a Ptolemaic accommodation. Another famous example, which I'll talk a bit more about, Darwin and Gossified creationism vis-a-vis the fossils and so on. I'll tell you what that one is later on. The point's got to be, however, that although these two sets of theories are data equivalent, they're very definitely not empirically equivalent. And that means that there are empirically expressible differences between the two theories. So they must be theoretical issues, even though expressed in the theoretical language. So data equivalence, which I've not yet defined, says two theories are data equivalent with respect to some range of data D, just in case every singular observation statement concerning D entailed by T is also entailed by T dash, and vice versa. And clearly, intuitively, this is a weaker notion. Every empirically equivalent pair is data equivalent, but certainly not vice versa. So here's Philip Goss, one of my favorite people. He's great for teaching basic scientific method too, because he's got this wonderfully, he's the ultimate in ad hocery. He makes ad hocery, I don't quite know what. He has this book called Omphalos. Unfortunately, we lost Stathis, but does anybody know what Omphalos means? It's Greek. It means navel, and it's a weighty tome, about 300 pages long, addressed to a very difficult issue, namely why Adam should have had a navel, given the method of his creation. Now, how Goss thought he knew that Adam did have a navel was not clear to me, since, as I understand it, there are different viewpoints on this, but he took it as given, I don't know, maybe on the basis of some medieval paintings or something, that Adam did indeed have a navel. And at the end of 250 rather turgid pages, he comes to the view, well, why the hell not? God can do what he likes. So God created Adam with a navel, even though that wasn't a reflection of the usual process by which people get navels, because Adam was straightforwardly created. And he was used both by him and other defenders of creationism to defend creationism against various claims that there was strong evidence for Darwinian evolution, in particular the fossils, because Goss finishes up claiming that God created the world. You know, show me a load of so-called fossils. Well, why shouldn't God can do what he likes? God moves in mysterious ways. He can create Adam with a navel. He can create rocks with fossils in them. He can create stuff that already looks as if it's quite old, so that when you carbon date it, it's much more than 6,000 years old. You can create stuff. You can create batches of radioactive stuff such that some of it's already decayed at the very beginning. So everything, you can see that it's pretty clear that Gossified creationism, people using the Goss dodge, as I say, eventually you're going to finish up with a theory that's data equivalent to Darwin, but very obviously also not empirically equivalent. They're definitely not empirically equivalent, and we can easily identify statements expressed in the observational language over which they differ. So Goss entails and Darwin denies that there's nothing in the universe older than about 6,000 years old, because the universe was created in 4004 BC. Now, you might say, well, some people have said to me, well, age is a theoretical notion, you should use apparent age. Okay, well, even if you do that, it's clear that there are claims that are expressible in your preferred observational language, now just using apparent age. So Goss entails that there was a time at which things that Darwin holds had an apparent age and had none, because nothing had been created. Before 4004 BC, there was nothing with or without an apparent age. Okay, that's surely a theoretical difference expressed in purely observational terms. So it's not surprising, and we don't need to go to worries about quantificational structure like a la Popper or Hempel to see that it's in general not a foregone conclusion by any means that because something's expressible observationally, in observational vocabulary, it must be non-theoretical. So, although, as I mentioned already, I don't, of course, question the formal correctness of the closely related proofs of Newman, Putnam, and Ketland, though I can't help resisting pointing out some skullduggery in the latter, in that he uses the same symbols to signify both the predicates of the object language and the relations that they're intended to note when he constructs this meta-theoretical extension of an original theory, thus obscuring the fact that his Tarskian meta-theory in no way allows us to hook up the initial theory's theoretical terms to the real world, though it creates that impression. It used to drive me mad when we were having otherwise sensible discussions about football by saying, oh, it's easy, electrons refer to electrons. And it just, I mean, this is a similar. Prevarication, simply misleading. It certainly misleads students. I mean, it doesn't mislead him. Obviously, he says quite clearly that there's no hooking up there, and that everybody knows that Tarski's account is quite neutral between realism and anti-realism. So, obviously, but I'm not questioning, apart from the skullduggery, which I could do without, I don't, of course, question the formal correctness of the proofs. It's the impact claim for those results that I do want to question. Basically, all the questions for the negative impact on structural realism are essentially of the form, structural realism entails the Ramsey view correct, but this entails that there's no difference without an observable difference, or truth collapses into empirical adequacy, and that's supposed to be bad for any version of realism. And it would be if it were to do with this notion of data equivalence. It would be saying something that no realist wants to say, that there's it would be entailing some sort of purely instrumentalist view. It doesn't matter whether you think with Copernicus that the Earth moves around the Sun, or with Ptolemy that the Sun moves around the Earth, or it doesn't matter except on a pragmatic level. It may be easier to calculate the phenomena on one theory, but it's just a question of getting the data right. It's definitely not saying that, because it's not saying that, it's not saying that there's no difference between Copernicus and Ptolemy that's expressed in the observational language, as we'll see. One of them is their Ramsey sentence. So that's supposed to be incompatible with empirical realism. It sounds, as I mentioned, that what's being established is that once all the data have been incorporated, for example, both within Copernicus and Ptolemy, or within Gossified creationism and Darwinism, there's no epistemic difference between them. That's not so. So this is what I meant by one man's modus tollens is another woman's modus ponens. SR is happily committed. There's no negative result for it to the no difference without an observably expressible difference. Saying no difference without an observable difference sounds like you're being anti-realist, but not if you say it properly, which is no observably expressible difference, once you realise that there are very many theoretical issues that can be differences that can be that occur in the observational vocabulary. Indeed, given that if we lay aside possible issues about second-order quantifiers, the Ramsey sentence itself is expressed in the observational language. That was the whole idea: get rid of the theoretical terms by existentially quantifying over them. And that SR is committed, as I've said many times, to the idea that the full cognitive content of a scientific theory is expressed by its Ramsey sentence. We didn't need any fancy arguments from Ketland or Putnam or whatever to see that structural realism is committed to that view. It says that there can't be any difference without there being a difference at the Ramsification at the level of the Ramsey sentences, and but that doesn't mean the only differences that count are observational, because the Ramsey sentence is theoretical. Of course it's theoretical because it asserts the existence of theoretical terms. Okay, so returning to the Ramsey sentence, it does seem to me that if we take our cue from Quine, as it were, at the second order level, to be epistemically committed to is to be ready to existentially quantify over something, then emphatically the view is emphatically committed to the existence of, if you want to call it in these terms, natural kinds, T1 through Tn, where those are the extension, and as I mentioned already, there may be more than one string of such, since you don't want to have a uniqueness condition. I don't think that the idea, I mean, I'm convinced that we only get, at least with respect to proper science, we only get our notion of natural kinds from theories. We don't have a notion of natural kind ahead of theories. So the suggestion that we can get around the Newman problem, which isn't a problem, but let's assume for the sake of argument it were, the suggestion that we could get through by saying not there is something but there's a natural kind, but that's a complete non-starter as far as I'm concerned, because natural kinds are read off. The natural kinds, or rather, again, our current best shots as to what the natural kinds are, is that they're the extensions of the predicates in our empirically successful and unified and non-ad hoc theories. Okay, so taking our cue from Quine, then that does seem emphatically committed to the existence, which is just what a realist wants to say, and the temptation to try and go more realist and not existentially quantify just comes from this mistake of thinking that there must be some sort of knowledge by acquaintance of theoretical terms. If you don't believe that, then you should be ready to quantify. Okay, so now what everybody's going to say, is it really realism? And that's partly a boring sort of semantic issue, I think. But let me talk a bit about it. Anyway, the history of science gives us reason, I should say it's not really yet onto that, it's structural realism, really realism. History of science gives us reason to believe that the Ramsey sentence are successful theories, that successful, predictively successful non-ad hoc theories do reflect reality, not, notice, in a referential correspondence sense, that's been completely given up, but in a, admittedly, if you like, hand-waving, but a not further specifiable sense, that's betokened by the expectation that the general form of those current theories, if they are indeed successful both predictively and in avoiding ad hocness, will be retained at least modulo the correspondence principle in later theories. Well, so then if you do ask, is structural realism really realism? Well, not if you're wedded to various things. If you think, for example, that you're not a realist unless you're ready to assert the definite referential character of our theoretical terms, even though you're then ready to say that what we say about those allegedly definitely existing entities may be only approximately true, then obviously this is not realist because it gives that up right at the beginning. And if you're wedded in general to a correspondence or semantic view of truth as your account of corresponding with reality, then it's not going to count. But I don't see any reason on reflection why the way in which a theory mirrors reality should be by the usual term-by-term mapping described by traditional semantics. So structural realism takes it that the mathematical structure of a theory may globally reflect reality without each of its components referring to a separate item of that reality. So if you insist on, as I mentioned, on established reference for truth or near reference for approximate truth, then structural realism isn't realism. But it seems to me clear from the history of science that there's exactly because of reference change, there's no sustainable version of realism attainable if you do insist on that. This is all that structural realism... People say that Duhem's an instrumentalist, and he was an instrumentalist in the physics of the believer because he was pursuing a Catholic agenda at that point, but when he's being more serious in the main body of the aim and structure of physical theory, he's a structural realist. And he's a structural realist because of this single paragraph, 2 sentences, that shows how modest the view is. When he says this, the highest test, therefore, of holding a classification is a natural one, so some theories are natural classifications, that is, reflect reality in a way that, of course, Duhem knew just as well as Poincaré did, just as well as Elisar and I know, couldn't be couched out in standard referential terms, but nonetheless is very easily felt. The highest test, therefore, of holding a classification, a natural one, is to ask it to indicate in advance things which the future alone will reveal. And when the experiment is made and confirms the predictions obtained from our theory, we feel strengthened in our conviction that the relations established by our reason among abstract notions truly correspond to the relations of things. That's all structural realism is in my book. It may be too little for you to count it as realism, but in that case I'm sorry for you, but there's no stronger version of realism that's compatible with the history of theory change in science. It's extremely modest. It doesn't make false promises about telling you what this global reflection of reality means. Other than this, it's likely to be betokened by the continuation of the living on of the general form of our theories modulo the correspondence principle in later theories. It's consistent with the history of theory change in science. It's really, since it respects the no miracles intuition, just as we saw from that quote from Duhem, there must be something right about the theory, not necessarily something right that we can specify in traditional realist terms, but something right about the theory if it gets these amazingly unlikely predictive successes. It's not entirely trivial, though it's arguably close, but it's certainly modest. Maybe for some people, as I said, so modest that it's not worth talking about. But it's, as I said, the facts about theory changing science I don't think permit a more realist view that is consistent with facts about theory change. And the yearning for a more realist view seems to be in the end always to be based, no matter how subconsciously, no matter how often you say that it would be some sort of mystic view of that you knew theoretical terms by acquaintance, but it's some sort of outbreak of that operating in people's minds. But if you think that's what you have to have, you have to claim in order to be a realist, then you've got an easy time to refute the realist, because that would be obviously not acceptable. So I think structural realism is the only realist game in town, and so you should accept it. Thank you very much.
And I will be talking, as you see here, about typicality in statistical physics and dynamical system theory. So let me now introduce the problem. So when you look at Boltzmannian statistical mechanics, you find that a measure is defined over the possible states of the system. It's just a measure defined. And I mean, this is a long-standing foundational question in the foundations of Boltzmannian statistical mechanics, is how to interpret this measure. So should this measure be interpreted as a probability measure or as something else? And a recent, quite popular proposal, in particular among physicists who endorse Boltzmannian statistical mechanics, is that this measure is not a probability measure, but should be best interpreted as what they say a typicality measure. I'll say later more about typicality. But the idea is the measure is a typicality measure, and we can then use this typicality measure in claims such as I say here, typical initial stage approach equilibrium, or typical initial stage show thermodynamic-like behavior, and so on. And I mean, statistical mechanics is, of course, a theory in physics, and dynamical system theory is not a theory in physics, but this is really a mathematical framework with application in various sciences, including physics, but also biology, meteorology, climate science, and so on. But there's a similarity to statistical mechanics, namely that you also have measures here, because it's measure-theoretic dynamical system theory. And here's also the problem, how do you interpret those measures? And again, some have argued you could interpret them as typicality measures. So a similar problem here. I'll say more later about that, but the guiding idea, what these physicists also have in mind, is that typicality measures count states. They do not represent the probability of finding a system in a certain state, and they just count state or represent the relative size of sets of states. This is the idea. And I mean, the connection to this conference, of course, a typicality measure, because it's not even a probability, is very much an unobservable and theoretical entity. And there will be the question then later also how it relates to these observable entities, and I'll get back to that later. So the situation is what you have in statistical mechanics and dynamical system theory. You say there are people that claim, well, these measures are typicality measures. But what you don't have, I think what is missing, is why these specific measures are a good choice of typicality measures, a motivation or an argument or a justification. And because, of course, I mean, if you have a set, you can have very different measures on that set. And the measures in statistical mechanics and in dynamical system theory just under the use that claim to be typicality measures, but you need a justification why you should use those measures and not other measures as typicality measures. Okay, and so, I mean, this is really the guiding question of my talk, the idea we need a motivation why these specific measures are a good choice of typicality measures. And in the end, I will propose a first attempt at a motivation of these typicality measures, and along the way also criticize the only motivation of typicality measures I know in the literature from Pitofsky, who already addressed and tried to solve that question. Okay, I mean the outline, this was not an introduction. Then I'll just briefly introduce statistical mechanics and dynamical system theory and the systems there. And a few comments about typicality and the typicality approach and what typicality is. Then I'll outline Pitofsky's argument, criticize it, and as I said, I'll argue that, I mean, it's great that Pitofsky addressed that question and tried to come up with a proposal of how to justify typicality measures, but I don't think that in the end he succeeds, and so I'll provide a new motivation of typicality measures, which hopefully is better, and then then at the end the conclusion, as usual. Good, I mean now about the systems in statistical mechanics and dynamical system theory. Formally there are these triple, gamma E, phi t, and mu E. So what you usually consider in statistical mechanics, and what I'll do here, is of course, you consider systems consisting of, for instance, n particles, like a gas. And the assumption which I make here is that these systems are isolated from the environment. This is a very common assumption, but it will be important. And then what you get is these systems here. Gamma E is just a set of all possible states of the system. Relative, because the energy actually is conserved. Also all position or momentum coordinates at a certain energy level. This is the possible states of the system relative to a certain energy level. Then phi t, is just simply the evolution function. So the idea here is phi t of x is the evolution of the initial state x after t time units. So you start with initial state x, t time units, evolve it forward, and you get a new state. And that's phi tx, And I mean, this is the standard measure used in statistical mechanics. It's the microcanonical measure, mu e. And this is claimed to be the typicality measure. And this measure, as I will argue, for this measure, we need a justification why it is a typicality measure, because we could also use another measure as a typicality measure. Okay.
How is it defined, if I may ask?
This is really defined by, what you do is you start with the uniform Leibniz measure on, not on gamma E, but on the whole phase space of all position and momentum coordinates. This is what you start with. Then by Liouville's theorem, you get that this is invariant, this measure. And this measure is just obtained by restricting then the measure on gamma to the energy hypersurface. It's not the Leibniz measure because the restriction is not uniform, but it's what you get when you want an invariant measure. You have an invariant measure on gamma, and then you look at the energy hypersurface, which is sec n minus 1 dimensional, then restrict it such that it is invariant, and you get that. It's defined in terms of the Leibniz measure, but it's not quite the Leibniz measure. Okay, and then dynamical systems, they consist of, this is a very general framework, as I said. Dynamical system theory has applications in physics, biology, chemistry, of course, meteorology, even the social sciences. So it's just a tool. It's called theory, but it's really a set of tools of mathematical techniques. And so what we have here, it's again a triple, and X here is just a set of possible states, also called the state space. And then Ft are the evolution function, which just again is before the idea that Ft of X is the evolution of initial state X after t time units. So you start with X, evolve it forwards, t time units, and then you get Ftx. And then again, you have a measure defined. And they are standard measures, which are usually used in dynamical system theory. This is where you learn. And these measures are usually called mu x, and they are invariant. This is just a technical condition. We will come to that condition later, which means that, if you evolve sets forward or backwards in time, here only backwards, then the size remains the same. This is the condition. We'll come back to it later. So, an example of dynamical systems, because this is a very abstract framework. Statistical mechanical systems, which are introduced on the previous slide, these are just examples of dynamical systems. They just fulfill these formal requirements of dynamical systems. And another example, which probably many of you will know, and because it's so simple, we will use it here, is this famous logistic map, just defined on the unit interval, has different physical and so on interpretations. I don't go into it, but it's defined on the unit interval. The evolution function is just fx, 4x, 1 minus x. So this means if you start at time 0 in x, then fx is the system at time 1, and then you iterate again. So f of x is then the system at time 2, and so on. And this is not a logistic map, what you see here. This is actually the standard measure used for the logistic map. It's interesting because it's not the uniform measure, but it looks funny like that. So it's not uniform, but it is, this is the standard measure used for the logistic map. This is what dynamical system theorists use. And the question will, can we justify that this is a typicality measure in certain contexts? Okay, so now to the notion of typicality. So the guiding idea, of course, is that something is intuitively speaking typical if it happens in the vast majority of cases. So you can think of examples like typical rowers are tall, or typical lottery tickets are blanks, and so on. So this is the intuitive notion of typicality, and the typicalists, they appeal also to these intuitive notions. So formally, I mean, you can give, of course, formal definitions. And this is the definition we will be working with. We say that giving a basic set of elements C, so like all your lottery tickets or rowers, we say that the typical elements have property P relative to a typicality measure T, if and only if T of D divided by T of C equals 1, where T consists of those elements in C that have property P. The idea really is here, as you see, I mean, D is just a subset of C, and it's typical if it is a full measure. This is one of the standard notions of typicality invoked in the argument. I mean, you can also, sometimes you find something less stringent, namely this idea that, well, it's not exactly 1, but it's just very, very close to 1. So typicality measure of D divided by the typicality measure of really all the elements, C, is greater than 1 minus beta for a very, very small beta. And I mean, we will be working in this talk with this notion just because it's simpler for what I will present. But I mean, the main results are really some theorems, and they can be extended to hold for this notion of typicality. I just work here with, I mean, I present the results for this notion because it's a bit easier. But really, analogous results also hold for this notion. Okay, now to the requirements of a typicality measure. You ask yourself, well, we're interested in the notion of typicality measures. What requirements should such a typicality measure fulfill? One requirement, which is very much shared by the physicists, and you find them in their papers, is that what's called the typicality measure is invariant under the dynamics. And what you mean here is, I mean, the intuitive idea is what I write here. So if states are evolved under the dynamics, so if a set of states is evolved under the dynamics, these states cannot become more or less when they are evolved under the dynamics. And that's why the invariance condition should hold that the measure of ft minus 1 of A equals the measure of A. So it shouldn't become more or less. Formally, you express that as in this condition. So the minus 1, I mean, if you're interested in that, is just a technical thing because the logistic map is not invertible. So for statistical mechanical systems, you can't just ignore the minus 1. You just say ft of A equals T of A. You just want that the size is preserved under the dynamics. As I said, this is a very common condition endorsed by physicists like Goldstein and Leibniz. And I will endorse it too because I think it makes a lot of sense for a measure that counts states. I mean, these states shouldn't become more or less when evolved under the dynamics. Okay, now to Pitofsky's argument. As I said, I mean, as far as I know, this paper by Pitofsky is the only paper which tries to come up with something like a justification of typicality measures. So let me now introduce his idea. So what he does is, I mean, he considers the set of all sequences, infinite sequences, we start with the finite sequences. The set of all sequences of length n consisting of zeros and ones, so just sequences of zeros and ones. And then Pitofsky says, well, this is the first step of his argument. For a finite state space of n elements, the typicality measure is just a uniform measure over these elements. So the number of elements of a set divided by n. Makes intuitive sense. I mean, you can even question this, but I don't have to do that here because, I mean, if you even question this, then Pitofsky's argument is even in further trouble. And so hence, you know, for your sequences of length n of 0 and 1, you get that the typicality measure is the elements in A divided by 2 to the nth power. Because, of course, there are 2 to the nth power elements, different sequences of zeros and ones. Okay, but this is the first step, just saying uniform measure for finite state spaces. The uniform measure is the typicality measure, and you apply it to the specific case. Okay, then Pitofsky says, but well, I mean, in statistical mechanics and dynamical system theory, the real issue is these infinite state spaces, of course, and they are not finite. What should we do with those? And he considers and starts with the special case of all infinite sequences of 0 and 1s. And this, of course, you can, I mean, this is standard in measure theory, in ergodic theory. You can, of course, approximate a measure on these infinite sequences with these finite measures on the sequences of 0s and 1s of length n. And this is what Pitofsky does. And he obtains a measure on the infinite, on the set of infinite sequences of 0s and 1s. And this, he claims, is the uniquely correct typicality measure. I mean, this is the main argument he propounds. And of course, I mean, this state space, the infinite sequences of 0s and 1s, it's not something which you often find in physics or dynamical system theory, of course, because usually you find subsets of Rn or something like that. So the question is, what about other infinite state spaces? And Pitofsky then says, well, for the moment, let's just concentrate on the case of the unit interval, like for the logistic map. And what he does here, he maps the points of the infinite sequences of 0s and 1s to the points of the unit interval. I mean, what you do here, this is the map, but it's in essence, the idea is very simple. You just say, well, this sequence here is the binary development, the binary representation of the number here in the unit interval. I mean, this is just what Pitofsky says. So you take a number in the unit interval and assign to it the binary representation. This map is unique with some qualifications, but they don't matter here. And so you have this map here, and then what you do is you use the map psi to obtain a measure, to map the measure on these infinite sequences of 0s and 1s to the measure on the unit interval. And this, Pitofsky claims, now we have the uniquely correct typicality measure. The measure you obtain here, that's very easy to see, is the uniform measure. So just the uniform measure over the unit interval. And this is really Pitofsky's argument, saying, well, now we have it, and we have the typicality measure, which is just the uniform measure on the unit interval. This is, of course, a neat argument, and as I said, it's great that Pitofsky tackled the question, because usually it's just claimed, well, these measures are typicality measures, but you don't know why they are. But I think the argument itself is unfortunately not very successful for several reasons. I'll outline two problems, which I think are problems for the argument. Because the first thing is really, I mean, when you look back, I mean, here he uses the map psi, which has this specific form. But one first thought you can, of course, ask is, I mean, why this map psi? You can also use different maps. For instance, you could use what I call here kappa, which is just this map. Of course, looks a bit more complicated, but it's also a one-to-one correspondence. And there are, of course, an infinite number of different maps you can use. And for instance, if you use that one, I mean, I've here written down that one, because if you use that one, then you actually obtain, if you plug in that map instead of psi for Pitofsky's argument, you actually obtain the measure of the logistic map. You don't obtain the uniform measure, but the measure of the logistic map. So it's not clear, I think, why psi should be preferred over other maps. I mean, you could run some simplicity arguments, but I think that would be, anyway, I don't think these simplicity considerations are very fruitful, and there's really a question why you should use psi over other maps. And Pitofsky also doesn't address that, he just uses psi. And then, in a way, also a serious problem, because Pitofsky himself states that he's not only interested in statistical mechanics, but also dynamical system theory. And he says that his argument also applies to the standard system, standard measures in dynamical system theory. This would imply, of course, that for the logistic map, the uniform measure is the correct typicality measure. And there are then immediately two problems. I mean, first, dynamical system theorists choose a different measure, namely the one we have seen, which is not uniform. Okay, then you could say, well, maybe dynamical system theorists are wrong, which is, of course, a possibility. But the problem you have is that the uniform measure is not invariant. I mean, it doesn't even satisfy the invariance condition. And so the measure mu L, the one which I introduced for the logistic map, is invariant. So I think because it's even not invariant, it would be very hard to claim that the uniform measure is in this case the correct typicality measure. So you run into troubles. So you have really basically counterexamples from dynamical system theory, but Pitofsky says his argument does apply to dynamical system theory, but it leads to wrong conclusions in these cases. So, I mean, the general picture is, of course, and this is an important point, that if you look in dynamical system theory, for some systems, you have the uniform measure as the standard measure used. Think of something like the tent map. And for some systems, you have the uniform measure. But for others, like the logistic map and many others, you don't have a uniform measure. So what this suggests, and I think this is widely shared among the typicalities, but Pitofsky doesn't really consider that, is that you need to consider the dynamics when justifying or motivating typicality measures. Because if you just look at the state space, the unit interval, you know, if you always say, if you have the unit interval, then one measure is a typicality measure, then you can't account why so many say, well, for different systems on the unit interval, you actually should use different measures. Okay, one thing that dynamics needs to be taken into account, I think, when motivating or justifying typicality measures. And of course, it's something which I'll try to do. Okay, then now to a first attempt of providing an alternative motivation. Okay, so what's the guiding idea here? I mean, the first important consideration is to say, best motivated probably with statistical mechanics. I mean, in statistical mechanics, you prepare the system, like you prepare the gas in a certain macro state. And what philosophers and physicists often do is to say, well, this preparation is described by an initial probability distribution. Because, of course, I mean, it's just initial probability distribution which gives you the probability of preparing a system in certain microstates. And, I mean, these initial probability distributions have been discussed in philosophy. And my argument will be based on the assumption that these initial probability distributions are translation continuous. This is the formal definition, which just it's just a continuity condition. You see it here. I mean, as t goes to 0, the probability of A plus t is just a translated set. In Rn is the probability of A for all open sets. That's the condition. I mean, this condition is discussed in a set of relatively famous papers, I would say, in statistical mechanics by Malament and Zawel, and later then by Runners. And interesting in this context is two things, really. I mean, this condition is, for those, I mean, who know more about the technicalities, is equivalent to the condition that the probability distribution is absolutely continuous with respect to the Lebesgue measure. This is a condition which might be more familiar to some physicists. And this absolute continuity of probability distributions with respect to the Lebesgue measure, this is often endorsed by physicists and seems to be at least widely accepted by some physicists. And furthermore, Malament and Zawel in their paper, they have motivated that condition by, I mean, the guiding idea is really, I can't go into detail, is to say when preparing a system, we do not have sufficient accuracy to create any other sort of probability measure than such a probability measure. Because, I mean, if the probability measure is not translation continuous, what you have is that the probability measure is really peaked on basically just one microstate. And to get something like that, the argument is you would have to have very, very accuracy, which we don't have. I mean, this is basically the argument. So this is a major assumption, but I think it can be motivated. It is relatively plausible, though to some extent we will never know for sure whether it's correct, because we just know very little about these initial probability distributions. Okay, and then as a next step, I mean, what we want is really typicality measures. We want to use them as a shortcut to make claims about any possible initial probability distributions. So this is how we will connect the typicality measure to experiments. So the idea will be typicality measure should serve as a shortcut to make claims about all initial probability distribution of interest. And since we don't know, as I write here, which probability distributions actually arise in practice, we just allow all translation continuous probability distribution. This is premise one. Premise one just says, so the initial probability distributions we are interested in are all translation continuous probability distributions. And I mean, this is now for statistical mechanics, but for measure theoretical dynamical system theory, similar to justification or motivation I'll propose here will just hold whenever the initial probability distributions of interest are just all translation continuous probability distributions. So then the second premise I already discussed, that is really this premise has been already which I already motivated, that typicality measures should be invariant under the dynamics, widely endorsed by physicists, and I think for a good reason. And then, I mean, this will be quite important for the argument. Now, two premises follow, which really are about linking typicality measures to probability measures. Because, of course, if you say, well, let's use this as typicality measure, immediately the question will arise, well, if it's a typicality measure, how does that relate to experiments I mean, is it just this abstract typicality measure, how does this relate to experiments? And the premises will be about that. So first premise is if states have probability 0 for all probability distributions of interest, then they should be atypical. Formally, very simple, just say probability of A is 0 for all initial probabilities of interest, then the typicality measure should be 0. I mean, here really equivalent formulation, you could of course equivalently express it in terms of typicality, saying if states have probability 1 for all initial probabilities, then they are typical. It's possible too. It's just equivalent formulation. And now the second link of linking probabilities to typicality is to say if states are typical, then the states have probability 1 for all initial probabilities of interest. So if states are typical, then the probability is 1. And again, of course, you can also, I mean, you have just chosen that formulation because I think it's a bit more intuitive to express it in terms of typicality than atypicality. But equivalent formulation, again, you can say if states are atypical, then the states have probability 0 for all initial probability distributions of interest. So these are the two premises of linking probabilities with typicality measures. And then there's another premise, which is really to say a sufficiency conditions for typicality measures. So the idea here is if premise 2, 3, and 4 hold, which I've just introduced, so this invariance and the typicality as a link probability to typicality 1 and link probability to typicality 2. So if these hold, then the measure is a typicality measure. I mean, you can in principle question that. I mean, the reason why this premise seems at least plausible is, oh, sorry, I haven't included that here, so I should say that, is that you will actually get that the typicality measure, which fulfills premise 2, 3, and 4, can be used as a typicality in the sense that any other typicality measure will agree in judgments about typicality. And so it's fine just to say that this condition is sufficient. It doesn't get you into any troubles. You know, it would only be trouble if, well, these conditions say premises are typicality measures, but then you actually get that this premise implies that there are different measures which disagree about judgments of typicality, which are typicality measures according to this premise, but this doesn't happen. So, when here the argument for statistical mechanical systems, first to summarize again the premises and then discuss the conclusion. This is just again this idea that initial probability distributions are translation continuous or equivalently just absolutely continuous with respect to the Lebesgue measure. Premise 2 is the invariance condition. Premise 3 and 4 are these conditions linking probabilities with typicality measures. So if states have probability 0 for all probability distributions of interest, then they are atypical. States are typical, then the states have probability 1 for all initial probability distributions. And then this premise 5, sufficiency conditions about typicality measure. So what you then can conclude, you can show that is that the standard measure used in statistical mechanics is a typicality measure. And this is important. I mean, this measure may not be unique. So there may be other typicality measures. But this does not matter because any such other measure will agree on which sets are typical. So you can use another measure too, but we'll just give you the same judgments about typicality. Okay, so I mean, this is the basic structure of the argument. I mean, in terms of a cost-benefit analysis, if you attempted something like that, you have a major assumption is, of course, really this assumption that the initial probability distributions of interest are absolutely continuous or translation continuous. But this is a condition, I think, which, as I said, we know very little about these initial probability distributions, but it can at least be reasonably motivated and has also been motivated in philosophy and physics. Okay, and I mean, what you get is that mu e is a typicality measure, and so in terms of the benefits of the analysis, you of course have just this conceptual benefit that you just know, well, mu e can be justified from these premises. And you also get what is, I think, relatively nice. You get this link between typicality and probability, because as I mentioned, I mean, if you just say, well, that's a typicality measure, but then again, you don't know how it connects to experiments, then this will be always a question, how it connects to experiments, and premise 3 and 4 say something at least about that. And I mean, furthermore, I should also mention that, I mean, what is very often done, I mean, this is standard in statistical mechanics, they just say, well, this measure here is the probability measure. This is something which very often you find in physics, in foundations of physics, philosophy, literature, of course, just claims that, well, mu e is the probability measure. But then some philosophers, I think rightly so, like, could mention here von Lith and Leeds, Hemmo and Schenker, they have all pointed out that, well, seems quite dubious, the assumption that mu e is a probability measure, because these initial probabilities, they can be of various kinds. I mean, it's not clear why they should be just this specific microcanonical measure. And the good thing with this justification here is that it just allows for a very, very wide class of initial probability distributions. You know, it can be relatively uniform or not. It just needs to be translation continuous. Okay. I mean, the argument, really the same argument you can run for typicality measures in dynamical system theory. Premises remain the same, just express it in, I mean, it's just really the same premises. What you need here additionally, or maybe not additionally, I mean, for statistical mechanical systems, this automatically follows. I mean, statistical mechanical systems are just equivalent to the Lebesgue measure, so you get this automatically. But for dynamical systems, if you run that motivation, you just need that mu x of a set is 0 if and only if the Lebesgue measure is 0. This is also called the equivalence to the Lebesgue measure. This is something only for these dynamical systems you can run this kind of justification. But I mean, this condition is fulfilled for, I think, most of the standard systems anyway, like logistic map, temp map, and so on. Okay, really the same argument you get from the premises that this is a typicality measure and may not be unique, but doesn't matter because any other typicality measure will agree on which sets are typical. And then finally, one further uniqueness result, because I think it is interesting that you get also a uniqueness result about the typicality measure is when you add another premise. So if you add the premise that the system is ergodic, you get the uniqueness result. I mean, first some more comments about this condition of ergodicity. I mean, this is a very notorious condition which has a long-standing history in foundations of statistical mechanics. So many think that, I mean, Boltzmann didn't have the mathematics at that time, but many think that he invoked already something like the idea of ergodicity in his arguments. Didn't have the mathematics, but many think he, the pre-formal idea he invoked in his arguments. And then there's a lot of controversial discussion in the foundations of statistical mechanics whether systems in statistical mechanics are ergodic or not. I mean, here for this argument, this discussion isn't really that important because all I want to say is that if some of these systems turn out to be ergodic, which is certainly a possibility at least, then you actually even have a uniqueness result about the typicality measure. But I mean, to say at least something, you get that there is some evidence that gases are ergodic. The problem is really here that the mathematics, of course, in statistical mechanics is incredibly difficult. So you only have results for very idealized systems. And the only proper mathematical result you have is, and this is really a very, very big achievement, and they needed decades to prove it, is this Boltzmann-Sinay conjecture, which just says that the motion basically of hard spheres on a torus, on a 2- or 3-dimensional torus, is ergodic. And just in 2010, I think, this was finally proven has a very, very long history. Sinai first thought that he had actually proven it, but it then turned out that he hadn't. But now it seems to be the case that it has been proven. But this is only about very idealized systems. I mean, hard spheres are extremely idealized. It's really very much controversy whether these results can be extended to more realistic systems. But as I said, any case, I mean, my results will just show that if some systems are ergodic in statistical mechanics, then you get a uniqueness result. So, I mean, here's a definition of ergodicity. You don't need to understand it, but for those who are interested, there are various equivalent definitions of ergodicity. But this is one which is standardly given, which just means it's not, in a measure theoretic sense, indecomposable. So whenever you have that ft minus 1 of a equals a for all measurable a and all t, then this set is a full measure. So it can't be decomposed. This is the idea. There are other definitions too in terms of equivalence of time and space averages and so on. I don't go into this. But anyway, the important thing here is if you add this premise, then you actually get a uniqueness result. Immediately follows that the typicality measure is unique in statistical mechanics and also for dynamical systems. And as you have some interesting examples. I mean, something like the logistic map is, of course, ergodic. And so you get this measure we saw at the very beginning. With this kind of argument, you get that this is the unique typicality measure. And hard spheres as well, you get for these systems then that you have a unique typicality measure here. Okay, this is really what I wanted to say. Then I'll conclude. So the topic of the talk was really how to motivate or justify typicality measures. And a recent popular proposal is that measure should be interpreted as typicality measures, as counting states or as representing the relative size of sets of states. And the question is, how can you justify this choice of a typicality measure, which is usually not addressed, I think. And I just, first of all, of course, argued that Pitofsky's proposal that the uniform measure is the correct typicality measure does not fit the bill because there are clear counterexamples in dynamical system theory, and you have these technical problems where you use the map. Oh, sorry, psi, shouldn't be phi, psi preferred over other maps. And then I proposed this and tried to come up with at least a tentative proposal of how to justify typicality measures, which is basically a theorem. And the main premises are these probability distributions are translation continuous, that the typicality measure is invariant, and that you have this link between typicality and probability. What you get here is that the microcanonical measure and the standard measures used are a good choice of typicality measures. You get that at least from this assumption, and this is at least conceptually interesting, and you have this also nice empirical link, I think. Okay, well, I think this is all I wanted to say, so thanks very much, and I'm looking forward to your questions.
The subject of my talk, focus of my talk will be about the Carnap's suggested epsilon-reconstruction of theories that has been mentioned in the previous talk, and how it relates to scientific structuralism. And more specifically, what I'll try to do is to apply Carnap's epsilon reconstruction to mathematics and to see how this can be used to explicate the semantics of mathematical terms or expressions, and also to see how this squares with different versions of mathematical structuralism. So here's a brief outline of my talk. I'll first say a little bit about how Carnap viewed this epsilon reconstruction, how he set it up, and what its motivations were. And then I'll say a little bit more get a little bit more explicit about the logic of the epsilon operator and its choice semantics. And then in the third step, I'll turn to mathematics and see which kind of mathematical structuralism squares well with this kind of epsilon reconstruction of mathematical terms. And this is basically it. So the background of this is, of course, Carnap's late work in the logical
logic of science or logical reconstruction of science. And there are two sources, two documents where Carnap explicitly introduces this epsilon reconstruction. And the one published source is the 1961 article that was previously mentioned. And there is also this unpublished lecture, which was made public in a paper by Psillos in 2000. So these are the two main sources. And basically, what Carnap does is that he assumes a rich background language or background theory. Usually, I think it's a simple theory of type, or here in this case, a set theory. And an axiomatic theory is expressed as a complex formula in that language, where that is basically expresses the conjunction of the axioms of the theory. And the T terms here are the theoretical terms, and the O terms here represent the observational terms. Then you have Ramsification in the standard sense, and this is done by replacing the T terms by variables of a given type and binding them by existential quantifiers. And then in the third step, you have this explicit definition of T terms, and T here stands for the tuple of T terms occurring in that theory. And here you have in the definitions this term-forming epsilon operator, and basically intuitively what it says is that, so what the Ramsey sentence says is basically that there exists objects in our theoretical domain that have the features that the theory phi attributes to the T terms. And what the explicit definition here does is really give you an epsilon representative of these theoretical entities, if there is any. That is, if the theory is consistent. Carnap is not really explicit on his motivations for this, but I think you can find at least two in the recent literature. One is a point that I think was mentioned in Holger's talk yesterday, and that is to you reintroduce T terms in order to mimic informal deductive scientific reasoning with implicitly defined theoretical terms. So this has been stressed in a recent paper by Friedman. And the other motivation that is stressed in Psillos' paper is that Carnap intended to give a non-heuristic, atomistic specification of the theoretical terms in terms of his epsilon definitions. However, what interests me here in the present context more than these motivations is how this reconstruction, or if this reconstruction is compatible with the form of scientific structuralism. So in this recent paper by Michael Friedman, he suggests this, and he says, to quote, Carnap may in fact have articulated a version of structuralism that recognizes the strength of both instrumentalism and realism while simultaneously avoiding the philosophical pseudo-questions on which they appear substantially to differ. And the question, of course, is which version of what he calls a metaphysically neutral structuralism can we think of here? So in addressing this question, I will make, here in the present talk, I'll make three limiting assumptions in a way. So first, I'll assume what's usually called a Ulisean account of theoretical terms. I'll secondly focus exclusively on mathematical theories. And third, I'll see if the epsilon reconstruction is compatible with a particular kind of mathematical structuralism. So what I mean by a Ulisean account of theoretical terms, this is basically this understanding. Ulises says that a T term is just a term that is newly introduced by a theory, whereas an O term is really an old term, and a term that has been introduced before the theory in one way or the other. Could be another theory, could be by acquaintance or whatever. Second point, applied this to mathematics. So what I'm trying to do is to apply Carnap's approach to axiomatized mathematical theories, and the Ramsey sentence then really expresses the consistency of a theory. And the epsilon terms can be seen to specify the reference of terms like the successor, 0 plus, and so on, the group operation, and so on. And the Friedman's question or Friedman's claim can then be translated in a sense to this question, and this will be the main question in my talk here. Is this logical reconstruction of mathematical theories and their T-terms, their theoretical terms, compatible with mathematical structuralism, and with which version of mathematical structuralism? So this is the main question. Before addressing this, it seems useful to say a little bit more about the logic of this epsilon term or this epsilon operator and its intended semantics. So as I mentioned before, the epsilon terms were introduced by Hilbert and usually understood as a term-forming operator. That is, if A is a formula with variable x occurring free, then epsilon of x of A of x is a term where all the occurrences of x are bound. And what you can do is describe or specify the behavior of these terms in your language by certain axioms. And what Carnap actually did, so this was one of his motivations, was to show that by using this operator in explicitly defining terms, you can actually recover what he called his Carnap sentence. You can actually prove the Carnap sentence by definitions using this operator and the Ramsey sentence. But I think what's even more so important for Carnap, and this is really the crucial idea for Carnap, is that it's the specific semantics that comes with these terms. So at one point, that's in the 61 paper, I think, he says that the epsilon symbol was intentionally introduced by Hilbert as an indeterminate constant. Its meaning is specified only to the extent that any non-empty set has exactly one representative, and that this representative is an element of the set. If it has more than one element, then nothing is said as to which one of these elements is the representative. So this is really the motivating idea for Carnap for using this. And of course, this is rather imprecise, and Carnap does not really specify how the semantics look like, but usually in modern epsilon calculi, you present the semantics in terms of a choice, in terms of using choice functions, or in terms of a choice semantics. And this is basically the fact that you take a model as a triple consisting of a standard domain and a standard interpretation functions to the non-logical constants, and a choice function on the from the power set of D to D, such that for any subset of that domain, the choice function assigns has a value, an element in X if X is non-empty, and any other element in D if it is empty. So this is a classical interpretation of the choice function underlying the epsilon operators. And given this, you can specify the reference or make precise the reference of epsilon terms in the following way. You just say that this is based on a paper by Richard Zach. So you say that the value of this epsilon term, where A is a formula, you say that the value of this epsilon term is really the output of the choice function for the value of this formula. And this is this is basically the set or the subset of D defined by the formula. So the reference of an E term is really the value of the choice function for this set. And what's interesting is that this, what Carnap called the indeterminateness of the reference of epsilon terms is very close, in fact, a variant of how you treat instantial terms semantically in the context of natural deduction. So in particularly instantial terms connected to the use of existential instantiation and quantifier introduction rule. So, and this is usually in recent literature, this is termed arbitrary reference. So for instance, in a recent paper by Breckenridge and Margitor, they specify arbitrary reference underlying these instantial terms in the following way. They say it's possible to fix the reference of an expression arbitrarily. When we do so, the expression receives its ordinary kind of semantic value. So it receives an ordinary kind of value, though we do not and cannot know which value in particular it receives. I think this is really, this idea of arbitrary reference is really what lies at the basis of this use of epsilon terms. And I think, at least for Carnap, this was the main motivating idea. And just as a side note, note that this understanding of instantial terms is different to the proposal that can be found in Kit Fine's work, where he says that these terms refer classically, but to non-classical objects. So they refer to abstract objects. Whereas here, you have the case that you have a kind of non-classical reference based on the choice semantics, but you actually refer to your standard object in your standard domain D. Okay, so question is now, how does this relate to mathematical structuralism, and in particularly to which theory of mathematical structures this fits best. And very roughly, the idea of mathematical structuralism is the view that that mathematics studies the abstract structure or structural properties of objects like numbers, graphs, groups, etc., without regard for their intrinsic qualities. And you have a number of different theories that try to cash this out, and that basically all have to do with making claims about the proper ontology of these abstract structures. So you have typical classifications of these views. For instance, the distinction between eliminative and non-eliminative versions of structuralism. These are basically realists about structures, abstract structures like Shapiro. Non-eliminative views would hold that the talk about abstract structures is really shorthand. I think that's Shapiro's phrase, shorthand for the generalization of models of your theory. And another classification would be the distinction between ante-Rem and in-Re structures, and these concern the ontological dependence relation between abstract structures and their concrete instantiations. So ante-Rem structuralists like Shapiro would hold that abstract structures are actually ontologically independent or prior to concrete mathematical objects, whereas in-Re structuralists would deny this. So Reck and Price give a nice overview over the different accounts you can find in the literature. And what's interesting is that in a recent paper by John Burgess that has not been published yet, putting structuralism in its place, what Burgess tries to do in this paper is, in a way, to take a step back and say that all these ontological theories about the nature of mathematical structures are really have a common root, the same common motivation, and they are generalizations of a common family of phenomena that you find in mathematics, and these are what he calls the indifference to identification. And this can concern the indifference of the identification of mathematical objects. So for instance, the questions concerning the identity of the natural number 2 and the real number 2, and they can also concern the proper identifying definition of an object, so the reals as cuts or sequences, for instance, and in our context, most importantly, they can concern questions about the reference of mathematical terms. And with respect to this third kind of indifference, Burgess holds, based on Shapiro's work, I think to some extent, that expressions like 2 or the group operation, but also the real number symbol, actually function as parameters, that is, as instantial terms in the sense specified above in mathematical discourse. And what's interesting about his account is that he says different interpretations of how these parameters refer lead to give us different versions of mathematical structuralisms. So what he says is that you find the idea of undetermined reference in terms of parameters in all different forms in different types of structuralisms. And what's really relevant here is how you specify the semantics of these terms. So for instance, parameters in this sense, or arbitrary constants, have been used in work on anti-Rame structuralism. So for instance, in a recent paper by Shapiro, Shapiro suggests that you can use the term for the imaginary unit as a parameter that denotes arbitrarily, in a sense, either one of two structurally indiscernible places, I and minus I, in a given anti-Rame structure of complex numbers. And a somewhat similar idea, but now in the context of eliminative structuralism, can be found in a recent paper by Pettigrew, where he suggests that in this context, so in context of what he calls Aristotelian theories of mathematics or eliminative structuralisms, mathematics expressions like this one really should be or can be understood as free variables, or as what he calls contextually dedicated free variables. And it's important that they are dedicated by context, because these expressions can, of course, occur in different theoretical contexts, right? So what he says is, what you have to add to the fact that these terms act semantically like free variables is theoretical constraints like this one. So you have to say that for instance, so you have to say like these satisfy the axioms of a complete ordered field, or they satisfy the axioms of a complex field, or satisfy the ring axioms, and so on. So you see that these two cases show that you can use parameters or interpret the semantics of parameters in two different senses. In the one sense, they are treated as constants that refer arbitrarily, in the sense, to abstract structures or places in an abstract structure. But you can also interpret them as free variables that, in a way, range over your models of a given theory. But then there is a third interpretation that is stressed by Burgess in his paper, a third version of semantic indifference that he characterizes as follows. He says that there is another account would be that a parameter like a Hilbert epsilon term denote some specific but unknown object. And he says that it is this lack of knowledge that explains the crucial property of parameters. So that's a third interpretation of the semantics of parameters. And what he says that this leads actually to a altogether different third account of mathematical structures. He says that what you get here is a kind of epistemicist structuralism that hasn't been discussed in the literature, really, although Shapiro has mentioned it or so. So two questions arise here. First, how does this epistemicist structuralism look like? And second, how precisely can we use, as suggested by Burgess here, how can we use epsilon terms in order to specify the semantics of mathematical expressions within this kind of philosophical background, within this epistemic structuralism? I think the only place where a version of structuralism that fits this picture has been discussed in the literature is a paper by Erich Reck and Price, and they called this particular version relative structuralism. And what's interesting is that, at least prima facie, it's very Kanapian in spirit, you could say. So basically what it is, it's a metaphysically neutral account of structures. So it doesn't really say whether there exist abstract structures, but it doesn't say that there don't exist abstract structures either. And what it assumes is a non-structural or interpreted background theory, like type theory or set theory, just as in Carnap's case. And the objects are represented in that framework as structured, for instance, as structured sets in the cumulative hierarchy. And the central idea about this structuralism is semantic, basically. And this is what Reck and Price call the relativity of reference of mathematical terms. That is the fact that the reference of a term like successor, zero, group operation is specified relative to a particular model or a particular set theoretic representation of a group, say, but the choice of this group is completely arbitrary. So you could pick any set theoretic representation of a group you could find. So in the slogan, you could say relative structuralism is really a realism about sets and a theory of arbitrary reference for mathematical terms. So just to reiterate this, terms are treated as constants here, and not as free variables in Pettigrew's account. And they refer arbitrarily to concrete mathematical objects or set theoretic representations of these objects, and not to abstract structures or places in structures as in Shapiro's account. And really the crucial feature to stress this again is that their reference is specified relative to an arbitrary choice of a particular object. That is, one picks out any object in the category in question and then fixes the reference of the terms, group operation and so on, relative to this choice. And I think that the main point I want to make here is that Carnap's Epsilon-Reconstruction gives a really natural explication of the semantics of theoretical terms in this framework, given this structuralist conception of mathematics. And what's important is that it satisfies, so Carnap's reconstruction satisfies the two central desiderata here, namely that the reference is indeterminate and that terms like 0, plus, times, and so on must be subject to certain theoretical constraints, theoretical contexts, right? So in Carnap's framework, arbitrary reference, that is the first point, is expressed by the epsilon operator and its choice semantics, and the theoretical constraints come in by the Ramsey sentence, by the given Ramsey sentence that occurs in the definitions of the definition of a term. To give you one rather simple example, consider the theory of monoids, algebraic structures. That's basically a triple, a set, a group operation, a monoid operation, and a neutral or identity element that satisfies these two axioms, associativity and the existence of an identity element. The Ramsey sentence of such a theory, and recall that phi, big phi, is just a conjunction basically of these two axioms, is this here. It's this formula. And the epsilon definition in Carnap's sense is really this sentence here. And so recall the two desiderata that we want to capture. The arbitrariness, that's given by the use of the epsilon operator here. So you pick out any arbitrary object. And the theoretical constraint is, of course, given by this here. So this specifies that the representative that you get, that the epsilon representative that you get is actually a monoid and not another algebraic structure, for instance. So this is basically it. Just final one last slide. I think that there are different ways, and this is basically future work, plan for future work. There are different ways in which this epsilon reconstruction of theories might be applied to topics that are interesting and relevant in mathematical structuralism. So one issue would be to actually formulate a new eliminative theory of structures based on these epsilon terms. And you could, along the lines of thinking of a structure as the structure of a particular mathematical object as the epsilon representative of a given isomorphism class, for instance. And then you could say that you could have a standard structure abstraction principle where you would say that if two objects are isomorphic, then they have the same epsilon representative and vice versa. And based on this, you could try to explicate several interstructural relations like substructures or structural extensions based on epsilon terms. And what you could also try to do is explicate a notion of structural continuity between successor theories or theory extensions. And finally, what you could do is try to explicate this notion of cross-structural identity in domain extensions. So as the example I mentioned before was the identity, the question whether the natural number 2 should be seen as identical to the real number 2 and so on. So these would be issues that one could investigate in, but that's future work, so I'll stop here. Thanks.
Okay, so the rough idea in general of criteria of empirical significance, not for terms, but in general, is to somehow determine which statements have empirical import, where empirical import, what that exactly is, depends on a lot of things. Typically, it's spelled out as being somehow inferentially related to clearly empirical claims. So, and the kind of inference that you can use might be inductive or it might be deductive. And I'm going to talk about deductive criteria. And then you might want to connect your statement directly from directly to your empirical claims, or you might want to first connect your terms to empirical claims and then say that a statement is empirically significant if and only if it contains only empirical terms. And this is, again, what I want to talk about today. Well, and then finally, there is a lot of possibility for logical inference too, and I'm going to work in higher order logic here. to a huge extent simply because most of the criteria that I'm going to discuss have been suggested in higher order logic, and they also assume that the empirical claims are actually phrased in higher order logic. So the observation terms include all of mathematics, what Carnap, I think, called the extended observation language. But apart from that, it's the standard account. So I have my vocabulary V, and I bipartition that into basic and auxiliary terms. And I'm going to follow Reichenbach here and just assume that my basic vocabulary B is not necessarily observational, but just in this context, uncontroversial. And specifically, it's directly interpreted, so I don't have to think about any theory in this respect. And this is actually really important for the criteria to actually make sense. It's precisely interpreted. So, and the auxiliary vocabulary is then only interpreted through the interpretation of B and the accepted sentences that we have as background assumptions, for example. Yeah, and then if we have this precise interpretation, then we can use the Ramsey sentence very neatly to describe our criteria of empirical significance. Because, well, this is just my standard notation here. My basic sentences here as a tuple, my auxiliary terms here as a tuple, and I existentially quantify over the auxiliary terms. And then, and this is basically what Jeff referred to when he said that if we identify a theory with its Ramsey sentence, then the truth of a theory is just its empirical adequacy. Because if I have a basic structure, this is what I do with the B here, a basic structure that makes the Ramsey sentence true, that just means that there is some, not necessarily the real structure or something like that, there is just some structure that expands the basic structure. And so the reduct of this other some structure B is just the basic structure. And in this expansion of the basic structure, sigma is true. Okay.
Can I just ask, do you let fracture be, you don't let the domain grow?
No. Those are, well, if you do it, things get a bit more complicated, and you cannot phrase it nicely in Ramsey sentences anymore. And this is basically the main reason why I don't let the domain grow. And basically, this is the assumption that is behind many of the criteria that I'm going to discuss. And so my hands are in a sense bound here. Okay, and if you use the Ramsey sentence, then you can actually phrase basically all major extant criteria of empirical significance for sentences in a very neat way. And so here I'm going to win the Ramsey sentence bingo of the conference. You can phrase them all in terms of Ramsey sentences. And so falsifiability of sigma relative to our supplementary assumption theta is then just, well, if you think of the Ramsey sentence as the empirical content, is then just the demand that the empirical content of theta has to be, must not be as great as the empirical content of sigma and theta together. And basically just means that there is some observation sentence that I can infer from sigma and theta that I cannot infer from theta alone. And Hempel already noticed that you can get verifiability out of falsifiability by just negating the sentence that you're interested in. And so if you do exactly that, then you get verifiability. Now, you can combine these two, and this is a criterion that has been suggested independently by David Runin and in a more semantic way by Marian Przewonsky, and just say a sentence sigma is empirically significant if and only if it is either verifiable or falsifiable relative to theta, and then you can really just, in this case, also just build the disjunction here and get this. And this is actually the weakest criterion that I know of that has ever been suggested for the empirical significance of sentences. And the strongest criterion that I know of, apart from straightforward translatability of a sentence, is this determinacy. So sigma is determined by theta if and only if its truth value is determined, that is, in every expansion to a model of my background assumptions theta,
the sigma is either true or in all the expansions it's false. And this is exactly expressed by this Ramsey formulation here. And it basically just means that I can't expand the same basic structure to one model in which sigma is true and to one model in which sigma is false. And this criterion has been suggested also by Przemwanski, but independently of Przemwanski by Pat Suppies in connection with measurement, because Suppies gets there by demanding that the truth value of a sentence is invariant under all admissible transformations, given a specific basic structure. And these all admissible transformations basically then give you all the different expansions to models of theta. Now, in that sense, I actually do think that this search for a criterion of significance has been a raging success, because we have 4 really neat criteria that have a very clear logical structure, that do something very specific, and depending on what we want our sentences to do, we can use the different criteria. Well, and yeah, we could say we're done. The big problem here is this relative to theta part. And so we still have defined significance only relative to some supplementary assumptions. And it's basically there where things really got difficult. And when, for example, Ayer suggests his criterion, then he assumes that this set of supplementary assumptions itself consists of already empirically significant sentences. And from there, it becomes a complete disaster. And then you really have a long history of people who try to patch up Ayer's criterion because it turned out to be trivial, and then get their criterion trivialized as well, and it goes on for that. And so it goes on forever. And so in the end, this one was the problem. And then we get the history of trivializations. And at least according to Hempel, this history of trivializations was one reason why people were looking for different criteria, namely for criteria for sentences. And this is what I want to talk about. Sadly, though, my overall conclusion is going to be that this search for the criteria for terms is also kind of a disaster, because the criteria are basically unmotivated and don't do what they're supposed to do. And so we should have stuck with the criteria for sentences right from the beginning. So what I'm going to talk about is, well, there are basically not 4, but in this case 3 criteria for terms. One is definability, and then there are slight wrinkles to that. Then there is reducibility, and finally there is this is the one suggested in testability and meaning. And then finally there is B-dependence, which is basically also a criterion suggested by Carnap. And the reason, well, and then finally I'm going to talk not about criteria not for single terms, but for sets thereof. And the reason that I'm still talking about it, even though I think the search has been kind of a disaster, is, well, basically for 3 reasons. The first one is it's interesting to know why it's a disaster. And connected to that, some people actually do still think that this search has not been completely pointless. And specifically, I think James Justice has argued that Carnap's last criterion is actually still a kind of a good idea. There is no reason that there is something wrong with it. I think there is, and I'm going to argue for that. And well, and finally, I actually think that the criteria can be used for other stuff, not for empirical significance, but they have their uses. And so this would be sort of the string theory defense for criteria for terms, because so the idea is that even if string theory were not to give us any interesting physics, it still gave us a lot of interesting mathematics that can be used in other areas. And so this is how I think of criteria for terms. First criterion, definability. This is just the strongest criterion ever suggested, specifically by Carnap in the Aufbau, where you say that my auxiliary relation AI is definable by theta if and only if there is a B formula such that in all models of theta, this B formula is coextensive with my auxiliary term. And well, this is sort of even in reductionist terms, this would be the most strict demand for reducibility that is typically suggested. And you can switch the quantifier though. So I have said that there is one formula such that in every model this formula is coextensive. You can switch it around and say that, and demand only that for each model of theta there is one formula that is coextensive. And then you get definability in every model. And this is exactly what I just said. So in every model of theta I have a coextensive formula. And if you think of definability sort of in reductionist terms, then what you then you have something like a type identity between the formula beta and the auxiliary term AI. And here, what you get here is something like a token identity if you think of the different models of theta as the different situations that you can find yourself in. So the different worlds that are allowed according to theta. Because now I have this identity for all contexts, but no identity for all contexts at once. And if you then further think of the basic terms as the terms of physics, you end up with something very close to what Fodor has called non-reductive, well, Fodor has suggested and could be called non-reductive physicalism. So I don't have an identity between auxiliary terms and physical or special science terms and physical terms. And interestingly enough, this definability in every model can be phrased equivalently in something that is very close to our normal idea of explicit definitions. And that is just we use a disjunction of explicit definitions. The idea is pretty clear. For all models, I get basically one disjunct, which is equivalent to my auxiliary term. And if you remember Fodor's article, there he has this weird construction where he says, okay, I have an explicit definition of my auxiliary term or of my special science term with a definiance that is a disjunction of physics terms. And I really think what he should have written and what fits way better with his overall argument in the paper is something like this. You don't have an explicit definition with a long disjunct in the definiance, but you have a long disjunct of explicit definitions. And I think actually this fits. So and this is more or less my first, no, this is clearly my first suggested jury-rigging use of criteria of empirical significance, namely for questions of reduction. Yes?
This is probably Herbrandization, right?
I have absolutely no idea. It might be.
Well, if it is, then the set J may not be recursive.
That could also be. Yeah. I mean, it's I'm sort of this is all very pedestrian logic-wise. No? So I'm not thinking about recursion here at all. And I mean, this thing can be in any way infinite. After all, I have to get one disjunct for each of the models.
Yeah, but I mean, infinite is not the problem. I mean,
no, infinite in terrible ways.
Yeah, exactly.
Yeah. No, this could very well be. I mean, in first-order logic, this is actually finite and nice because of compactness, but it doesn't hold in general. Yeah, and that's it. Oh yeah, so now the relation to the criteria of sentence, because as I've said, we actually have kind of nice criteria for sentences. It's clear, well, this is just basic definition theory, that definability entails translatability. So if every term in my sentence is definable, then the whole sentence is translatable. A nice thing is that definability in every model leads to determination. And this is nice to a certain extent because definability in every model has been suggested by Luce as a criterion of empirical significance for terms, also in connection with invariance of truth values of extensions for measurement procedures. And so if you go to the terms and demand this invariance the way Luce did, then you end up with a criterion that connects nicely to the invariance criterion for sentences that Sulpice demanded, both in the connection of measurements. But of course, those are only sufficient conditions. The problem is that they are not necessary at all. So I can have translatable sentences in which terms occur non-vacuously that are not definable or definable in every model. So the suggestion then is to look for something weaker. And well, Carnap has suggested reducibility. which is basically a necessary condition or a sufficient condition that is not trivial. So I want to have some formula beta, which I will call reduction formula, that has at least in one model of theta, at least one a non-trivial extension or a non-empty extension. And this extension then, this formula is either a sufficient condition for belonging to AI or a sufficient condition for not belonging to AI, and thus provides a necessary condition. The problem with that is a little bit that we might still have, the beta formula is kind of unrestricted. It might not contain any basic term at all. And so to have something that actually connects to basic terms rather than, for example, just rather than just logical terms, we can demand non-logical reducibility. And this is adds the demand that the reduction formula should not be equivalent to one that is consists only logical constants, contains only logical constants. So, yeah, and if I really were to go for the king of the Ramsey sentence crown here, I can phrase that also in terms of Ramsey sentences if you really want to. Yeah, the relation to the criteria of sentences is a bit, well, this is kind of extra tragic. It's sort of a slightly weakening of the overall strong criterion of definability, and what you get out of it is basically nothing. So you can have sentences that contain only reducible or non-logical reducible terms, but that are neither falsifiable nor verifiable, so don't even fulfill the weakest known criterion for sentences. And the other way around, it doesn't actually look better. So even if I have a sentence that is translatable, it might still contain terms that are not reducible or non-logically reducible. So it's neither a sufficient nor a necessary condition, and you can basically use it for nothing. Yeah, so we can go one step weaker and demand B-dependence. And this can also, again, be phrased nicely in Ramsey sentences. And here it actually becomes important that I'm using a subscript for the vocabulary that remains after extensionally generalizing on the vocabulary. And so we say that term AI, an auxiliary term, is B-dependent in theta if and only if the Ramsey sentence for theta and the basic terms in conjunction with the Ramsey sentence for theta and the auxiliary term does not already entail the Ramsey sentence for theta and the union of the basic sentences and the auxiliary term. And what this basically means is that I can't just choose my the interpretation of my auxiliary term nilly-willy, as long as it's at all possible to interpret my auxiliary term like that, and combine this interpretation with the interpretation of the basic terms and still get a model of theta. This is what this effectively requires. And this connection is strictly weaker than non-logical reducibility. So if something is non-logically reducible, then it's also B-dependent. And this now actually does connect very neatly to Carnap's last criterion of empirical significance for terms. This is the first step in Carnap's criterion. His criterion is actually longer, but this would be the first empirically significant term according to Carnap, and then there's a long chain of further empirically significant terms. So the idea is that we have an auxiliary term, and then we have one B sentence B, beta, and an AI sentence, that is a sentence that contains only the auxiliary term, alpha. And this AI sentence, alpha, should be compatible with theta and should entail my B sentence, beta, but in conjunction with theta. But theta itself should not actually contain the B sentence. And now the sentence alpha is kind of weird thing, because there is not much that you can say about alpha if you're only allowed to use logical constants otherwise. And so you basically can only say something about the cardinality of the extension of alpha. And the result of that is that you actually have situations in which you have a reducible term that is not actually Carnap significant. And, well, this was not exactly what Carnap had in mind, I assume. And, well, it's also not what he assumes when he argues that his criterion is not too strong. Because when he does that, he uses a very unique, let me put it that way, unique interpretation of his domain. He assumes for that all objects in the domain, in his domain, are actually numbered, and so he can refer to those objects by mathematical terms. And thus, he can directly interpret, give the extension of AI directly by just naming the numbers, and still the result, according to him, is a purely mathematical expression, except for the occurrence of this one auxiliary term. And I honestly don't know whether that is even consistent. I'm really not sure how that is supposed to work precisely, because, well, you're really naming objects in your name, specific ones. And so it's hard to argue, I assume, that this is still a mathematical term. But the effect of that is that I can give a direct interpretation of my auxiliary term. And if you do that, then this thing becomes equivalent to B-dependence. And so we can phrase this very nicely in the way I have done before. Okay. So, but there is, so apart from that it's formulated a bit weird, it seems a completely fine criterion as far as the criteria in general go. But I have quite a bit of things to say about the motivation that Carnap produces. And while I, in general, really admire Carnap stuff, this one I don't admire at all. So he starts out with sort of the most, the most base natural language analysis. So how he ends up with this definition there is just, he says, well, this is kind of what we mean by empirical significance, don't we? And then writes it out, and he's done. So there is no subtle analysis of how this explicates the original notion according to his own criteria of explication or something like that. It's really just, this is what we mean, and we're done. And then he just, the next step then is he does show non-triviality according to, or tries to show at least. Yeah, so the other thing is, and this is a problem that this criterion shares with all the other criteria that I have discussed so far, it's also defined relative to supplementary assumptions theta. And the supplementary assumptions, after all, were the ones that started the whole mess with the trivialization proofs in the first place. So if we define everything relative to theta, then we could have just stuck with the criteria for sentences and not go the route of defining criteria for terms. And because then we have really good criteria. Falsifiability is one. And the weird thing here is that Carnap, in a sense, agrees because of this. Because he demands that the alpha sentence is, in a sense, falsifiable because it entails a basic term that is not a basic sentence that is not entailed by theta alone. And this can be phrased like that. And so what he does is he motivates his criterion by assuming a criterion of empirical significance for sentences, gets a criterion for the empirical significance of terms, and then with the help of this criterion defines a new criterion for sentences by saying a sentence is significant if and only if it contains only the terms that are significant according to this criterion. And so this is, well, I would say at least the motivation for it is inconsistent. Good. So, but this is really just the motivation. I just wanted to point out that there is no, that the motivation really has almost no legs. And so there's nothing wrong in principle with B-dependence, though. So this is why one could go a bit further. And if you remember, the B-dependence connects nicely to non-logical reducibility, but we can also define a criterion that connects nicely to reducibility. And this is just, this has been suggested by Rosenbaum. He says that a term AI is given effective meaning by theta if and only if the Ramsey sentence of theta for B, the Ramsey sentence for theta and B does not already entail the Ramsey sentence for theta and the union of B and A. And the difference to B dependence is just that this here stands alone and there is no other conjunct for the Ramsey sentence for theta and AI itself. And then we indeed have sort of reached a weakest criterion. So we can, it's then straightforward to show that if a term is not given effective meaning by theta, then if we have any sentence that contains only this auxiliary term and otherwise basic sentences that is not already falsifiable by itself, then it can't be made falsifiable by adding theta. So it's also not falsifiable relative to theta. And this criterion connects really nicely to reducibility. So this is strictly stronger. And we end up with these relations. So on the left side, we have the straight line from definability to definability in every model, reducibility and given effective meaning. And on the right side, this takes into account that we don't want to have purely logical sentences or purely logical formulas as observational or basic formulas. And then here, this is sort of the interesting result about the Carnap significance, that it's just B dependence. But so far, I have only talked about single sentences. I mean, in the end, we want to build interesting sentences with lots of auxiliary terms. And so Carnap has suggested, in connection with his criterion of reducibility, has suggested chain reducibility. And relation AI is chain reducible to the basic terms in theta if and only if there is such a chain A and then A1 to A ik, with the last term here being just my original relation that I'm interested in. And each element of this chain here is reducible to itself reducible to the basic terms and the previous combined with the previously established reducible terms. And the first one, this here, has to be reducible by itself. Okay, the problem with that is that chain reducibility is not actually sufficient for reducibility or even for a term having effective meaning. So we can easily build sentences with chain reducible terms that are have basically no connection to observations whatsoever. And if Carnap does the same thing then later with his new criterion, his latest criterion of Carnap significance, and unsurprisingly, since it's even weaker, this doesn't fare any better. So, but the good thing is we have already criteria of significance for terms that can be easily generalized, namely B dependence. Namely B dependence. Zack. And there we can just take the original definition of B dependence, and instead of using a single term AI, just use a set thereof, and then say that the Ramsey sentence for B, the Ramsey sentence for I, should not already entail the Ramsey sentence for B union I. And if we demand this, then there is a good case to be made that the resulting, that a set of terms that is not B dependent is actually mathematical for the following reason. So if we have a model of theta where theta is just a sentence containing only I terms, and then we have any bijection to the domain of a model, or sigma, I wanted to say, any bijection to domain of a model of theta, then I can build a new model of theta and sigma that interprets all the terms in I according to the bijection G here. And so specifically, that means I can permute the extensions of my B independent terms and again get a model of sigma and theta. So if those two models here have the same domain. And this actually is exactly the argument that Dimopoulos gives in his paper on the rational reconstruction of our theoretical knowledge, to argue that in the Carnap sentence, all terms are mathematical. The only thing is that think Pierre Wagner has pointed that out as the first one. In Demopolis' case, that argument doesn't actually work. You can't permute nilly-willy the extensions of your auxiliary terms in the Carnap sentence. One instance is just an explicitly defined auxiliary term. You can't just permute its extension around on the domain. Well, but in this case, it actually does work. And so assuming that the overall idea that Demopolis has is right, then B-dependence is a sufficient criterion for mathematicity of a set of terms. There is one wrinkle to the whole thing, and that is that even if I have a sentence theta in which that makes a set of terms I mathematical, I can actually sort of surreptitiously make them non-mathematical, that is B-dependent, by adding a sentence to my sentence theta that does not contain the original terms. So I have my sentences about I, and they are mathematical. I have this permutation argument here. Everything is fine. But then I add somewhere else in my belief system or in my background assumptions, I add a different sentence that doesn't even mention my terms I. And then they become B-dependent, and the permutation argument doesn't work anymore. And this, so we have sort of a temporarily mathematical term, or set of mathematical terms. This can then be avoided by having one even weaker criterion, or stronger criterion, B isolation, where I just say that if I have the Ramsey sentence for all the vocabulary, all the terms except I, combine it with the Ramsey sentence for all the terms I, if that already entails my whole theory theta, then this set I here is B-determined. B-isolated. Basically, no matter how I interpret any of the other terms, I can always interpret those terms in I nilly-willy. And in that case, if a set of terms is isolated once, it will be isolated forever unless I explicitly mention those terms and say, okay, from now on, I declare continuity to mean it's green or something like that. And then but then I have to do something like that explicitly. Yeah, and so this is the second application that I suggest for the criteria of empirical significance, namely as a criterion of mathematicity of concepts. And that's it. So these here are the results about their relations, about the relations of the criteria to the criteria of sentences. And the typical one is that if everything is definable, I end up with translatability. This is a bit more interesting. It says if it's definable in every model, then the whole sentence is determined. This is the sad part of the whole thing. Reducibility doesn't do anything. I have no necessary condition, no sufficient condition that I could use. And then finally here, this is the kind of complicated use of given effective meaning. It basically just means that it doesn't make a non-falsifiable sentence falsifiable if I then add my theta here. These are, to me, the most interesting results, namely that I can use definability in every model for to phrase non-reductive physicalism in a nice way, and I can use non-B-dependent terms as mathematical ones, and B-isolated terms as mathematical ones that also stay mathematical unless I do something very explicit and fishy. And that's it. Thank you very much.
Oh.